KS ഇടണോ വേണ്ടല്ലോ. കിട്ടിയാൽ മതി. ആ, അച്ഛനൊക്കെ കിട്ടിയാൽ മതി.
So, good morning, good afternoon, and good evening to all the respected professors and the dignitaries that have joined this meeting. We are extremely proud to welcome you all to the 10th International Webinar on Recent Trends in Statistical Theory and Applications. It's a journey of 4 days into the academical world of statistics, and we are beginning the journey today. So this international webinar is organized by the Department of Statistics, University of Kerala, along with the School of Physical and Mathematical Sciences, University of Kerala, and the International Statistical Fraternity, in association with the Indian Society for Probability and Statistics and the Kerala Statistical Association. We are extremely happy to welcome you all. And let us begin the program by showing our gratitude to the Almighty. I request Devi Gauri Nandana for the prayer song. Gauri, over to you.
ഇങ്ങുമിങ്ങും നിറയും വെളിച്ചമേ എൻ മനസ്സിൽ ശാന്തിയാകണമേ എന്റെ പാദം ഇടരാതിരിക്കുവാൻ എന്നും എന്നിൽ കൃപ ചൊരിയണമേ പൂവിലൂറുന്ന പുഞ്ചിരി നീയല്ലോ പുസ്തകം തരും ജ്ഞാനവും നീയല്ലോ പുല്ലുമാടവും പൂമണി മേടലും പുണ്യമായി തരും ശക്തിയും നീയല്ലോ ഇങ്ങുമിങ്ങും നിറയും വെളിച്ചമേ എൻ മനസ്സിൽ നീ ശാന്തിയാകണമേ എന്റെ പാദം ഇടരാതിരിക്കുവാൻ എന്നും എന്നിൽ കൃപ ചൊരിയണമേ.
Song. Now, I would like to invite Dr. C. Satish Kumar, who is actually the driving force behind all of these endeavors, as well as the Director, School of Physical and Mathematical Sciences, University of Kerala, the former HOD Department of Statistics, University of Kerala, and actually the driving force behind ISF also. So I request you, sir, to please welcome the gathering. Over to you, sir.
Okay, very warm good morning, good afternoon, and good evening to all. I hope everyone can hear me. And happy National Stress Day. We are in the
in Statistical Theory and Applications 2025, in conjunction with the 9th Annual Convention of Statistical Fraternity Kerala, SFK, and the 19th National Statistics Day celebrations 2025 during June 29 this year to July 2nd, along with other organizations. In this age of data revolution,
ಸಾರು ಬೇರೆ ಜಾಯಿನ್ ಇರುತ್ತಿಲ್ಲ ಕಲ್ಯಾಣ ಸಾರು ಶಿಂದೆ ಸಾರು ಸಾರು ಓಕೆ 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 ಸರಿ ಸರಿ
Sati sir, should we call him?
Sir, Kalyan Ramar sir, please unmute.
Um, so it's good morning, friends, from India, and I am only happy to be part of the national studies elections, which have been going on for quite some years in a particular formatted way, and I can only appreciate the kind of difficulties they encounter and organize such a conference. If you just look at the list of participants, you can really understand the kind of people who are coming and taking part in this wonderful event. And of course, this we could not expect in our days, because this is just because of the current availability of computer facilities that Satish and his crew is organizing such a program for about 3 or 4 days. Actually, these people will be sitting throughout the day and guiding the entire process of this particular procedures. Now, the Indian Statistical Institute was inaugurated in a meeting on 17th December 1931. And why I am saying this is, at that time, that is by 31 also, the Highness Maharana of Rangpur, that is Rangpur state, inaugurated the institutes with statistics as one of the components. It is a central research institute. There are two departments, one department on statistical theoretical problems, another one on the practical problems of the what do you call statistics, that is economic statistics department, which happened to be one of the major data collection organizations for this. So we have some equality with respect to the international, the national level, national statistics day, even though we will have a separate day on Kerala Statistics Day, which is having the same kind of say acceptability. Now, the statistics, with all the facilities available in India, it is being seen widely just because of the journal Sankhya. The Sankhya was actually inaugurated in 1933, and there was a committee formed at the initiation of Indian Statistical Institute, consisting of say R.W. Brooke, K.B. Madhav, P.C. Mahalanobis, C.L. Mehta, and H. Sinha as convener to think about generating a new journal. And of course, the Kerala Statistical Association generated a journal, and we know the difficulties that are there available for bringing up an academic journal. So naturally, these people think of all difficulties, and finally they gave shape to Sankhya as such. And the publication was not easy because it was costly in those days. Somehow or other, P.C. Mahalanobis organized finance from among themselves and generated it. Like that, this particular journal was given the name Sankhya. In the words of P.C. Mahalanobis himself, we believe that the idea underlying this integral concept of statistics finds adequate expression in the ancient Indian word Sankhya. In ordinary meaning, Sankhya means number, but in special meaning, you see that it is determinate knowledge. Determinate knowledge means what? And this required further disposition about it. So this particular problem was considered by one of my colleagues by name Professor T.K. Unitan, and he has brought out a wonderful paper on this particular aspect of Sankhya. Because Sankhyan system of inquiry is one of the six systems in Indian inquiry systems, which depends upon what you call as uh, perception, experiment, inference. So these three aspects he gave shape to the meaning and explained why this Sankhya means something very important as far as statistics is concerned. Actually, this particular paper was appreciated by Chinmayananda himself directly. I was just witnessing it. So this is something very interesting, and the journal is bringing out, and it had its own problems. And similarly, with respect to the organization of this seminar, with so many people coming from almost all area in the world, it's not very easy thing. And this year, Dr. Satish Kumar and his team is doing wonderfully well for the last 10 or 11 years. And so this has to be continued in every respect. And I can assure him that any help towards this particular aspect will always be provided from my end to the extent possible. So, wishing the function all success, and I have all the blessings for the conference to come to its logical conclusion. Thank you.
Thank you.
Thank you. Thank you, dear Professor, for your blessings and your words on the history of Sankhya. Actually, I would like to remind our participants that our distinguished chief guest is actually an integral part of the Sankhya journal, of which our dear professor was saying now. We have with us Professor R.L. Shinde, who is a senior professor in the Department of Statistics, KBC Maharashtra University, and he is also the secretary of ISPS. He is among us to say a few words of felicitation to the event. Professor R.L. Shinde, we are extremely proud to have you among us, and I request you to say a few words in support of the webinar. Over to you, sir.
Thank you, Dr. Nair. Good morning to all Indians, and good evening and good afternoon to others. Respected Professor T.J. Rao, Professor Krishnamurthy, and other respected invited speakers for this conference webinar, and all other participants. First of all, I would like to greet to all a very happy National Statistic Day 2025. I congratulate Professor Satish Kumar, convener of this international webinar 2025, and his whole team for providing this online platform for many researchers from India and abroad. My best wishes for this webinar and for these presentations of all participants and invited speakers. Best thing of this webinar is that Professor Satish Kumar has started this long back, and it was continued in the Corona period also in online platform. And not only that, this webinar is available for all Indians and others free of cost. There is no registration fee. So lot many students, researchers, if they are not finding any financial support, they are joining this workshop and webinar. Very nicely they are presenting, and many abroad invited speakers they can see here and they can listen their talks also. On the behalf of Indian Society for Probability and Statistics, ISPS, I offer my best wishes for this webinar and hope that we will find a fruitful output of from the presentations of many researchers and invited speakers from this webinar. I would just like to add here, as many academicians are there, I would like to add that on-job training is the concept introduced under the new education policy. So under this, our university has got the first batch of completed MSc Statistics under NEP 2020. On-job training was the feature of this new education policy, and two research projects in the third semester 4 credit and last semester 6 credit. So this was the important activity under the MSc Statistics program. 14 credits on-job training. Many students have completed on-job training from industrial environment, even government organizations, planning departments, different organizations of government, and that was fruitful for understanding the system of statistical activities from the government sector and private sector. So I would like to add this for others also. All other universities of this country should accept this, and they can get benefited for the purpose of students enhancement. Finally, I am thankful for organizers for felicitating and inviting us in this inaugural function of this international webinar. I would like to thanks to everybody and my best wishes for this webinar throughout these 3 days. I am thankful.
Thank you, sir.
Thank
Thank
Thank you, dear Professor, for your words of encouragement. Now I request Professor Manoj, who is the head of the Department of Statistics, to Manoj sir, to please say a few words. I think Manoj sir hasn't joined yet. Shall we move on, Satish sir?
yeah, please.
Okay,
Time is
thank you.
precious.
Yeah. So now we are entering a very happy moment because we are going to declare the names of the winners of the Professor TSK Mothad Memorial National Level Online Quiz Competition 2025, which was conducted in conjunction with the National Statistical Day and was organized by the International Statistical Fraternity along with the Department of Statistics, School of Physical and Management Sciences. The quiz competition was conducted in three levels, for the higher secondary level, for the undergraduate level, as well as the postgraduate level. On screen, you can see the winners, and I'll be declaring their names. I request if any of you are present in the webinar, I request you to please open your camera so that all of us will be able to see you and congratulate you. So first, the winner, higher secondary level, is Mr. Srihari, Model BHSS, Kerala, India. Srihari, congratulations on your win. Coming to the undergraduate level, we have got five winners. Miss Srija Ubadhyay, St. Xavier's College, Kolkata. Mr. Christian Jade Gia, Butgas State University, the National Engineering University, Nasugbu. Mr. Akshanya, University of Lucknow. Miss Rekshata Irappa Shidibhavi, Shivaji University, Kolhapur, and Mr. Manpriyam, University of Lucknow. Congratulations, dear winners. If any one of you are present in the group, please on your camera. So congratulations one again. Coming to the postgraduate level, the competition was really tough, and we have got four winners. Miss Pushkar Bora, University of Agricultural Sciences, Bangalore. Mr. Abhishek CP, University College, Trivandrum, Kerala. Miss Sneha Rajiv, CUSAT, Cochin University of Science and Technology, Cochin, India, and Miss Nivedya Premanand, Kannur University, Kerala, India. So, congratulations to you two, dear winners. We are extremely proud to present you as our winners, and we hope that your journey in the search of statistical knowledge will propel you to higher levels of knowledge and wisdom. So, congratulations once again. Actually, our time is we are tied up for time, and I would directly like to go into the a few words of gratitude to all the dear professors, the dignitaries who have actually, it's not, your presence is not restricted to this single event. Actually, all of you had been with us all through this journey for the past many years, and your presence and your continuous support is the reason why we are able to conduct all these programs in such regular and successful manner. So, I would like to take a few minutes to say a few words of thanks. First, I would like to thank our dear chief guest of the day, Professor Rao, for your for sparing time to be with us and for your great words of wisdom. And thank you, sir, for inaugurating the session. Thanks is due to our dear Professor Kalyana Raman sir and Professor Shinde for felicitating our program and actually for being with us all through. In every step, you are all with us, and we expect your continuous support and presence in our search for academic brilliance. And we have got so many dignitaries among us, so many great professors from around the world, and so many participants. And I would like to take this opportunity to thank each and every one of you. The journey is just beginning. It's a 4-day journey, and I really hope that your presence will add value to these days and actually create a statistical communication. We will be able to interchange knowledge and have a great 4 days ahead of us. And I don't know, but just for formality, I would like to thank you, dear Professor Satish Kumar sir, for providing this opportunity to all of us here, to all the younger generation who wish to travel your path. Actually, your motivation and your energy is extremely it's a great motivation to all of us. So thank you all once again, and we hope you'll be having a great journey in the coming 4 days. So we can wind up the inaugural session with a national anthem. I request you all to please stand for the national anthem. Thank you. So we have reached the end of the inaugural session. Our sincere thanks to ISPS, to KSA, to the Department of Statistics once again, and we'll be entering the technical session soon. So Satish sir, over to you. So
Let's just move to the first technical session.
Statistics, currently based in Chennai. Over the course of his distinguished academic career, he has made enduring contributions to the fields of quantitative methods and research methodology. Even after retirement, he continues to engage actively with academia, particularly through his
എന്തെങ്കിലും ദോഷം ഇട്ടിട്ടുണ്ടോ? ഭംഗി വിളിയൊക്കെ
of International Statistics Institute, fellow of the National Academy of Sciences, India Fellow of ISPS, and Fellow of the American Statistical Association. Currently, the only working statistician in India with this recognition. So it's only very happy to read even the achievements. And actually, I'm very happy, very gifted to, to say this. So I take immense happiness in inviting Professor Rishan Gupta to come and I hand over the mic to Ashish Gupta and request him to present his presentation over the time allotted. Thank you, sir.
Can you hear me, sir?
No, presentation is not coming in.
Yeah, I can hear you.
You can hear me, right?
Yeah, can hear you.
Yes, Professor. Yes, Professor. Yeah, let me see if you can. Can you see the presentation now?
Now it is coming.
Good, good. It will come. Yeah. I just wanted to say hello and thank you. Now I'm going to make it full slide.
Yes, yes, okay.
It's okay. All right. Thank you very, very much, sir, for your nice and kind introduction. And again, as I said, it's a pleasure to have such a senior statistician like you to chair this session. It's a double pleasure because I'm going to have this talk in the name of Professor E.S. Nair, who is a very, very renowned statistician. And then again, today is the birthday of Professor P.C. Mahanovich. So it's a joint event. I am very, very pleased to have a talk in this particular opening ceremony. And my talk will be on the AI in modern statistical machine learning, reflections and visions of Professor P.C. Mahanovich. Though it's a U.S. Nair talk, Professor U.S. Nair had been instrumental in forming the Department of Statistics, and here it is, a very short bio of Professor Nair. So he is known as the father of statistics in Kerala for the younger generation, the people who are there, the students and the research scholars. And for those who are not knowing about Professor U.S. Nair, he is the father of statistics in Kerala and was a key figure in establishing the postgraduate department of statistics at the University of Tiruvannamalai, now University of Kerala, in 1945. I think it was the second university in India which started statistics. And also, uh, here's a more detailed one, pioneering statistics in Kerala. He has done immense work, phenomenal work to develop statistics in not only in Kerala but also in India. And also, he had been in the Kerala Statistics Day has been named in his honor. So, as you see, very illustrious, very influential, and above all, a person who has devoted a lot of his time and effort in developing statistics in India, not only in Kerala, but in India. So, with that, I move on to my talk. Uh, this is in statistics, obviously, and it is regarding the upcoming interest of AI in statistics. So that's what my talk is going to be briefly. So I will try to stick with some of the methodologies. Now, uh, I'm going to, for the sake of time, I'm going to cut short the data science aspect and statistical data science. The statistical machine learning is in the one that you are all familiar with, that deals with not only the machine learning aspect that I'm talking about in computer science, but the statistical machine learning. So, what is the difference between those two? I'm going to talk about it shortly, highlighting the difference between machine learning, as we know in computer science, and statistical machine learning. Okay, so we will be using the statistical unsupervised machine learning (SUML), and these are in statistics we know as this as cluster analysis. Like many other terms, computer science has made their own terms from our statistics, which were known long time back. And this is one such one, what you call a machine learning, supervised machine learning, unsupervised machine learning, which is cluster analysis, and then you come at model selection. They will have over here deep learning in that aspect. Similarly, regression, the feature selections, we talk about determining the variables. So these are synonymous, but computer science people have taken those terms and given some new names. Now, the SVML, the invariants are probability distributions, the dimension reduction. So I'm talking about distributions and the dimension reduction in some manifold, which is not our usual Euclidean manifold. I will come to later on. And then the construction clusters, and determination of the optimal number of clusters, identification of group membership, performance evaluation, and the deep learning part. So I'll run you through some of the advancements, but before that, we need to talk about the manifold. So what is this hyperbolic spaces that we're talking about? Moving away from Professor T.C. Mahalanobis's work, the seminal work which made him so famous, Mahalanobis's D square, which was on the Euclidean manifold, which is actually the linear space. We will be talking about something that is more general, which are applicable to the emerging cases and facets of modern research. And so the indispensability of statistical approach, where does it come from? And this is because you will note that the methods used in computer science are basically distance based. So the use of, I'm talking now about ACML, and basically those are based on distances, so distance measured, some similarity measured. This could be on the usually the ones that have been adopted so far. These distances measured are usually on the Euclidean manifold or R square, but they have been generalized to the case of spheres by using the spherical distances or geodesic distances. But the problem is our events that we look at are stochastic events, and these are not dynamic. So the methods in the computer science have to be augmented. There are some nice papers in the computer science journals which do point out for the requirement of this statistical part, the probabilistic and the stochastic parts that should be coming in. And that's where we need to bring in our statistical model. And that's where the methods used in computer science do utterly fail, and if I may say so, because they have not been utilized or may have been able to develop such methods in the case of stochastic events. For example, earthquake, we do not know where actually the earthquake is going to take place or what is going to be its epicenter, what is going to be its magnitude, or the space debris. There's so much talk about our now the missiles, I mean the mission going into space that we're looking at currently in the last few days. So there's another question of the space debris comes in. I'm going to talk about it a little bit later on. Okay, so to show how the statistical innovations can enrich data and the nonlinear data, it can be used in the circadian, genomic, etc. And in general on non-Euclidean or non-linear manifold. And there are real-life applications unique to such data. So Mahalanobis came up with his D square, and this D square was basically the real new innovation. Why? Because the distance between two points on the straight line or on a plane is very well known, and so is the distance between 2 points on RP. Okay? If you take the Euclidean distance, the problem was how do you measure a distance of a point from a group of points? Okay, so in order to do that, measure the distance of a single point from a group of points, you cannot simply take the distances of each individual points and add them up. Okay, because you realize soon that these points over here that you're looking at, there could be multidimensional, there can be correlation between these points, there can be dependence between points. Not only that, there's a scale factor that comes in. So how do you get rid of this and bring in the invariance? That led him to the development of the statistics, which is Mahalanobis D square. Okay. So in the case of the multidimensional case, for example, where we are looking at data not on the RP, on the, let's say, on the Euclidean manifold, but rather on, let's say, on the circle, which is S1, which is the embedding of R2, or you can think of a sphere, which is an embedding of R3. These are nonlinear manifolds, and hence the distances here don't, regular Euclidean distances don't make sense, and thus the usual techniques will not make sense. Okay, so this is one I talk I gave about the AI. I'm now going to move into AI. And those of you are interested can look this up. It should be in the tube. This was a discussion and a fire-based talk that was given in the Yale University in the World Salon, New York. And some of you, if you're interested, you can see this in the tube. They are going to put it up and possibly commercialize this soon. But you can look at it who are very interested in further discussion. So the AI for understanding SML, this, as I said, the context of mining, deep learning from the stochastic models, and then we need to develop probability models. So here comes the difficulty, which we do not get to see being addressed by in the computer science jargons. So how to develop probability models? Because that's what we need in the stochastic approach cases. And finally, the developing algos. Definitely, we need the computer people because we need to develop algos and then the visualization for the interpretations and accuracy. So now let us look at, I tried to first look at the AI because that is the emerging area. And I tried to look at, okay, let's see what AI can help me with. So I tried to look at these models. Many of you realize this. This is nothing but exponential distribution, but it is reflected. So it is a generalization of, you can say, of a double exponential distribution. So I asked AI to give me a graph of this, and then I went into the manifold. So if you see the problem two, that is the same, just same, looks like the same distribution, but the distribution now is defined on a circle. All I did was to properly normalize it and make the support on 0 to 2 pi, and this is going to be periodic. That is the restriction I want to keep. And I asked, okay, let us give this try. What can AI tell me for the young scientists, our new researchers? So let me give the graph. So I asked this, and okay. So the AI gives me this graph. All right. So you see these graphs that they're presenting to me. So I was a little bit astonished. And what is that they're giving me? And they say they're giving me a mixture of two Poisson distributions. Okay, as you can see, the previous one that I gave the example of, it was two exponential distributions. Okay, here it is. But now AI is giving me two Poisson distributions because they have not possibly seen this kind of distribution before. And it's a wrong answer. And I saw, okay, let me try to guide them. I told them that, see, you cannot do this. It's a wrong answer. This is a continuous distribution and you have to change it. So I told them that this displays a mixture. I said, please note, you can see at the bottom that the problem was not for Poisson mixture. It is for piecewise functions with weighted exponential distribution on the positive. And similarly for the second one. So now they correct the graph and they are able to give me. So with the prompting of that, they are able to give me the piecewise weighted exponential distribution. So this is the next step to look afterwards. So AI has been successful to lead the way for the in the Euclidean space. Now what happens to the space when I talk about the circle? For this problem two, the graphs are still wrong because AI is not familiar with the statistical development, it is giving me a wrong answer. So I tell them this is wrong. You cannot have a discrete distribution like this. It's a distribution defined only on 0 to 2 pi, and you have to correct it. And they give up. They say this is advanced analytics and it not within our scope. So the moral of the story is while AI can be quite helpful in certain areas which are already known or a historic, let's say you want to find out the details, the historic details, but it can not only miserably fail, but in its attempt to be a know-all, quote unquote, it gives us misleading solutions which can be drastic and devastating. So one has to be very, very careful when we look at the developments of AI. So now AI, I think, is not for statistics ready yet. Rather, statistics should be there for AI. Okay. So now I go into the manifolds. So the introduction is the circular data that we look at, and I'll show you how we relate to these. So these are the data on the angles and directions. And if you look at the zero that is fixed, its circular observation can be uniquely represented with reference to this direction. Because north, for example, is the zero direction for people in uh, physics. South is the zero direction for people in geology. East is the zero direction for people in mathematics and statistics. So any inference we do should be invariant with respect to the choice of this direction. So now let me move on. So directional data in general then consists of multivariate observations with the components in linear, circular, axial, or combination of those. This leads us to distribution in the hypertorus, hypercylinder, hypersphere, hyperdisk, which are basically distributions in the more general hyperbolic spaces. It's a very nice geometry that you need to look at, and in this topological space, the derivation of the distribution becomes even more and more interesting. Kerala is famous for mathematical statistics. A lot of people have contributed to this area in the mathematical statistics, and I think it's a suitable arena here to present this talk so that the young generation or even the young professors and our researchers there can be motivated in taking up these challenges in mathematical statistics, which are unfortunately and sadly trying to, I say, diminish given the quick solutions, black box solutions, which are coming from the arena of computer science. Again, I say computer science does not deal with this, which is necessary for our stochastic event, and we are not dealing with dynamic events. So now let me go on. This is the example on the area of the genes who are interested in bioinformatics. Another example, phase in heart and phase in liver. It's a microarray experiment, and with this microarray experiment, you can see the phase in the heart. That is the peak time, which at which the liver, the particular gene, has its expression level. So the peak time means the time at which the peak level does occur. Okay, so this particular gene 98079 underscore S, the carbonic anhydrase 14, has a peak time, that is the value that at which it had the maximum value was 0.12 in radian. So you can convert 360 degrees into the 24 hours. So each hour corresponds to 15 degrees, and similarly you can convert the 6.28 radians into the area of 24 hours, and you can get this from minus the 3.14 plus 3.1. That is the support in particular circular case. That's why you see the values like minus 2.56, minus 2.04, and at the same time plus 2.35 and 1.20 degree. So these are all expressed in radians. So writing programs in C will need the particular values to be fed in terms of radians. So, so this is the background. This was the question of how to convert. We try to segregate these genes. Rather, I would say cluster the genes into groups so that I see whether the delay is by 4 to 8 hours, because I don't want to give a medicine which is for heart that can affect your liver. You know that can be very detrimental, and it can be a serious issue, because if the medicine that the person is going to take, maybe not only month after month but year after year, for the heart, if that affects your liver, can totally damage your liver. So you don't want to do that. So that is why I want to see that these two groups are different, how different they are, what are the genes that are differently expressed, which are in different groups, and you need to cluster them. Okay, but again, these cannot be clustered in the way that we know using the Mahalanobis d square for the r square. We need some generalizations of that. We need to go into the mathematical probability distribution. The beautiful part with the Mahalanobis d square is that it is not only a measure which comes up as an intuitive distance measure, which was gladly and very enthusiastically accepted by the computer science community, but it also does come up as particular statistics when dealing with probability distributions like the multivariate normal distribution. If you look at the multivariate normal distribution, you will see the exponent that we look at. It corresponds to this minus d squared with a single point x. Okay? So that will be the starting point. And here is the space junk I was talking about. We would like to clear up this space junk. We are sending missiles, but that is creating a big problem because this space junk that is no longer useful for us. What is the space junk? The space junk is a agglomeration of hundreds and thousands of missiles, satellites, which are no longer active, but they are probably fragmented, broken up, and even if they are in whole, they are no longer active. But they are orbiting our celestial hemisphere. And what does that mean? That impedes on, that deflects, and that creates the difficulty of the particular active satellites which are sending the useful signals to the Earth. Okay? Because these particular debris will reflect those, and those signals will not be reaching our satellite stations down here in the Earth. So that's a big problem. And NASA had now created and launched a program for clearing up this junk. India is one of the major contributors of that because remember, India was the first nation in the world which did launch 100 missiles at one go a few years back. Okay? Now, the question after that from the European and the American government is what is going to happen? Who is going to clear up that junk? So we need to find out where the junks are located, what's the volume, how big are they. Okay? So that becomes, again, because the location there is in terms of longitude, and the value of the junk may be in terms of volume, because we cannot weight that right now. Okay? So maybe from the imagery, we will be able to use that. As such, you do not know what the value of that is. I mean, what the weight is going to be. So this will be data on the theoretical scale as well as on the linear one. We have to combine these and find the joint distribution. Here, we do not find the advancement of the computer science methodologies in terms of distribution, because that's where the probability distribution are needed to be derived. I'll come to that pretty soon. So this is the torus surface and the cylindrical surface we're looking at, and then this is the sphere that on the top, you see the points on the surface of the sphere. The last one is the point inside the sphere. That is what we call a high disk. Okay? So some statistics, very simple one. The first example of the hyperbola space is the circle as a special case S1. As you see the two observations 20 degrees and 40 degrees. If you take a usual angle mean, it will be 180 degrees. As you see, it is nonsensical, and you need to do rather a circular approach, which is zero. And zero is nothing but this is a mean, but it's a trigonometric mean that you all learn in your high school. Okay? So this is different from the usual arithmetic mean. The average, usual average doesn't make sense, but the trigonometric mean does. So this is the point of deviation. Similarly, the standard deviation is measured by the inverse of the concentration. That is not obviously the usual concentration that you take in terms of variance, but it is based on the resultant or average resultant R bar. The measures of the mean is the theta bar, which is the for the specific arc or the coordinate specific mean angle or mean direction defined over here. Okay. So the probability distributions are given by these three conditions. The first two are familiar with all people in statistics. The third one is the one that brings in the condition of periodicity. Because the angle of 370 degrees is the same as the angle of 10 degrees. Hence, any function that you define should be also periodic. And that is what Phi is saying, that if you have f of 370 degrees, it better be the same as f of 10 degrees. Okay? So this is the first one is the circular normal distribution. You are looking at, it resembles the normal distribution for kappa large, cosine is usually small. So that one will give you a normal distribution, but the support is 0 to 2 pi, and hence it's a periodic function. This is given a circular normal distribution, and it was developed by von Mises. Okay, and the generalization is by von Mises Fischer. So these are some initiating references. You can look up these books. This is coming up in 2025. Another one, this beautiful volume with lots of applications, and you can see this in coming up with a lot of mathematical contributions. Also, it is already published. The second one, the third one is about to come up hopefully soon. The fourth one is already there in Foreign Nightingale, and the fifth one is our initial book in topics in circular statistics, which will give you a good introduction to the area. So I asked ChatGPT, okay, let us look at how ChatGPT does. I wanted to get an estimate of the mean direction and also the kappa. So, and here's what ChatGPT gives us from the AI. The mean direction is okay. I said, all right, I can accept that as dark and truth. This is quite specific. But you look at the estimate they gave for kappa hat, you can see from the previous slide, as I mentioned, circular normal distribution, kappa hat has to be strictly greater than zero or equal to zero in very special case of informal. But this estimate they're giving him, in the case if the cosine lies between -1 and +1, and if you take it as a more normalized, the mu hat is the theta bar, then this will lie between 0 and 1. So kappa hat will inevitably lie between 0 and infinity. So it is not even in the support of the parameter kappa. So this is not even an admissible estimator. Okay, as nonsensical estimator, and Chat GPT and AI is giving us a totally misleading and wrong answer. So again, you have to be very, very careful of dealing with this kind of situation. So the toroidal model I'm going to talk about now, I'm going into the model. This is a model on the probability distribution, and we'll be developing models for clustering using the method of models of probability distribution. In contrast to the method using the distance measure, which are dynamic, these toroidal clustering models I'm going to present are going to be, these are all stochastic models. Okay. You can see that the first model, this is really like a bivariate normal distribution. If you take the Taylor series approximation of the cosine, you have the theta minus mu square over 2. Then sine is the x, so that will be theta minus mu. And for then, with a small theta being close to mu, if you can assume that, then with the Taylor series approximation being valid, and that is approximation, this basically approximates a bivariate normal distribution. But it has the rigor of being a distribution defined on the toroidal space. It is a doubly periodic function, and it is amenable to our statistical inference, being a member of the multivariate exponential family. Okay. So we choose the initial values. I'm not going to the details of these. I'm sure most of you are familiar with the clustering algorithms and using the k-means algorithm. But it is a similar approach in the k-means, but not the way that we are looking at the probability distribution. The k-means, the natural question would be, how does the k-means come in? And rather over here, the k-means is not at all applicable because the distance, linear distance, Euclidean distance on the torans is nonsensical. So I need a different measure of the distance on the torus. And that could be a measure on the Clifford distance on the topology of the torus. So I'll come to that briefly. Similarly on the sphere, you cannot have the Euclidean measure, different measure, geodesic distance. But what are the distances that bring us? That brings us to the visions of Professor Mahanavi working on the various different arenas and applications. He was a visionary, he wanted to apply statistics in different areas, not only to mathematical statistics, but for the benefit of the human, our mankind, in various arenas and applications that can benefit our mankind. So keeping that in mind, you see that if you look at the different applications and emerging areas of modern research, with the modern science rather, that is say, this kind of particular torus, sphere, hypersphere, hyperdisc comes in, and the distance measure becomes a question query. How can we measure a distance? Not easy to get a distance measure on a torus. Okay, and you can get it on the sphere, but not on the torus or easily. And how do you make a distance on the hyperdisk? How do you get a distance in topology of particular the hyperbolic spaces? Okay. So moving into our distributions, we can use the convergence of the EM algorithm. So I look at the cluster equation. Here is the EM algorithm The components of the EML contain the distribution density and nothing but the toroidal distribution that I showed you earlier. The choice of the number of clusters is going to be objective. You can base it on BIC or AIC. So what is the method of the ideology over here? You want to form the clusters so that the elements inside a cluster are going to be as homogeneous as possible. I mean, the elements which are different in different clusters, they should be as heterogeneous as possible. The within cluster variance, as I should quote unquote, or the similarity within cluster similarity should be very high, between cluster similarity should be very low. That is our aim. How do we achieve that analytically? Okay. So as I mentioned here again, the variance will not make sense. So I'll come into the distance measure and finally the BIC and AIC. So now we can see AIC again is a similar measure with the penalty, and similarly the BIC with the penalty indicator model 1, model 2. And what is model 2? The model 2 is the one that I showed you over here previously, and that can be a conditional model. In order to decide on the number of clusters, we choose the value of P for which the AIC or BIC is minimal. So here comes the distance. So now, if you want to look at it instead on the probabilistic manner, suppose in the computer science people will say, okay, so how do you know what the distance is? So this is difficult to have a concrete definition of the distance on the torus, the formula that can be implemented. Okay, it involves the integrals, and if you try to look it up, it is not at all a simple task. On the other hand, there is a measure which sort of mimics the Euclidean distance, but now in this manifold of torus, that is the, we call it a Clifford distance on the torus, and that is what is exactly given by dT. So we can measure the Clifford distances and see how homogeneous the particular clusters are. And this is the example that I'm giving you, the circadian rhythm with the genome data. You can see the BIC and AIC given values. So the one with the value, the least one is the 195. In both cases, you see 190 in the AIC gives you 154 with the 6 cluster, and here you have number 6 is also the number of clusters. So we can set the number of clusters to a higher value, but here you can see the at most 6 we have restricted the number of clusters. We show that 6 is the number of clusters that is giving us the maximum uh, preference for the choice of the number of clusters. Okay. Now, how do you do the cluster allocation? The cluster allocation is done by the likelihood now. This is probabilistic. We find the particular observation and allocate that observation to that particular cluster for which the likelihood is the maximum. In this way, I have 38 observations. As you can see, we are taking 4 clusters now, trying as an optimal number of clusters. The minimum has been obtained for 4 in the other situation. And then with the optimum clusters at 4, we find out the observations given as 14, 14, 3, and 7. This allocation is not done arbitrarily. This is not done on based on an arbitrary measure. It is done through probabilistic, rigorous, and over here the method that is an objective method. Okay. Now the optimum cluster module 1 and 2 is yeah. So you get over here the average toroidal distance we are getting over here. The 4 clusters, you see the distance within each cluster is given as 1.63, 6168, 1.89, and similarly the second one with the average toroidal distance is 1.5468, 1.94, 1.84. Okay, these are the within clusters, the toroidal distance that is obtained, the average one for the members within the cluster. The interpretation utility of the cluster. So after you obtain this cluster, so you one would say, so what was wrong if I dealt with the usual Euclidean cluster and you have k-means, let's say, obviously the whole thing would have been an utter disaster because the particular distance doesn't make sense, the normal distribution doesn't make sense. Okay, so so if you look at the choice of clusters, let's say the convergence is a question, and fortunately, because we are in the exponential family, the convergence is guaranteed by the theorem of Gapoor. Okay. All right, let's see. Now, let us have a visual presentation. So you see, if the number of clusters we have given their elbow plot, the right one, that gives you the BIC, and you see the BIC with the elbow plot that we're looking at. Of course, the six is the lowest one, but if you don't want that many clusters, there is a break. The elbow is at 4. So I can take the elbow, which give me select the number 4 as the number of clusters in total. That is why I was showing you those particular tables using 4 as the number of clusters based on the elbow plot that we're seeing over here. On the left hand side is the part of the data. So there are 4 clusters. You can see there are 4 colors over here: red, blue, green, and black. Okay. So,
So, Gupta, 5 minutes more.
yeah, I'm done. Right?
You have
Hello?
5 minutes more.
Right. Right. Okay. Thank you. So I'll continue a little bit then. Uh, so if you look at this cluster over here, you see the difference. If you do a linear clustering, no one in statistics will accept the fact that the points which are values close to -3 will be clustered in the same cluster as the points which are in the value of having in the region of +3. These are quite different. One in the negative region, -3, and -2. The other one is +3. So how come these are clusters? Okay. So that is the beauty of the clustering technique that we're using, and that is what actually it should be. Because when you look at the angles -3.28 and +3.28, these are nothing but 360 degrees and 0 degrees, which are identical. So naturally, the 2 points on the circle, the 0 and 360 degrees, are coincident, and hence the values close to, in terms of the radians, -3.14 and +3.14, they should come close to each other. And this is exactly what we are seeing in this figure too. This is an illuminating figure because it tells you that had we taken the usual k-means clustering, this would not have shown up and would have been getting some devastating results, which could be really very harmful for application, especially in the development of drugs and finally applying them in the human body. Now, in the last 3 4 minutes, I go into the astrophysics and the clearing of the space junk. And this is where the hyperbolic spaces come in. And in this case, the distance measure that you have to look at will be obtained from the tangent spaces. I'm not going into the details of the mathematics. It's a little bit, I'll say, non-trivial. And if you look into the developments of the basic probability distribution theory, the Russian mathematicians have been trying to develop the probability distributions in this arena, but not the way that you are looking at, for example, in the case of clustering. But we need to develop our own probability distribution because we have to bring in the concept of dependency. Are the heavier weights located in the similar regions? So is there the dependency between the region, which is a theoretical variable, and a linear variable? How do you measure the, let's say, quote unquote, correlation or association between a theoretical variable and a linear variable? These are very interesting questions. How to measure that? So one can do that. I'll give you just a hint. One can do that through the canonical correlation. As you recall, canonical correlation gives you association, a correlation measure between a vector and another vector, and a special case vector and a scalar. In this case, it is a vector in the sphere. It can be a three-dimensional vector using your polar transformation, and the scalar is a one-dimensional one. And then you can take this particular measure, which is a canonical correlation between a three-dimensional vector and a one-dimensional scalar. And this canonical correlation will give you one measure of dependency between these two quantities. So these are the upcoming ones that in the footsteps of Professor on the beach will try to develop these particular generalizations of monolith D square in the hyperbolic spaces. Okay. Now the objective is to cluster here again, and if you want to cluster this, so now let us see what kind of data we have. These are latitude, longitude. I'm just talking about the sphere. Forget about volume now. Here I want to put that. Here are the data points that you can see in the red. They're all Indian, connected from the Indian archive. So our satellites are there. And here you can see, of course, Earth is rotating. We are taking this as geostatic, so that if the problem is that they are far enough, so that the angular differences will be negligible, and hence if both the debris and the earth are moving, we assume they're moving at the same speed. Otherwise, if they're not geostatic, and out of this assumption, it will be very, very difficult to even approach it from a temporal spatial clustering approach. Okay. So now, so this is again, I asked AI, give me what you can do with this clustering for the hyperdisk. So the AI, as usual, is all no. So they give me this particular one. And what are they giving me? So they give me a mixture of Gaussian model. And obviously, this is wrong. The Gaussian distribution is not going to be a distribution which is on the sphere. Okay, so the Gaussian mixture model is used obviously on the RP, and there you go. The AI cannot be used. It's again giving us a very very misleading answer. Okay, so here they are giving all these NumPy, Matplotlib, scikit-learn, all these are giving us their references. But look at what bullet number 2, apply the Gaussian mixture model. Okay? And this is a totally wrong. And here they give me a nice plot, but again it's a Gaussian mixture model. So if you want to present this in a conference, they may not know. The computer science people, okay, here is the cluster, there you go. But this is a totally nonsensical result coming from the chat GPT. And I'm sure this will be the deep fake learning also, the deep seek learning will also give a similar type of thing. Okay. So to identify this number of clusters and to normalize this, we do that by using our theoretical k-mean algorithm, and then we move on to the, here are the three ones, not the Euclidean space, but the spherical k-mean. Okay, so we are just a snapshot of what the latitude and longitude are. We got the classes over here, but then going into the probabilistic, this is the distribution that we're looking at, which is the generalization of the von Mises distribution. It's called the von Mises-Fisher distribution. We hold that no association between the components of X are given here. So since it is not there, it will fail to model the dependency between the components of X, except that they have to lie on a hypersphere. So with this is the first approximation. And with that, we use our, again, it is in the exponential family. We can use the mixture algorithm, the EM approach, and then we can do the hierarchical clustering. Similar approach is that. To move on into the hyperdisk and the hypersphere, and in specifically the hyperbolic spaces, here is the distribution. The distribution is obtained by the Mobius transformation, conformal mapping, three conformal mapping simultaneous to one after another. It is in the arena of Lie group and Lie algebra. Finally, I am not going to bore you with the details of that. You can see it in my paper in the JMA. And here it is, snap of how it will go around with using the Lie group and Lie algebra. And the group is the GLP plus 1. Okay, and the distribution is a generalization of the Kumar-Samy distribution in the hyper disk situation. One can try to use that, and this will be our next attempt. The future scope is how do we deal this on the, as I said, the altitude of the space debris, predict the chances of particular debris entering and moving the Earth's atmosphere. So this can be very useful with our space mission, which is a big thing nowadays. The data I had given to, I asked my some of the students, I had given a lecture and asked some of my students there who were attending. This is in NIMS to work out, and here the team of these students worked out this particular. This was known the data they have used for the using the k-means or k-spherical mean, the distance measure. Okay, not the ones that I'm showing you like later on with that. Probably they are not, of course, within their scope. Okay, they are way far away before they can at least get into this arena because they have been mostly dealing with the computer science and programming aspect. But they did a good job, as I showed you. So the formula and course must be checked for the proper usage and accuracy. Don't jump into AI. Critical and deep insight will be needed. Don't worry. We are not, the traditional statistics have been fast evolving. So an introduction to AI, even at the undergrad level, should be included in the curriculum because obviously it can save you a lot of time for gaining insights from historical data. But when you come to the development of new methodologies, where traditional statistics is being fast evolving, rigor is to be acquired and proper implementation of AI is needed, which they are lacking. So the thing is, statisticians will and have become indispensable to play this guiding role, to bring in the rigor, bring the correctness in the AI. Do not jump into AI. And it is now the time that we have statistics for AI. Okay, before we can usually use statistics in AI. So rather, the AI people should come and use our statistician, the knowledge from statistics, to develop rigorous and correct methods, and not to mislead the academic and the other scientific communities. The essence of AI, as is statistics, is to make sense out of data, and this can be achieved only when we implement it sensibly. So, there are, as I said, the future scope, lots and lots of scope here. And thank you very, very much for the patient hearing. Thank you very much, sir. Over to you.
Assis, Assis Professor, have a
Yes,
very
yes.
wonderful talk. Good morning, good morning.
Thank you very much.
Thank you
Thank
very
you
much,
very much.
Assis.
Thank you. Thank
The
you.
field is open to the audience. Maybe
Okay,
Gupta may take one or two questions.
okay. Assis, I have one small question.
Sure, sure.
Yeah, I am Professor Irandan already, you may know.
Yeah,
I
yeah,
am
yeah, I
working
know.
in I am working in Sastra as a full-time professor faculty here. We are handling machine learning and deep learning. Any other one textbook for the student for taking class for BTech and MTech students? Machine learning. Any one textbook which is
Uh,
so related to BTech and MTech students for
I
the
would
allied
say there is
courses.
a beautiful book. I will, Professor Hagani, I am going to say that I would rather uh,
Ah,
not impose on you, but request you to look into the arena of statistics. Look into
arena
the
of statistics.
the
Okay,
statistical machine learning. So
okay,
this is a book by Steve Shirani
okay, okay.
and others. It's a
Oh,
very well written book,
ah,
accessible to your students, and
ah,
certainly the
okay,
what I'm talking about today,
ah, okay,
the basic thing that emanates from this beautiful book of Steve Shirani on
okay.
statistical machine learning. In your course, if you can give at least a few lectures on statistical
Okay,
machine learning, they can
okay.
appreciate the beauty of statistics and above all the rigor and the need of statistics rather
What is
than
it?
rely and wrong path.
Name of the author, let me know. Once again, assist. Name of the author.
Statistics, Tip Shirani, Tibshirani, Tip Shirani,
B-I-B,
Tib,
P-I-B, B-I-B,
SHI,
S-H-I,
S
uh,
RAN, RAN.
S-H-R-A-N. Shiran. Okay,
Please
it
send
is
me an
sure.
email.
Okay,
Please
fine.
send me an email.
Uh,
Send me an email. I'll give you the details of the book with a snapshot, so that you can
okay,
look into it.
fine.
Okay.
Okay,
Maybe
thank
it
you
will be
very much for
available on
your.
the web also. You may be able to download a free copy.
Okay, okay.
Okay. Let me know.
Okay.
I'll
Thank
be
you very much,
very,
Ashish. Very
very
wonderful talk.
thankful. Thank you so much.
Thank you very much. Thank you very much.
Thank you.
Okay, fine. I think we are almost over our time. So if there is anyone who is ready to answer, ask a question, possibly he will be able to take.
Professor Kalyanaraman, they can contact me through email also later on. They can
Pardon?
contact me through email also.
Yes.
Okay. Yeah.
And you can comment. You will audience are requested to contact him over email so that
It's
any
a
question
request.
can be solved. Sir, I just want to ask one question, simple question. So
Sure.
you have said much about data, and now they are talking about quantum computing. What will
Ah.
be the kind of data that you will come across?
Ah. See, when you talk about this big data doesn't only mean quantum computing comes in the arena of quote unquote big data. But big data is not naturally the volume only. The big one is the variety. In the four
Yes.
V's in big data is variety, the velocity, also you have the volume is there and the velocity. Okay, so here the variety is the part. The quantum continuum will be very much essential when you look at the dimension in the hyper disk or in the hypersphere, which will be in a higher dimension. For example, this hypersphere I gave you can be, I have some examples where the dimensions can be more than 200 or 300 in the hypersphere. And then if you go to hyperbolic spaces, that's a different type of computing. These are integrals in different higher dimensions and multiple integrals. So this cannot be done with regular computer, quantum computing with the call of the day. So we have to join hands with the computer science people. We have to be friends together, not foes. for the benefit of the humanity. We need to join hands with the AI and computer science, but keep our head high. So we should be the leaders. We should be the leaders from statistics. Okay, that is the hope today.
Thank you. And on behalf of the organizers, I thank you very much for providing wonderful insight into data. And after 23 years, I'm doing it for the first some time. And you have drawn us to different directions. So naturally, it's going to be one of the interesting aspects. Those who would like to work may work much on this with further types of computing coming in. So I once again thank you from the part of the organizers and the audience, and thank you very much, sir, for coming here. And please try to come always. That is something I like
Yeah,
to
we'll see
publicly
about it. Satish is very close to me, dear and near to me. And thanks very much to Satish and his team for inviting me and giving me an opportunity to present this first talk today. And definitely, thank you again, sir, for your kind remarks. It was a pleasure to see you, at least virtually. Thank you again. Thank you. Bye, everybody. Thanks for your patience. Thank you. Bye bye.
over to the organizers. Yes.
Thanks to the organizers, definitely. Bye now. I'm signing off. Okay? You
Okay,
can.
thank you, Professor Ashish, for your wonderful talk. And TJ Rao to speak. Yeah, please.
Good morning to all. It gives me immense pleasure to welcome you all to the 10th International Webinar on Recent Trends in Statistical Theory and Applications. On behalf of the organizing committee, I extend a warm and heartfelt welcome to each one of you joining us from across the globe. This session is being held in honor of Professor P.C. Mahalanobis, the pioneering statistician whose legacy laid the foundation for the Indian statistical system and continues to inspire statisticians worldwide. It's my privilege to introduce the chair of this session, Professor A. Loknathan from the Central University of Tamil Nadu. Professor Loknathan is known for his expertise in reliability theory, Bayesian estimation, acceptance sampling, and cluster analysis. He has contributed significantly to statistical education and research and is highly regarded for his academic leadership and mentorship. I'm equally honored to introduce our keynote speaker, Professor T.J. Rao, affiliated with the Indian Statistical Institute and the C.R. Rao Institute for Mathematics, Statistics and Computer Science. He has published extensively in leading statistical journals and has been involved in various editorial roles for journals like Sankhya and Survey Methodology. His work has had a profound impact on the theoretical foundations of statistics, earning him national and international recognition. He will be delivering the keynote address titled National Statistics Day 2025. We are privileged to have both of them with us today. With that, I now invite Professor Loknathan to take the session forward. Over to you, sir.
Thank you, Dr. Satish Kumar. Thank you, Dr. Gauri. Good morning to all of you. Happy National Statistics Day. Greetings to you all. And it is pleasure and I feel it is a pride to chair this session. The speaker of this session is Professor T.J. Rao. I have been a student of his sessions at ISI during refresher courses, and he taught us usually that unified approach to sample surveys. Still, I remember. And later on, while preparing a chapter on official statistics for a textbook of Tamil Nadu Statistics, Tamil Nadu Textbook Society. There I found his writings on official statistics of Indian official statistics, and you admired very much, sir. And it is, of course, I feel it as a happy to chair this session, and I request you to deliver your
keynote address on the day of this celebration, National Statistics Day 2025. Sir,
Thank you.
the schedule
Thank you.
from 35 to 10, 11, 20, and I leave it to you to manage the time, sir. Uh,
Thank you.
Now, I welcome you to make your presentation, sir.
Yes. Thank you very much. My talk today, as you have seen, is titled as National Statistics Day, as well as the 132nd birth anniversary of Professor P.C. Mahalanobis. Next. Actually, as you know, the main purpose of Statistics Day is to create awareness in the public about the role of statistics towards human welfare. Today is the 19th Statistics Day and also the 132nd birth anniversary of Professor P.C. Mahalanobis. Next one. As you know, as I have already mentioned, he was the chief architect of post-independent statistical system in India, pioneering statistician, founder of the ISI, Sankhya, a well-known famous statistical journal, well-known for his concept of Mahalanobis distance, large-scale sample surveys, etc., etc., etc. Next one. Statistics Day in some other countries has already started long ago. For example, Africa, all the countries, they started on the 18th of November since 1990, whereas Japan started on the 18th of October since 1973, Turkey 9th May, etc., etc., etc. 102 countries are celebrating Statistics Day week or month to raise the profile of official statistics around 2020. So looking at all these things, World Statistics Day was first announced for the nice date 2010, and this United Nations Statistical Division mentioned that every 5 years we can celebrate worldwide this kind of Statistics Day. So what about India? So India happens to be a little lagging behind in spite of their superiority in statistics since Mahalanobis started working on statistics since 1937. Next one. There have been some representations from the ISI Council to the Government of India, and it is in 2006 during the Platinum Jubilee celebrations that former Prime Minister Manmohan Singh pronounced Maulanabi's birthday, namely today, 29 June, as to be celebrated as Statistics Day at a national level. So from then on, every year we have been celebrating and we are having conferences like this webinar now. Next one. This year, World Statistics Day is being celebrated on 2010, 2025. So ours is kind of a curtain riser for this World Statistics Day. It's also the 18th anniversary of United Nations. The theme is that driving change with quality statistics and data for everyone. Next one. In a world driven by information, World Statistics Day is a celebration of the data that helps us to understand the past, navigate the present, and prepare for the future. This is something which you have to look forward. Next one. Until recently, about 193 countries are participating in the global statistical system for United Nations Statistical Commission, along with India. Next. This year, 2025, is also the 75th anniversary of National Sample Survey, NSS, which was initiated by Mahalanobis in 1950. Furthermore, the International Statutory Education Center, ISAC, at ISI is also 75 years old. The next one. Now I shall go back a little bit and then talk about the post-independent statistical system. Let us see also about the history and origins of National Sample Survey, because that seems to be the theme for the central government today also. The Ministry of Statistics is celebrating Statistics Day with this theme, that NSS at 75. As soon as we had an independence, we were still having lots of gaps in the data. There was the Standing Committee of Departmental Statisticians in 1948, as well as National Income Committee, which National Income Committee consisted of PCM as the chairman, D.R. Godgill from Gokhale Institute as a member, and V.K.R.V. Rao, the famous economist, who is also a champion in national income, as one of the members. So these three people sat together and tried to devise a scheme to collect national income. Next one. On the 18th of December 1949, then Prime Minister Nehru decided that a sample survey should be covered the whole country, which should be organized at a large scale. He thought that it could be possible because he knew already Professor Mahalanobis, who was in charge of the statistics division of government of India. Next one. So look at the date. Within 1 week, on 25th December, Maulana Besh, with his experience in large-scale sample surveys at ISI since 37, he quickly prepared an abstract scheme for organizing a national sample survey. Next. There was an approval immediately by the government in 1950, and on the 10th March 1950, the National Committee recommended, you remember this NIC is those three members which I just mentioned, the use of sampling techniques to fill the gaps in information. Next. Around the same time, ISI in Calcutta and Gokhale Institute of Politics and Economics in Pune were conducting socio-economic surveys under the direction of PCM at ISI and Godgill at Gokhale Institute. And these two happens to be the members of the National Income Committee. Next one. So it's natural that both Calcutta Institute and Pune Institute should go ahead with the celebration, and they should collect interested with the collection of the data and start something like collection of the data for the whole country. So the data collection for the first round of national sample survey does start in October 1950, only for rural India to start with. Next one. Now the first round was completed in 51 December, and unfortunately after the first round of analysis was completed, the Pune report also was ready later. And when the report was there, the differences of opinion between Godgill and Mahalanobis were shown. Godgill thought whether it should be possible at all to collect information really obtained by basis of a sample. Next one. And Mahalanobis' answer for that a large-scale survey, like all large-scale productions, requires a period of breaking it. The first round can never be looked upon as a definitive inquiry by itself, and there is a series of dialogue between Professor Godgill and Professor Mahalanobis, and finally it was Mahalanobis who set his foot down and he said, I have experience in large-scale sample surveys. I find that LSS is functioning better than I had ever expected. Next one. So indeed, it is PCM's tenacity and wisdom has given the world, the statistical world, the 75-year-old well-acclaimed phenomenon called National Sample Survey, and its data is being used for promotion of better lives to policy decisions and research projects of Government of India. Next. And also, it should be remembered that the Economics Nobel of 2015 was based on data on the consumption. Dieter and Kosovo has a paper on this as well, the World Bank Research Observer. And also, welfare economics of Amartya Sen was also based on the NSS data. So you can see how important this NSS data looks like. Next one. These surveys greatly helped the government to introduce various reforms for the betterment of society and human welfare, which Mahalanobis always wanted. Next one. PCM was also responsible for the Central Statistical Organization a year later. He gave a model for second five-year plan, as we know, in 54. And there's a perfective planning division in the mid-50s. Isaac, he started in 1915 in Calcutta. Isaac is for the international officers who used to come to ISI and get trained in statistical education. It's a 10-month course in ISI going on, and they are also celebrating the Jubilee this year, Platinum Jubilee. Next one. Now, if you look at the way in which Mahalanobis conducted surveys, it's not only just the household surveys. He was also interested in crop surveys from the times of Bengal famine, because he has got lots of observations on these food availability and so on. He was influenced by Habak, an ICS officer who was conducting crop surveys at that time by using some kind of cuts. So Maulana started using circular cuts to collect data and based on that estimate the area under crops. PCM's Jute survey in Bengal was conducted in 1940s, and his sample survey gave 7540 bales, one bale equal to 400 tons, and he used 600 to 700 employees, and he spent 8 lakhs of money. Whereas the complete liberation for the same thing that has a lower answer 6304, they employed about 50 times more employees, and then they had 10 times more money spent on that amount. So now between these two figures, you can't argue which is good and which is bad and so on. Therefore, the third figure, which is by the customs and trade figure, because jute is something which cannot be eaten, it has to be exported. At that time, just before independence, it used to go to Liverpool and Manchester and so on, and for the factories there. A little bit is left in the country for the local consumption. So if you add together, you get the customs and trade figure. Next one, please, which is quite close to the smaller basis figure. Next one. The customs and trade figure showed an estimate such that the sample survey estimate is 0.3%, minus 3.3%, while the complete liberation of government was minus 3.6%. And this convinced the whole world that one could use large-scale sample surveys for collection of data. And Moularbis also took care not only of the sampling errors involved, but also the non-sampling errors. He has his famous IPNS technique, interpreted repetitive network of samples, which he used in this service. Next one. Not only that, he also wanted to have an independent supervisory staff during the field operations, not just the collection of data by investigators. He had one level higher than that, called supervisors, who used to get and check, and not only that, he used to help the investigator. Actually, he got influenced by Kautilya's Arthashastra, where there is a need for cross-checking of independent set of by independent set of agents who were working under the disguise which was mentioned in Arthashastra. So Maulavis must have got his idea of having an independent supervisory staff to check the operations of National Sample Survey in the field. Next one. UN Statistical Subcommission on Sampling. This is again about Maulana BCC influence, and he wanted not only the commission but also the subcommission, especially for sampling, and they had one such subcommission. And their fifth session in December 51, they observed that they were much impressed by the high promise of the National Sample Survey and its potential value. Next one. Next one, please. In view of the dual control of the NSS by the field wing of Directorate, the Government of India, and the technical wing in ISI, there used to be a lot of delays in publication of results. Naturally, when somebody is doing some work in the field and somebody is collecting and trying to analyze that thing in the technical area in ISI, there were delays and the results are not coming properly on time. Next one. So what happened? The government of India appointed a three-man committee consisting of Sivaraman, Dandekar, and R.R. Bahadur, who recommended that these two should be combined and should be called a National Sample Survey Organization, NSSO, in 1970. Next one. Nearly after 3 decades, a third review committee by J. Roy and S. Ramanathan Iyer was appointed in 1999 to again review what was been happening during the NSS and NSSO. The next one. And in view of the Roy Iyer Committee recommendations, in the year 2000, immediately after Roy Iyer Committee recommendations, the government of India set up a commission to address appropriately the growing statistical needs of the society. And this National Statistical Commission was chaired by none other than Dr. C. Rangarajan. Next one. The report of the Rangarajan Commission covers the modern era of Indian official statistics and offers a wide variety of suggestions. About 600 or so suggestions were given, and most of these recommendations have been implemented, and they are still being implemented one by one. And it is still called the National Statistical Commission, even though the Rangarajan Commission wanted to have another name for that one. Next one. Well, we know that non-response and refusals are a major problem in the collection of surveys. So the National Statistical Commission, they had a law to enforce the collection of statistics, such as Collection of Statistics Act of 2008, and it will be helpful only in certain situations. It was done by the second National Statistical Commission, but unfortunately still there was a lag, and some of the people and some of the agencies are not giving the data on time. Next one, please. Awareness is the most important, and more attempts should be taken to make it popular in the collection of statistics of data. Actually, as we are all statisticians, we are all aware of what is happening around us. And as you know, that there used to be what's known as the NSS consumer expenditure data based on the calorie content. They used to have a poverty estimate by the Planning Commission, but now there is no Planning Commission, and now the thing is taken care of by the NITI Aayog, as we all know. So the NSS and NSC, they provide the data in their reports and so on. Sometimes the reports are not on time, and sometimes they are delayed and so on. And we are all familiar with the controversies that have arisen and so on. But at the same time, we know that the good work is being carried out, and things are coming out properly for the policy decisions and so on. Uh, and also, we should be aware of other things like what happens. We should not be guided all the time by what the, for example, media says and so on. For example, Maharana Base, as we know, was a champion in the National Sample Survey as well as the large-scale sample surveys. He has been as a member of the UNSC, UN Statistical Commission, since 1945 for a number of years, and also he chaired two sessions of the UNSC. And also in India, V.R. Rao, who was the Director General, also chaired one session in 1951. So we have a long history with UN Statistical Commission. But a couple of years back, we were all saying that India became a member of the UNSC for the first time and so on and so forth. But as we know that we have been not only the member but also the chairpersons for consecutive Maulana Beast twice or thrice and so on, V.R. Rao once and so on. So we have to be aware of the things around this statistics day is one thing which makes us aware of things around, and I'm sure most of us are ready to accept this one. Next one. PCM, there is a question. Somebody asked me, is he a statistician or a data scientist or both? PCM as a statistician, you know that we have a large-scale sample surveys, Maharanabi's distance, IPNS technique, and so on. This IPNS technique, Debbie used to say that I didn't know that it has been done by Maharanabi's. It has been there for quite some time. And also, Maharanabi's is the pilot surveys is one thing which Abraham Wald mentions in sequential analysis book, that he didn't know that Amalarabi started his pilot surveys, but his sequential sampling is again same thing based on the Mahalarabi's pilot surveys and so on. And also the traveling salesman problem, when people at US, they are trying to find out what is the best way and what is the optimum size and what is the expected time taken and the cost and so on. During the 30s itself, 30s, late 30s, Mahalanobis himself has already calculated what it would be and how we can get the expected cost for that, which is proportional to square root of the number of units to be selected and things like that. So he has been already ahead of everything. And as a data scientist, he advocated cross-examination of the data a la Fisher. So Fisher used to say that a statistician should not only look at just take the data and accept it, he should also first cross-examine the data. And Maulana did that during his first paper in Sankhya, first edition, 1933. He took the old 1893 data of Risley's anthropometric on the tribes of northern India, and he corrected the data because there were some discrepancies there, and he has corrected and published it, corrected the version. And Fisher suggested that it is the best data scientist papers at that time. He may not have used the word data scientist, but he said it's a good data analysis and recommended very much that paper. And also his data on meteorological data and flood research data, etc., are all very well known. For example, he has done flood research data for 60 years, and based on that, he recommended that when there was a flood from Brahmani River near Katak, Mahanagar and Karak and Bhubaneswar areas. He suggested that there is no need to increase the height of the bund. It's at the river bank, as the engineers suggested, which involves a lot of cost. But what we have to do is we have to build a dam near the original area, and then that resulted in the catchment area that they had the dam, and that is this recent dam there, which was built hydro project there near Sambalpur. Next one. So another question somebody asked me long time back was, does VCM know about machine learning? I don't know whether he knew or not, but VCM did a very interesting thing. He had these facet machines which were imported in ISI, which all our student statisticians and the workers used to use. And he asked the workshop in ISI to construct what's known as the Sankhya Yantra. They had something similar to the facet machine, and it was only now in exhibition. It was very costly, and one couldn't proceed those things and so on. So what he did, he dismantled the facet machine, and he learned from that machine how it looks like, and started explaining to the people in his workshop, and they produced this Sankhya Yantra. But little did he know at that time, his ML uses D square, and he uses the multivariate tool later on. Next one. Mononomial distance is not just only a fundamental contribution to classical multivariate analysis and taxonomical classification. It is found to have an important role in machine learning, pattern recognition, and artificial intelligence. Next one, please. Now, I'll just give some few examples for the young students here. I have been giving this in some seminars already. Maybe some of you are already aware of these. Suppose you say that the ages of 10 employees in a government department are noted as these 10 numbers. What is the mean age? So as you know, that mean is just nothing but the sum of 10 numbers divided by 10. The mathematician will say that adding these numbers, which gives you 430, and divided by that, the answer is 30. Next one, please. The mathematician's answer is 430 by 10 or 43. If you give it to Google, Gemini, or all these chat GPTs, they will give it the answer is 43. But they don't look at the data. As a statistician, as a data scientist, should cross-examine the data and note that in the government office, there are age limits for employment. So 16 and 73 are errors in this, and they cannot be. So he may have to compute something like a truncated mean of 8 observations and so on. This is something which sometimes the AI or the chat GPT, they all miss those things. Next one. Another favorite example of mine is this. You have data of these 30 numbers here. Closely examine the data and comment. What is the point here? So this is a replica of one of the examples which Professor Sierra faced in 1945 Bengal anthropometric survey. I put it in a different language so that you can all understand that easily. So look at this data. You don't find anywhere 6 or 7 or 8 or 9. So that means if you look at the next slide, next one, the point is that is not a decimal, because you don't find 6, 7, 8 or 9. So it's something rounded after 6. So that's when you compute the average, you take the average modulo 6, you don't take it like a decimal and so on. This is something which normally the other things which use your artificial things don't tell you. So as a statistician, you notice that thing. So, and then if you don't have to know cricket for this, in fact, these are the number of overs bowled by a cricketer in one-day matches. And if you ask somebody to calculate the average, maybe your child or your brother or your sister, they will be able to compute because they don't know cricket very well. Otherwise, the statistician has to look at this and try to get the revised estimate for average. Next one. Now, briefly on learning resources, the application of software. Now, some of the students use software data without following what are the assumptions behind that. So they look at the theoretical background behind that thing. So unless they understand the theoretical background, it will be difficult to see how things come out of this thing and what exactly is happening and so on. I'll give you an example. So sometime back, one of the students had a contingency chi-square test on R rows and K columns. So he has been using, there are just, how many rows are there? Start with the row. There is a column which says on the top rows and then other things. Then there is a column which is columns and which says the columns and so on. So he has been using, there are R rows and K columns in all. Therefore, it's R into K as the degrees of freedom instead of our statistical R minus 1 into S minus 1. He was just counting the number of rows and number of columns, not just looking at the numbers which are inside that. So he has got R into K instead of R minus 1 into K. So when using the secondary data, even if it was collected by you, the cross-examination of the data is a must. So start with the corrected data and use that corrected data for your calculations and so on. That is something which is very important and must be done. Next one, please. Now I'll give you some more examples. Thinking outside the box. What do you mean by this? Normally, when you give the students some problems, they will immediately look at it and jump and they will remember this. My teacher did this, and they give you an answer. The question is this: from probability theory, of three independent events A, B, and C, the probability of A only occurs is P, B only occurs is Q, and C only occurs is R. Find the probability that none of the event occurs. I've seen many students trying to immediately jump and say that, this is just independent events, so complement A prime, B prime, C meant, therefore the answer is 1 minus P into 1 minus K into 1 minus R. Several students and even some research scholars got bowled over by this example. They immediately jump and say it's 1 minus P into 1 minus Q into 1 minus R. Of course, they don't say 1 minus PQR, but there are some who said also the answer is 1 minus PQR. So I suggest that some of the young students to go ahead and calculate this and show it to your teachers the correct answer. It's none of those. Next one. Next one, please. Mahalanobis was the chief architect of the Indian statistical system. He gave us the National Sample Survey, CSO, Central Statistical Organization, State Statistical Bureaus, Perspective Planning Division, and several other important statistical things. To go quote a few of these things, and above all, the Indian Statistical Institute, as you know, a mighty monument of his handicraft, as C.R. Rao puts it. It's no wonder that National Statistics Day is observed on his birthday, that is today. An international prize is instituted in his name. A building is named after him. A postage stamp and first day cover were released. And the list goes on and on and on. Next one. The United Nations Statistical Commission, in its resolution at the 17th session of the 1972, they condoled the death of Mahalanobis as remembering his pioneering efforts on behalf of social statistics, remembering him as the champion of statistical leads of developing countries, remembering the outstanding stimulus he gave to the statistical development throughout the entire world. Next one. It is now the age of big data, IoT, AI, etc., etc. Looking at the big data or IoT or playing with AI alone is not enough, as I have been mentioning. Big data, IoT themselves do not make better lives. Big data need not be better data, as we have been observing now. IoT and AI have to be carefully and judiciously managed. In fact, just previously, Professor Shane Gupta also mentioned about this judicious use and how carefully it has to be used and so on. Another thing is, especially if you go to the health statistics and so on, the medical scenario, privacy of individual has to be guarded. That's quite something very important which has to be taken care of. And also, there could be dangers of using sometimes in a bad way, like the deep fake and so on. So one has to be very careful with these things and so on. So the statisticians have to have a big role in this to make things look better. Next one. It's the better data, better understanding of concepts, and the better use of statistics, including AI, arising out of these, that leads to a better human welfare, as Maulana Nabi always wanted. Next one. Thank you all for your attention and happy Statistics Day. Thank you very much.
Thank you, sir. Thank you for your wonderful lecture on this National Statistics Day, recalling the contributions of Professor P.C. Mahalanobis as an architect of establishing a very good national statistical system in India and establishing the Center for a higher seat of learning of statistics in India. And thank you, sir. Thank you very much. Hope that there won't be any questions. However, if there are any comments, I welcome. And
Yes, sir.
to make it, Professor Dilip,
Yes, sir.
let me take the first one.
Sir, I have not question. This is query for me. You have discussed top cutting experiment by Mr. Mahlobis and also of PB Sukhatme. So, as per your idea, which tool is more efficient?
I'm sorry, I can't.
No, you said that crop cutting experiment of Professor P.C. Mahalobis and also of PB Sukhatme. Now, as per your idea, which techniques is more efficient if you apply?
Professor Rao,
Yeah.
Professor
Apart from
Dilip is asking which one is which one you could recommend, whether the crop cutting survey recommended by Professor PCM or Professor Sukatme. Which one you would which one you would recommend?
Actually, Mahanarabis himself said several times that you can have a joint representation and try to check for that thing. It has been done by the Planning Commission at that time, and they found that it's not really the area. Of course, Mahanarabis is small areas and so on. He also mentioned that he should not. So he increased the size of the cuts, the crop statistics, and so on. And finally, the Planning Commission with the committee, they decided they did experiments, and it's not really the size or anything, etc. Of course, you have to have a larger size, not the small 2 feet radius which has been taking. They have to large, smaller one. But then they decided it's mainly the errors which they are making about the collection of the data, the field work, and so on. So Mahalanobis' theory was that the circle has the smallest errors when you compare with the other rectangles, and so if you take the pi r square and so on, that's the best thing to do. So that was his argument for that thing. But essentially, it is the field work by the organized by supervised by the planning commission that in the 70s, I think they did that. They found that it's perfectly all right and so on. But actually, as we all know, Mahararabi's never was sort of angry or anything with anybody else like Sakatmi. He, in fact, he he sent one of his papers, he recommended one of his papers for one journal. Normally, so those days, one used to recommend a paper. You have to communicate a paper. That he communicated, and Sukatme worked with Maharabis in ISA for a while, and they had very nice rapport. For example, when Maharabis gave a lecture on why statistics in 1950 Pune conference, Sukatme gave on why sampling. He gave another example. So Deming used to say that even though sometimes he was a bit harsh and so on, he really never discouraged anybody, and he was always cordial with the people and so on. So that way he has some very great ideas and so on. Thank you. Thank you for
Thank you, sir.
inviting this.
Thank you, sir.
Thank you.
Professor Rao, I have a doubt that anything which we want to learn, we need a formal material for learning. In that regard, of course, for statistics and all disciplines, we have books. As far as official statistics is concerned, particularly Indian official statistics is concerned, it has a very long history, as you described, and of course you have also authored two articles. One appeared in Resonance Journal also. I From that only I learned about the basics of Indian statistical system. I mean. The establishment of the Indian statistical system. Is there any proper record of? Is there any book yeah, consolidating the details about the world the statistical system as well as an Indian official statistics? Is there any book on Indian official statistics? Because nowadays it is the duty of the teachers also the basics, particularly the history of the history of any discipline to the upcoming generations. In that respect, is there any book on Indian official statistics which can be recommended to the learners?
Uh, Actually, at ISI, Professor J.K. Ghosh used to be a bit worried about these official statistics. In 1999, J.K. Ghosh, myself, and some of other colleagues, we joined, and we had a paper in the International Statistics Review on the evolution of statistics in India. That was one in 1999. So after that, I also got interested in official statistics, and in 2010, in the Journal of Official Statistics from Sweden, I contributed a paper on statistics in India, past and present. That was in 2010. And then later, J.K. Ghosh once again said that we have to sit once more because there was this problem with the collection of. Uh, Actually, let's look at the problem of GDP, computation of GDP. That's one of the important things when official statistics is done. So you have two things. One is based on the surveys, and one is based on the national accounts data. So there were some controversies about these things, the national sample survey data and national accounts data and so on. So what was the problem? In the 80s, Dr. Minnas, who was the chairman of the governing council at that time, he had lots of observations and suggested what is to be done. And he criticized the way both accounting was done and so on and how it's done. Then later on, there were several committees appointed and so on. Each committee has its own way of giving the poverty estimates and so on and so forth. Uh, what we did later, J.K. Ghosh once again, is that suggested some other procedures for collecting more and more data. Things have improved slowly. For example, the data earlier was not available for companies and so on. There's something called MCA, and that data has been using, but that again is not completely out. So there were some problems with the updation. Naturally, after some time again, they revised the GDP and so on and so forth. So this causes some confusion with the user. As a user, we will not understand why is this happening and things like that. In fact, one thing again which we perhaps missed this time is the census. From 1881, we have been having continuously every 10 years and so on. This year, after COVID, we missed it, and I think just now it started. Now in 2025, we are now having started the national census. So with these gaps and the change in the base period, there was this confusion for the user and so on. And therefore, I'm sure that this 75th year of National Sample Survey will be a good benchmark for the government official statistics to look for the future and try to make it more usable and understandable for the commoner, for the user. Because on these statistics, that's the whole idea, to make people aware of statistics of the country and so on. So we already have a strong tradition, and we should continue to build up the tradition and try to keep it up and so on. That's the thing. Thank you.
Thank you, sir. Thank you.
Sir, may I ask one question? Hello.
Yes, yes, madam.
Yeah, I would like to ask about one of the vertical in national education policy, that is Indian Knowledge System, ICAS. So, if we are having ICAS as a part of statistics education, what basically most of the institutes they are including in that is how data collection system has evolved over the time in India. So, can you guide us as what should be taught under this, and are there any references with respect to this?
Yeah,
Basically, your lecture has
can I
flown.
request you
Yeah.
to send me your email ID, please? I will try to definitely answer. My ID is possible. Uh, Dr. Satish Kumar will supply you the ID. Can you?
Sure,
So
sure, sir.
my ID is tjrao7@gmail.com. I will definitely answer your question. Sure.
Sure, sir. Sure. Thank you. Thank you very much.
If there are no further questions or comments, let us conclude this session. Sir, thank you, Professor Tejara, for making a
Thank you.
very
Thank
good
you so much. Thank you. Thank
sir.
you very much.
And on behalf of the organizing committee, I thank you once again. And I hand over the session to the organizers, Professor Satish Kumar. Thank you for giving me this opportunity. It's a wonderful, wonderful opportunity and experience to chair this session. Thank you, sir. Thank you very much.
Thank you. Namaskar. Thank you. I'm sorry about this hearing problem and so on. Thank you.
Okay.
Sir,
Uh, yeah.
It
sir,
was
may
not at all
I
a
ask
problem,
a
sir. You
question?
heard, you answered the questions. You gave very good clarification, sir. No doubt in it.
Yeah. Yeah.
Sir, am I
Yes.
audible? May I ask a question, sir?
Yeah, please. If I can hear you.
Yes, sir. Sir, actually, I am having doubt regarding membership of UNSD. Sir,
Yeah.
yes,
At that time, perhaps forgetting that Maulana has been there since 45 and so on and so forth. Maulana had a very big hand in the United Nations Statistical Council. Not only that, he also insisted on having something for the subsamples. There's also United Nations subsampling committee, subcommittee on sampling. So this is at the insistence of Hararabis, who used to not only just look at the Indian large-scale surveys and so on, but also for all the other governments and so on. So everybody used to follow. So as the he was also not a very interesting person. He was also wanted to have a review committee on NSS, and he had Fisher, Linder, Yates, all these people as the members of that first review committee of NSS. And they suggested it's doing well. Only thing is, it has to very quickly publish its data. And also, they said that other countries have something to follow from Mahalanabi. They have something to teach from this thing. And really, he was just the leading figure at that time. So Mahalanabi really has a good role in the UNSC. So
so
we
sir,
are
this is the
perhaps
third
glad
time we are
to.
getting membership.
Yeah.
Sir,
Yeah.
I was asking that is this third time we are getting membership after Mahalanobis sir and P.R. Rao sir?
C.R. Rao didn't have to go. Maulana visited after that. There were other people who were taken care of. There was a gap, as I said. And again, I think last year it was re-elected. Now it's a 4-year term. We have a 4 years term for the UNSC.
Okay, sir. Thank you so much, sir.
To have
There are not many things to hear from your experience, sir. However, the time is so important. So I request all the participants to contact Professor TJ Rao through his mail, tjrao@gmail.com. And thank you, sir. And I hand over the session to the organizers, Professor Satish Kumar.
Yeah, Professor.
Thank you.
Thank you, Professor. Thank you, Professor T.J. Rao, for your very excellent talk, very informative talk, in fact. And also thankful
thank you very much. Thank you, everybody. Thank you, everybody.
Thank you for the, nicely managing this session and chairing, supporting us through as a chair of the session. And in fact, we have a little 2-3 minutes, no problem, because we have given time in between while these types of deliberations are quite relevant. That's why. So because of several are asking questions like that. And in fact, in next session we will start put it the time as 11:30. So now there are 2-3 minutes, no problem. Of course. If anything you have to add, no, you can do. Otherwise, we can move to the next session. We are very much thankful to you, Professor Rao, for your
Thank you very much.
deliberations. Yeah, thank you. And also Professor Logadan, sir.
Thank you.
I hope we can, within 2-3 minutes, we can move to the next session. Anyone have to add anything, please? I hope in the next session we have Professor Somesh Kumar is here in the group. Yeah. And Professor Kajan Jain to chair the session. Yeah. Hi, madam.
Hello. Thank you, Professor Satish.
Welcome, madam.
I could not send the abstract as my husband was not very well.
Good morning, madam.
Good morning, sir. कैसे हैं आप?
बढ़िया हैं, आप कैसे हैं?
ठीक है सर. चल रहा है.
आई एम फॉर्चुनेट आपको मेरा सेशन चेयर कर रही हैं. अभी पिछली बार भी आपने मेरा सेशन चेयर किया था.
ओके.
कुरुक्षेत्र में शायद.
हाँ जी, कुरुक्षेत्र में किया. Yes. Professor Satish keeps on giving us opportunity to see each other.
We are also lucky to have your presence, madam, and assist.
Thank you, sir, Professor Satish. I wanted to give a talk, but my husband is not well, so I couldn't concentrate on that.
Oh, okay. I just tried to contact you, but I don't know. I know.
Really, I had been too busy for the last 10 days. He is quite bad.
Okay. Our prayers are always with you, madam.
Thank you.
For very much helps. Let us move to the session, I think so, because 2-3 minutes by the time the introduction, etc., we can take that. Our students, Tori or Lakshmi. Hello. Let's please introduce the chair and help her to run the session in a smooth way.
My voice was clear, no? Is it?
Yes. Clear.
Oh.
It must be raining a lot in Kerala.
No, not process. Well, now there is raining, but today is no problem. Yesterday, yeah.
Here in Kharagpur, it has been raining a lot now.
Even here, in Chandigarh also.
Hello, Ashwini. Ashwini, Angela, someone there?
Network issue.
And probably, yeah, it's a slight network issue maybe. Yeah. Some audio problems maybe. Yeah. Just,
There
we have
seems to
tried.
be.
Anjana or Ashwini? Valerie?
I think you call them through their mobiles.
Yes, sir. Anjana Baiju will host the session.
Okay, okay, okay. Please. Please ask her to introduce.
Anjana, please take over the session.
Audible, sir?
Yeah,
Yes.
yeah. Yes, audible.
Sorry for the delay.
No problem, please.
Network issue.
Yeah.
So, good morning, ladies and gentlemen. It's my privilege to welcome you all to the third technical session of the 10th International Webinar on the recent trends in statistical theory and applications. Today, we are honored to have with us two distinguished individuals whose presence truly elevates the value of this gathering. Let me begin by introducing the chair of this session, Dr. Kanchan Jain from Punjab University, Chandigarh. Dr. Jain is a distinguished academician and senior faculty member in the Department of Statistics at Punjab University. She has made significant contributions in the areas of multivariate analysis, statistical inference, and sampling theory. Her work has been published widely in reputed national and international journals. Now, I have the pleasure of introducing our speaker for this session, Professor Somesh Kumar from the IIT Kharagpur. Professor Kumar is a renowned expert in statistics and mathematics with particular expertise in statistical inference and decision theory. Over the years, he has made significant contributions through high impact research publications and has guided numerous students in their academic and research pursuits. This plenary session is being held in honor of Professor S.N. Roy, whose foundational contributions to the field of statistics continue to inspire and shape modern statistical theory and applications. Please join me in warmly welcoming Dr. Kanchan Jain, chair of the session, and Professor Somesh Kaur, our esteemed speaker. Over to you, ma'am.
Thank you. Um, so it's an honor to chair this session, and I thank Professor Satish Kumar for this opportunity. Though she introduced Professor Somesh, but I'd like to add few more things to his introduction. Professor Somesh Kumar is from Department of Mathematics, Indian Statistical Institute, Kharagpur. He is an elected member of International Statistical Institute, Netherlands, and received Professor K.S. Rao Best Researcher Award from ISPS in 2022. His research interests are actually, there is a long list of his research interests. I'll just read out one or two. So, decision theoretic estimation, Bayesian estimation, and estimation of boundary parameters, reliability and hazard rate estimation, estimation under equality constraints, reliability ordering, inference in parameters, on parameters in directional distributions, quantum computation, and quantum information. Sorry, Professor, two research interests, so I can't read. You are a multifaceted personality. So he has to his credit 115 publications and a number of book chapters and publications in conference proceedings. He has developed 5 video courses and involved in consultancy for Calcutta Port Trust and Government of Tamil Nadu. He has to his credit 19 PhD supervisions and has held many institute and departmental responsibilities. He'll be speaking on tests for simultaneous homogeneity of effects against simultaneous ordered alternatives in two-way heteroscedastic ANOVA models with interaction. So over to Professor Somesh. I think you will have 35 to 40 minutes. Although you can have 35, 5 for discussion.
Thank you, Professor Jain, for very generous introduction. First of all, I thank Professor Satish Kumar for organizing this conference very regularly, and then he invites me. So, thank you very much. And so today it is an auspicious day because it happens to be birthday of Professor P.C. Mahalanobis. And the session which I am giving a talk, it is called in honor of Professor S.N. Roy. So actually, I am an academic descendant of these two, because Professor S.N. Roy did his PhD under Professor P.C. Mahalanobis, and I am actually grand student of student of Professor S.N. Roy. So Professor S.N. Roy's student was Ingram Olkin, his student was Maurice Eaton, and his student was Professor Divakar Sharma, and then I am there. So I am from his genealogy. So it's a privilege and very happy moment for me to speak in this session. So let me share my slides now. So is my slide visible?
Yes.
Okay. So I will be speaking on the test for simultaneous homogeneity of effects against simultaneous ordered alternatives in two-way heteroscedastic ANOVA models with interaction. So actually it is the research work of my PhD students, my current PhD student, Mr. Raju Day. So this is still unpublished actually. We have prepared the work has been done and we have prepared the paper, but not yet published. So, but I thought this is a good occasion to just present this one. So let me just brief about this one. The abstract says, so is my slide changing?
Yes, sir.
Okay. Yes, sir. Yeah. So quite often it is noted in the factorial experiments that in the planning of the treatments and other factors, the responses actually show certain monotonic trends. So that means they may be increasing or decreasing, etc. So here what we have considered a two-way ANOVA model with the heteroscedastic variances and unbalanced cell sizes. And the null hypothesis is that the simple effects of both the factors are simultaneously homogeneous. And the alternative hypothesis is that they are simultaneously following a monotone ordering. For this type of testing problem, we develop the likelihood ratio test and multiple comparison tests, and then the procedures, how to implement them, the simulation studies are there, and then there is a software package. So let me introduce the model here. So this is a well-known two-way analysis of variance model with the interaction factor, which we write as xijk is equal to mu plus alpha I plus beta j plus gamma ijk, and plus the error terms. Now, here you can notice that I am writing k is equal to 1 to nij. That means in each cell you may have nij number of elements which may be unequal. So it is not necessarily a balanced sample sizes. Although the design is balanced, because we are having A row factors and B column factors here. The important point which we note here in the third bullet point is that the epsilon ijks are independently distributed as normal 0 sigma ij square. So this is a major deviation from the standard two-way ANOVA model where we take normal 0 sigma square. So here we have considered them to be varied. Now this is the thing which creates statistical challenges, because when we take normal 0 sigma square, then most of the analysis can be done in a standard way, because we get the independent chi-square distributions with a common divisor, and then we can have the addition, then we can have the division, so to get t statistic, f statistic, etc. So they are the standard tests. So when the sigma ij square is not necessarily equal, it presents some statistical challenges, and then this is the problem that we have been handling for past couple of years in various models actually. So this is one of the you can say advanced models in that direction. So so some problems of this nature have been done earlier. So for example, two-way ANOVA model with factors treatment and center are used in clinical trials performed across multiple centers, and it has been frequently observed that across the centers we will have the heterogeneity of the treatment effects. And now when we consider the model which I mentioned here, that is alpha I plus beta j plus gamma ij, here alpha i's and beta j's are the main effects of the row factors and the column factors, and gamma ij is the interaction factor. But many times what happens that it is better to actually investigate alpha I plus gamma ij, which are called simple row effects, or if we consider the same thing for the column, it is called beta j plus gamma ij. So this type of study has been there in many papers which we have gone through, and I have just given reference of some of them here. Then there are constants that we have that we call generally the estimability constants. That is the sigma alpha is equal to 0, sigma beta j is 0, sigma gamma ij over j, and sigma gamma ij over I. They are all 0. So to just give a brief literature review here, in one or two ANOVA models, it is often observed that experimental conditions lead to ordering of constants on the effects of one or both factors. So the problem to test is whether they are significantly ordered or not. Rather than just checking whether they are significantly different or not, we just check whether they are significantly ordered or not. So that means the full parameter space becomes constant here. Now, there are various studies on this, so experiments in biological and environmental sciences, ecology, psychological studies, clinical trials, etc. In many of them, there is frequently the observation to have monotonic effects. And starting from Bartholomew in 1959, Barlow et al. Is a classical book on this, then Hirotsu, Munsinge and Wright, and so on. There are a large number of papers and as well as texts on this. Now, due to these constraints, the testing against restricted alternatives is considered to be more appropriate than the natural alternative in testing, because this produces more powerful tests. This is a comment that I have written in the last bullet point, and this is what we have observed in many other studies, starting from Bartholomew and on. So if we consider some example here, so this is a two-way ANOVA model, and here the tail flip time is considered as the response variable. And the factor AS, so this is an active ingredient of marijuana, and here there are three dose levels. One is 0.0, second is 0.5, and the third one is 1.0 milligram per kilogram. And factor B, it is morphine with 4 dose levels, again 0.0, 0.5, 1 and 2.5. So here the tail flip time actually measures the pain threshold by determining the time between the application of a heat stimulus and the animal's tail flip. So now this data has been there in the paper by Solokova. From the sample means in table 2 of this paper, it is observed that the mean differences at different levels of factors are not all equal. That means there is a chance of interaction between the factors. So that means the two-way crossed ANOVA is the more appropriate model here. And another thing which is observed is that since both of these are sort of drugs here, marijuana as well as the morphine, therefore both of them are likely to have increasing effects if we increase the dosages. There is another example that we have considered here, that is the education and economic status. How do they influence the life expectancy in various countries? So here, this is a two-way model by taking life expectancy as a response variable, education as a factor A having 3 levels, that is the number of years of schooling between 11 to 13 or between 13 to 15 or between 15 to 17, and economic status as factor having 2 two levels, that is the developing and developed. So the differences in the mean effects of the factors
మొత్తం తగ్గించేది ఇట్టింది തെറ്റിപ്പോയി നാട്ടില്ല മൂന്ന് പത്തൊന്നായിട്ടില്ല Sir, I'm Nikhil from Kerala University. I want to talk regarding the conference. Secondly, please check your mail, sir. Email, sir. Email, sir. Yes, sir. I think, okay. Please just click on that link. So, I think, yes, sir. Yes, sir. I said. Yes, I reply to the earlier mail. send it once. Send it to two email IDs. Yes, sir. Okay, I think we need a Google Gmail ID. Okay, it's asking email. I think maybe it's trying to sign in other Hotmail account or something. Otherwise, yes, sir. Yes, sir. Okay. Okay. So I will send an invitation to this. Yes, sir. Yes, sir. One second, sir. I send an invitation to the Gmail account. Can you check in the Gmail, sir? Okay. You- I think it's dvd7@gmail.com. Okay, sir. No, he's trying to join. I think he's in technical issue. He's in medical college. Madhya Pradesh. Yes, sir, it's working. The meeting is going on. Yes, sir. Yeah. Yeah, that's correct. Mike, okay. Okay, give it accept the access. Give it access. Okay. 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 Are you using Mac? Okay. Okay. Please click on Mac settings. I think yes, sir. one second. Not in the Google Meet. Okay. There is a okay. Join. Yes, sir. Yeah, I can see now, sir. Can see your photos. Okay, but I think you have to switch on the mic as well.
Yes, it is open now.
Yes.
Meeting is going on.
Yes, sir. Yes, sir.
So you just let me know when I have to start, okay?
Yes, sir.
Good morning, Professor Satish Kumar. Good morning. Good morning.
Good morning, Professor. Good morning. Morning.
Good morning. Thank you.
In fact, we are very
Yes, I back to India.
I feel very happy to see Professor Ghosh everywhere.
Thank you, sir. Thank you, sir.
Pleasure.
Thank you, sir. Suresh.
Hi, Professor. Please unmute your mic, Professor. Unmute your mic. Yes, unmute.
Yes, good to see you.
Very nice meeting you, sir.
My pleasure. Always meeting people is always blessing.
Yeah. Whether Professor Satish,
Let us
He is there. He is very much there.
it is time to start.
To introduce a person of the session, a distinguished scholar whose work in statistics has inspired countless individuals, Professor K.K. Suresh. Professor Suresh is a senior faculty member in the Department of Statistics at Bharathiar University, Coimbatore. Holding a PhD in statistics from the same institution, he has made significant contributions in statistical quality control, reliability analysis, sampling inspection plans, and applied statistics. An active participant in academic and professional circles, Professor Suresh engages in conferences, workshops, and collaborative research, leaving a lasting impact on students, peers, and the broader statistical community. Now, I'm honored to introduce our esteemed specially invited speaker. We have Professor Sadanand Dwivedi, a renowned academician, researcher, and biostatistician. Currently a professor in the Department of Biostatistics at AIMS, New Delhi, he brings over 30 years of expertise in teaching, research, and statistical consultancy. With more than 240 publications in reputed journals, Professor Dwivedi is a leading authority in biostatistics and epidemiology. With these introductions, I now respectfully invite our chair, Professor K.K. Suresh, to lead the session. Over to you, sir.
First of all, I thank Professor Satish for giving me a nice opportunity. And I request Professor Sadanand Trivedi to be brief in his presentation. And I request now to give him his presentation.
welcome,
Okay?
Professor.
Thank you.
Please unmute. Okay.
Sorry.
Yeah. No problem. Yeah.
No, I have some.
You can take 35 minutes.
Okay.
Professor Trivedi.
Yes, please. Just a moment. Share entire screen. screen is visible of my talk?
Yeah, yeah, it is fine now. We can make it bigger.
Is it okay?
Okay, okay, fine, fine.
Yeah, so first of all, I would like to thank you all, especially Professor Suresh, Professor Satish Kumar, and Professor Ghosh. My friend Professor Ghosh, I could see him on the screen. And I would like to give a special thanks to provide this opportunity to be with you all, specifically because yours is the theoretical department and we have been playing in the applied field. Why did I choose this topic? The reason is very simple because your theme of the conference, the international webinar, is on the statistical theory and applications. So I thought that the what is the major factor which plays important role while deciding the statistical tool, starting from planning of the study to carrying out the study to, and I find major issue which we statisticians should take into account. And reason is very simple. Even analytical methods might be same regardless of the study design, but while interpreting the data, we have to be very specific. The data was collected using which study design. And I will come on those basic issues. What do we mean by study design? I hope that by now you people might be having some applied paper in your setup and students will get benefit out of this talk. Now, in the public health generally, what happens, the obvious tendency of the clinician or physician is always to correlate something with something, means exposure to some outcome. Like if exposure is negative, then bad outcomes. If the exposure is good, like treatment drugs, outcome will be better, means cure rate and improvement. This is the usual tendency in public health. They always look for associating exposure with the outcome. And to understand the whole topic, I will advise you all to remember that the outcome is outcome. You people know it, dependent variable means it might be cure rate, it might be the mortality, it might be the survival, depending on our research question and objective. But exposure out of various factors, specifically in the observational study, is the factor in which we are interested. Like if you want to see the association of smoking with coronary heart disease, the smoking is exposure. Coronary heart disease is the outcome. So I think one can take thousands of examples as per your area of specialization or application. Now in public health, what happens? There is a directionality between exposure and outcome. Generally, if I say more than 90% of the study, people don't care about this. And those studies fall in the category of cross-sectional study. I will come on those issues specifically later. But let me tell you, this is the scenario generally in any area. There are prevailing sustainable host factors, means there might be malnutrition, there might be genetic factors, there might be poverty prevailing in the community, or in the family, or in the individuals. But suddenly the exposure of bacteria takes place either directly or from the other infections through the bloodstream. And that leads to infection, and infection leads to tissue invasion. And then, for example, I have quoted ocular tuberculosis, eye tuberculosis. And reason is why I took this slide, just to tell you what I mean by the directionality, means exposure should precede the outcome. Generally, what happens in public health, if you collect the data and don't care of the directionality, somebody who is being diagnosed with the coronary heart disease and who happen to be non-smoker and non-drinker throughout life, out of frustration, they might become a smoker. So just to avoid this kind of inaccuracy in the data, we have to ensure which study design was used to collect the data. I think that is the issue we have to remember. So there are two issues important. When are we starting the study? Means prospective timing means each study begins prior to the occurrence of the exposure and outcome. Retrospective means the occurrence of the study takes place after the everything has happened, exposure and outcome. And best example here is Bhopal gas disaster. When it took place, everything happened, and a study by the Indian Council of Medical Research was started later on. So that is best example to understand the retrospective timing of the study. Now, coming to the directionality of the data, the, the coming to the directionality of the data, here the issue here is that the sorry the here issue here is there are two ways. First, we collect data on exposure, and then we go on collecting data on outcome. That is known as in public health forward direction. And backward direction is first we collect data on disease status, and then we collect data on exposure. Backward direction. So accordingly, the name of the study design is considered. Broadly, there are two groups of study design. One is the prevalence study, disease frequency, what in other words it is known as the cross-sectional study. And cross-sectional study, what happens, once we go for data collection, everything we record as prevailing on the day of the study. Means everything. We are not taking into account the directionality, we are not taking into account the timing of the study. Everything is happening on the day of survey. Means any variable we are recording as prevailing on the day of survey, any outcome we are recording as prevailing on the date of survey. So I think if there is no directionality between exposure and outcome, every such study will fall in the category of cross-sectional study. The next broader group is there are advantages and disadvantages. Because of the time limit, I cannot elaborate much, but cross-sectional study is the easiest study design. Most of the PG students generally they use the cross-sectional approach. They carry out the comparative cross-sectional study, and reason being that they have limited time, they have limited resources. So they can finish within 1.5 years to 2 years everything, planning of the study, execution of the study, data collection, and all these things they keep doing. So issue here is for them cross-sectional study becomes easier. And if it is at the hospital setup, it further becomes easier. So we have to be very clear whether we are planning a study at community level, we are planning at the hospital level. And hospital level study cannot be generalized for the community level findings. The major disadvantage of the cross-sectional design is we cannot estimate the risk ratio. I hope you people are aware about what do we mean by risk ratio, what do you mean by odds ratio. Depending on the study design, this is measure of risk. Means if someone is exposure, for example, maybe 2-3 folds more at the higher risk of suffering from coronary heart disease, something like that. Any measure we an interval estimate always is quoted because point estimate alone does not serve the purpose. So same issues what we have been dealing in the descriptive statistics. Anytime you report the mean interval estimate has to be there. Anytime you estimate the proportion, you have to report interval estimate as well. The cross-sectional study, thousands of study you will find in literature. Another group of the study design falls in the category of the incidence study. There are various synonyms: cohort study, follow-up study, concurrent study, longitudinal study, prospective study. And here the issue here is I will take 2 slides to explain you. If you see the upper diagram, study begins when exposure and disease has already taken place. And that is why I told the best example is the Bhopal gas disaster. And if we are starting a study after everything has happened, this kind of study is known as the forward retrospective. We are data collection, we are starting from exposure, and then we are going towards data collection on the disease. And that is why it is called as the forward retrospective. But in public health, it is known as the historical cohort. The second design, what we do it, we are starting when everything has happened. But because disease is rare, we start with the disease status. We take the set of required number of diseased people, and we take the desired number of the non-diseased people, and then we go retrospectively to collect backward side and collect data on exposure. And here I would like to caution there. We have taken disease and non-diseased people, but among the disease and non-disease, we have collected data on the exposure retrospectively. Like, are you a smoker? Yes, no. Those who are no, have you ever smoked? And those who are currently smoker and ever smoked, we have to collect data on since how long you have been a smoker. On an average, how many bundles of berries and cigarette per day you consume. This is known as the density problem in public health. Using that data, you have to create the covariate. And scale of measurement, being a statistician, we all should be aware that the scale of measurement plays a big role. So along with the study design, the which scale I need to consider. And simply like people take smokers, yes, no. And which is totally wrong. We can have publication. We can go on hundreds of publication. But appropriate consideration, if it is not there, then our findings will not stand valid. So I will advise, being a statistician, what is our role? Wherever we are, we have to ensure appropriate consideration of the covariates, which are the confounders, which are the effect modifiers, what should be the scale of measurement, what should be the categories of the covariate, whether continuous variables should be considered as continuous, or we need to categorize. All these issues a big debate. It takes time. Because in AIMS, let me tell you, for more than 3 decades, we used to especially cry just to make sure, and that is why, because their clinicians are very well comfortable with the research methodology. So if our goal is to talk in terms of risk factor, we have to ensure the appropriate study design. And if you are considering the cross-sectional study, comparative cross-sectional study, which I showed you earlier, the using the term risk factor is not allowed. We have to use the associated factors. Very clear. Our study design of the study does not allow us to use those terminology until unless we have ensured the directionality about the data collection on smoker and heart disease. Now, next, if you see the upper design, forward prospective cohort study, and randomized control trial RCT. I think all of you might be aware because of the corona, because randomized control trial on the vaccine took place. And AIMS New Delhi was the central coordinator center. I was there. So issue here is prospective design means very simple, that you are taking exposed and non-exposed group. For example, under observational study, you are taking those who were exposed to gas and those who were not exposed to gas, and then you are going to follow long term what kind of disease pattern prevails in that cohort. That is under the observational study. But the moment you call randomized control trial, exposure is under the control of the investigator. And that's where the randomization takes place. And generally, we have to be very clear about the randomization. Time will not permit to elaborate much more, but being a statistician, I will like to simply remind you, all of you know it, that if we do not understand the importance of randomization, who else on the earth will understand the meaning of randomization? Randomization should not be taken as an English language until unless it has been done appropriately under a study. So we statisticians have to take care of. Another design is sometimes we are study using the prospective cohort, but outcome is rare. And there is a specific research question by the PhD, and we have to simply reply like under population-based profile, case control design had to be used in the early years. After 10 years or 20 years only, the figures started coming because cancer is very rare, we all know it. So there you can use the nested case control design. Nested case control design means it is case control design carried out using the data collected under prospective cohort. Very simple. Because if cohort is very huge and if you take too large number of control, real relationship between exposure and outcome might get masked. We statisticians should appreciate and should take care of. That is why we recommend that the go on the case control design, take number of available cases, and then take the controls. And case control design, one can do 1:1, 1:2, 1:3, 1:4. We have done research. One of my PhD student worked on this, that what maximum number of controls may be taken to conduct the case control design. Publications are already there, and if you see there, if our goal is to find out the risk factors, the even 1:1 design is okay. But like statistician, if somebody is more particular about to decide and estimate of the one has to use the 1:4. And that will stabilize the variance, means stabilization of the estimated standard error. There are advantages and disadvantages. I have indicated already. We have to take care of. And under case control design, again, efficient sampling of exposure is possible because we are starting from exposed and non-exposed. We can have the direct estimate of risk ratio, which is not possible out of the case control design. And clear temporal sequence of exposure and disease is there. And can perform survival SIP analysis, time to event. I think these days, this topic is under master's course, I believe. In our days, this topic was not there. We learned when we joined the job. When I joined the Indian Council of Medical Research as research officer, then became senior research officer after 1 year. Then after 4 years only, I joined the AIMS. So the issue here is time to event data in public health is prevailing. Many areas, cancer studies, you can take many of the RCTs where this is the timing varies, inclusion of the study from one time to other time, over time, because it depends on what frequency of the availability of the patient is there. So these issues we have to take care. And so many publications. These days you can go on seeing that. Under randomized control trial, what happens? Very simple. Either we need to compare new drug versus the gold standard or new drug versus the placebo, no treatment. Times randomized control trial are done. Like in case of vaccine, ideally we were comparing the new drug versus placebo, whether it is efficacious or not. Now, types of clinical trial is starts from the vitro study, and from vitro study, if biology is understood of that topic, then animal studies are done on very small number because of the Maneka Gandhi issue. We cannot sacrifice too many animals under the study. And then if drug seems to be little better, then we go on the volunteers, phase 1 trial, with a small number of patients, volunteers, 10 to 20 or 30. And then if toxicity is lower there, which clinician can compromise, then we choose the specific doses and go on the phase 2 trial. Phase 2 trial have the 2 arms, 3 arms, 4 arms of the study, depending on the scenario under phase 1 trial, how many doses have been found, which have lower side effect, which have lower toxicity. And remember that the being a statistician, from in vitro study to phase 2 trial, there is no involvement of the sample size exploration. Generally, what we have to do it, as a rule of thumb, we have to consider everywhere recommendation is there. Only pilot study has to be done. Pocock says if you study his randomized control trial book, then you will find that he has recommended that a minimum of 100 to 200 patients in each arm has to be there under phase 2 trial. But believe me, none of the PG student is able to consider that large number. And ideally, even preliminary phase 2 trial is conducted. So we have to remember all these issues. The sample size exploration comes in under phase 3 trial. And under phase 3 trial, what happens? That the after you declare, if the study finds that the vaccine is efficacious or drug is efficacious, it can go for the marketing. It can go for the practice in the hospital level and clinic level. And that is why every component has to be planned seriously for phase 3 trial. And phase 4 trial, again, there is no involvement of anything. In routine clinical practice, you have to keep recording possible side effect if it is there. So always remember that the देखो हमारा talk चल रहा मम्मी को कॉल करिए मैं So issue here is we under phase 2 trial, if you see all the hospitals and major private practitioners, they have their own computer system, they develop their database of their own patient who go to them, and using those data one can explore what is the pattern of toxicity, whether it is same as observed under phase 3 trial, or while under the practice the toxicity has gone up. And if it has gone up, then policy planners have to take a call whether drug can still remain in the market or we have to stop. So this is, we have to be very clear. Under RCT, there are specific hypotheses. Superiority trials means both direction. One may be the superior to other one. Non-inferiority trials means new drug might be non-inferior to standard drug. Even one of my students has done non-inferiority trial. If some of you are interested, you can Google. It is regarding the treatment of the thyroid patient through the use of the radioiodine active dose. And that is the globally first trial that has changed the clinical practice globally. Instead of using the higher doses, preferred doses, now one can use the lower doses, 25 millicurie, and there is no involvement of toxicity and no involvement of the isolation rules for admission of the patient. So always remember that the statistician has to play a big role to generate the evidence which can guide, we can modify the future public health practice and the clinical practice. Similarly, non-superiority trial, but non-superiority trial is not done. At least to my knowledge, often in clinical practice, non-inferiority trial is done. And if at all required, the equivalence trial is there, which involves both non-inferiority component as well as non-superiority component. Because time is not there, I'm sorry, I cannot elaborate the related components that the what are the issues we have to take care of. This is classic randomized control trial. Investigator control random assignment has to be done. And this how we do it. And typically we go in this way. After randomization, we have got patient under the study group. We have got patient under the non-experimental group, control group. And then we start data collection baseline. Then we give the intervention under placebo, no intervention. There are specific guidelines how to ensure that the intervention and non-intervention group get the same kind of capsule or tablet. Only thing is control group will get placebo. There is no medicine in that. And then last follow-up as per the time limit fixed for the recording of the outcome. So this is how we go on doing that. So now randomized control trial, even the so many trials you will find. To summarize the study design, I think this will help you to keep in your mind how to conceptualize about the study design. And for a statistician, it should not be a difficult task to conceptualize the ideas. If you see here, we have to start from, did investigator assign intervention? If yes, then only a study will be experimental study. But if random allocation is ensured, if random allocation is yes, then only it will be a randomized control trial. If random allocation is no, it will remain a semi-experimental study, no RCT. So what a statistician should know, that the randomization is not simple English language. We all know it. It involves two components. One is generation of the unpredictable allocation sequence, and another is to maintain concealment until a patient goes into a specific study arm. So I think there is a big area. I think it requires a couple of days for detailed discussion. I am trying to give you the take-home message with a simple terminology. If on the same topic with same research question RCTs are conducted, multiple RCTs, and they have reported the conflicting findings, then, like in treatment of the cancer, neoadjuvant chemotherapy, some of the study have reported that it is efficacious regarding the breast conserving surgery. Some of the studies reported that it is not. And that is how one of my PhD students worked on the systematic review meta-analysis and believe me, she had 14, 15 international publication on this topic, systematic review meta-analysis. This is just to encourage the younger PG student, because they can plan accordingly. If you are meticulous, you can do the things. Now, if intervention is not under control of the investigator, those kind of study becomes observational study. And under observational study, if there is involvement of the comparison group, then only that study is known as analytical study. An analytical study are of three types: cross-sectional, case control, cohort study. I have already explained you, considering the directionality and timing of the study. If there is no comparison group, then that study is known as descriptive study. Like many of the PG students simply carry out their dissertation in their department, having the profiling of the patients who are attending that specific OPD and clinic. So I think this will help you to conceptualize the study. And this you have got, I think, enough host of literature. And here, unit of study is certainly under descriptive study. It is individual, ecological study, community based, district level data analysis, state level data analysis, country level. Generally, the anthropologists, generally you will see the ecological scientists, they carry out this kind of study. One of my friend, Professor Adinaran, we used to do from Coimbatore. He used to carry out and even guide PhD students on these ecological studies. Cross-sectional study, cohort study, case control design, individual. And under the RCT, what will happen? Under clinical trial, it will remain individual, but field trial, like vaccine trial, it will remain individual again. If you are doing even at community level, you have to provide the vaccine to everyone individually. But if community trial is using community randomization, means education CME program, one is carrying out at community level, those kind of studies are known as community trial. So we have to be very clear what are the RCTs, what are the field trial, what are the, and then only in case of the conflicting findings, systematic review and meta-analysis of the RCTs, there is global consensus. These days you will find in literature, people are doing even systematic review meta-analysis of cross-sectional study and case control design. But in my opinion, that is of no use. Carrying out systematic review meta-analysis is what? To help the public health person and clinician that yes, there are conflicting findings, but if you pool the information, this is the scenario, whether a drug or intervention is efficacious or not. So I think in other study design, at least I am not convinced. And that is what you have to take care of. And generally, a physician is always interested about causality. Observational study, descriptive study, no ability, because there is no comparison group. But under comparative analytical study, cross-sectional study has a weak strength, cohort study has a moderate, case control design has a moderate, Ecological studies again have the weak strength about the causality. But randomized control trial, they are all strong. Even community trial intervention studies, if you take it is moderate, but if you do it meticulously, the evidence will be very useful for the public health researcher and the clinician. So, misses what I try to give you, that the depending on the specific design of the study as per the research question of the study, the level of the evidence created through those studies varies. Like if you see this, up to cross-sectional study, these data only help to generate the hypothesis, just to give the ideas on the topic. Then case control design gives the meaning with outcome. Just you are associating, because there, if you are doing 1:1, 1:2, 1:3, standard error estimate will keep varying. So while doing the things we learn, this case control design just will give us how it is associated if you do this study. But cohort study will give us the idea about relationship with the outcome. And if you are interested to talk in terms of the causality, there is no substitute of the randomized control trial and clinical trial. And as I told you, in case of conflicting findings under randomized control trial, we have to carry out the systematic review and meta-analysis. So I think for every study design, I have quoted here in this just three example. There are guidelines available. First guideline is STROBE, strengthening the reporting of observational studies in epidemiology. Guidelines for reporting of randomized control trial consort. But these within consort, you will find the guideline for parallel design. You will find the guideline for the non-inferiority trial. You will find the guideline for the equivalence trial. So much development is taking place globally. So as a researcher, we have to keep updating ourselves. What is the updated knowledge, and accordingly try to learn and then replicate in day-to-day clinical research field. Then third is the guideline for reporting systematic review and meta-analysis. And here, preferred reporting items for systematic review and meta-analysis, here PRISMA guidelines is available. And if you are interested, even if you Google in my name, you will find all kind of publication. So now summary is, use of a study design depends on considered research question. Without research question, we cannot be aware whether our study involves a hypothesis or not. Descriptive study does not involve hypothesis. All other study involves the hypothesis of the study. Study design plays a crucial role in its planning. For every study design, we have a separate way of planning, execution, data collection, analysis, interpretation, and implication. I have already indicated limitation of some of the study design. Prospective cohort study is a preferred study design for an observational study. To generate evidence for clinical practice, a large-scale multi-centric randomized control trial is a preferred choice. Like you might have seen the news while the trial were going on the vaccines. We have to be very, very clear, because here life of the people involves. In case of conflicting finding, as I told you, we can go for the systematic review and meta-analysis. So I think there are series of references one can these days. I think on the Google everything is available, in PubMed everything is available. I would like to formally thank Professor Satish Kumar and who contacted me for this webinar. And in spite of the fact that I am busy in other webinar today itself, but I gave my consent that the Kerala has a special place in my heart. Let me tell you, my boss, when I joined AIMS, was from Kerala, Professor K.R. Sundaram. Unfortunately, he is no more. So I used to visit Kochi, Trivandrum, and all these places for lecturing. So I have little association with that part of the and recently we had our society's conference in Kottayam, and I was president for that conference. So I have that. Other faculty scientists of the department actually kindly excuse me for my ignorance. just I thought that I should not miss thanking and appreciating and expressing my gratefulness to each and everyone involved in this setup to conduct this kind of webinar. And obviously, finally, I would like to thank my present college, RD Gandhi Medical College, Ujjain. So thank you very much. If there is any specific queries and question, I would love to try to explain.
Professor Suresh, you have to unmute your mic, Professor. Unmute your mic. Professor Suresh, to unmute mic. The mic is muted. Okay, now it is okay.
Well, the excellent result presented by Professor S.N. Trivedi on decisive cohort studies in public health. So I am very much thankful to Professor Trivedi and Professor Satish Kumar. Now it's a time for asking one or two clarification from the scholars who are interested.
E-card.
I hope there is no query from the student side or persons who are hearing. I request Satish Kumar to take charge and continue and guide me.
Thank you, Professor Dwivedi, for your excellent talk. Professor Dwivedi, for your excellent talk. Very much, and we are very much thankful to you, Professor, for your
My pleasure, sir. My pleasure.
And also, I wish to extend our gratitude to Professor K.K. Suresh, sir, for chairing this session and for your support to our conference.
Thank you very much, Satish Kumar.
Thank you, sir. Thank you.
Grateful to you, sir. Thank you.
Okay, thank you, Professor Dwivedi.
Thank you, sir. Thank you.
And in fact, we are several have some questions probably. They will contact you, Professor, through email. Or
Welcome, sir. Whatever little I can do.
Yeah, okay, Professor. Now, let us have a lunch break time. And after that, before 2, you please join for the next session. Professor N. Filippo from Greece. He will talk on some. Yes. So
You can kindly excuse me, sir. Can I leave now?
Yeah, Professor. In
Yeah.
fact, we have the short lunch break earlier,
Thank
but
you.
the other
Thank you.
speaker is not here. We have about 55 minutes there, or we can take 50 minutes, and after that, we can all of us
Thank you.
can join together once
Thank you,
again.
sir.
Okay, thank you.
Thank you. Thank you. Thank you.
Thank you very much.
Thank you, Professor. Thank you, Professor Ghosh. Now you are here or USA?
No,
In
I
India?
came back. I came back in January.
Oh, okay, Professor. Okay.
But after that, I went to my hometown for 1 month.
Okay.
And then Kedarnath, Badrinath.
Oh, okay.
And these were cities always just traveling.
Yeah.
Significant place.
Yeah, great. Thank you, sir.
So one thing I want to tell you.
Yeah.
See, I am ready to give you 1 lakh rupees to your association for one award under my name. Will
Okay,
it be
Professor.
possible?
Okay.
Will it be possible?
Yeah, possible. That's great.
Okay, then I'll give you 1 lakh rupees.
Okay, Professor. Okay. Thank you.
Thank you. Thank you.
Thank you.
ദിവസം കിട്ടുന്നല്ലേ?
Hello, Professor.
Hello.
Hello.
How are you?
Fine, Professor. Fine, doing well. Yeah. Professor, Professor Filippo is also here.
He's there online, I think.
Yeah.
He's muted.
Yeah, okay.
Yeah.
We are ready.
Yeah, now the right time we can start, Professor. Okay, welcome, Professor. Devika, please.
Good afternoon to all esteemed participants, scholars, and attendees. It is my privilege to welcome you to the keynote section of the 10th International Webinar on Recent Trends in Statistical Theory and Applications, a global forum that continues to unite researchers and academicians in the field of statistics for the exchange of ideas, innovation, and impactful dialogue. We are truly honored to have this section chaired by an eminent statistician, Dr. David D. Hanagal, professor in the Department of Statistics at Savitribai Phule, Pune University, India. Dr. Hanagal is widely recognized for his significant contribution to survival analysis, reality models, and statistical applications in biomedical science. His leadership and insight make him an ideal chair for this significant section. And now it is with great pleasure that we welcome our keynote speaker, Dr. Andrei Filippov from the University of Patras, Greece, and former Education Minister of the Government of Cyprus. Dr. Filippov is a respected academic whose work has greatly influenced modern statistical theory. He has made substantial contributions to probability distribution, reliability theory, and statistical inference, and continues to shape the academic landscape with both theoretical depth and practical relevance. We are truly privileged to have him with us today, and we look forward to an enlightening keynote address. I now invite Dr. David D. Hanagal, the chair of this section, to kindly offer his opening remarks and formally introduce our keynote speaker. Over to you, sir.
Okay, thank you. Thank you for the introduction. Good afternoon to all of you. It's the first day of the conference in the afternoon session. First of all, I want to wish everyone happy National Statistics Day. The keynote speaker today is Professor Andreas N. Filippo. He's from University of Patras, Greece. He's a former education minister, government of Cyprus. His topic today he is going to talk on Fibonacci numbers, probability, and gambling.
It is.
We can see the screen presentation.
Dear colleagues, first of all, I want to congratulate Professor Satish Kumar for organizing in such a wonderful matter WSTA 2025. My interest on Fibonacci numbers and probability distributions over decay started several years ago when I spent some time at the American University of Beirut. That's the first time I got to know what the Fibonacci numbers are. And working with a friend of mine, at this university, we tried to find the probability of waiting for the kth consecutive success, and we found out that this probability is related to the Fibonacci numbers of order k. We could not prove that this probability added to 1. This we were able to prove with 2 colleagues at the University of Patras a few years later. And we named that the probability the geometric distribution of order k. And adding distributions of order k, we were able to get the negative binomial distribution of order k. Later, with a PhD student of mine, we were able to find the binomial distribution of order k. And after that, several students of mine and colleagues were able to find many distributions of order k. And just to recap, any distribution of order k is simply an infinite class of distributions indexed by k. For k equal to 1, it is the classical distribution. So, let me start with my topic today. I will say a few things on Fibonacci numbers, a few things on distributions of order k, and the odds in some odd-even games. Leonardo Fibonacci was born in Pisa, Italy. He traveled a lot and wrote a lot. His most famous was Liber Abaci, Book of Calculation, through which he introduced the Hindu Arabic numerals to Europe. The numbers 1, 1, 2, 3, 5, 8, 13, 21, etc., formally defined by the recurrence relation 1, 1, have been named Fibonacci numbers by 19th century French mathematician Edouard Lucas to honor Fibonacci. Of course, we now know that the Fibonacci numbers were found many years before Fibonacci in India. However, as things stand, the Fibonacci numbers are named to honor Fibonacci and not the Indians who found them hundreds of years earlier than him. The astronomer Johann Kepler rediscovered them in 1611. Lucas studied them extensively, and the sequence 1, 3, 4, 7, etc., formally defined by the recurrence 1, 2, bears his name. During the 20th century, interest in the Fibonacci numbers and their applications rose rapidly. In 1961, the Russian Vorobyov published the Fibonacci numbers, and Hogarth Jr. in America followed in 1969 with Fibonacci and Lucas numbers. In 1963, Hogarth Jr. founded the Fibonacci Association and started publishing the Fibonacci Quarterly. Finally, in 1984, the first international conference on Fibonacci numbers and their applications was held at the University of Patras, Greece, when I was vice rector, and the proceedings were published by Rydell. The second was held in Santa Clara, California, the third in Pisa, Italy, and so on, one every 2 years in Europe and the USA, respectively. Their proceedings have been published by Kruger until 2004. 7 of the proceedings were edited by myself, Bergum, who was the the editor of the Fibonacci Quarterly, and Horadam, an Australian mathematician. The Fibonacci Association started publishing
the proceedings from 2014 until 2024, and from this year, Taylor and Francis took the job. The Fibonacci numbers, as most of us know, appear almost everywhere in sunflowers, pineapples, and phyllodaxes. They appear in geometry and architecture, in computer science and probability theory, in coding and gambling. The scrambled version, 1332211185, of the first 8 of them appears in the Da Vinci Code, a novel by D. Brown. He wrote that in 2003, and there is a film on them. The name Fibonacci numbers actually was given to Fibonacci because of the rabbit problem. I will just read the problem for you, and anyone who is listening can count the numbers and find the answer, or can prove this in a different way. On January 1st, there is a pair of adult rabbits in an enclosure. This pair produces 1 pair of baby rabbits on February 1st and 1 pair of baby rabbits on the first day of each month thereafter. Each baby pair grows to be an adult pair in 1 month and produces a baby pair on the first day of the 3rd month of their life, as well as on the first day of each month thereafter. What is the total number of pairs of rabbits in the enclosure a year later, on January 1st, after the day's births? By counting or otherwise, one can find out that the total number is 377. And this is simply the adult rabbits and the baby rabbits, and that's F sub 14, which equals F sub 13 plus F sub 12. And that's why the name of this sequence was given to Fibonacci. The Fibonacci numbers, however, were known in India many, many centuries earlier. Golden section, alpha, or golden ratio, golden mean, divine proportion. And according to Euclid's Elements, the famous Greek mathematician of antiquity, a straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the less. Suppose we want to divide the line segment AB into 2 line segments AS and SB, so that AB divided by AS equals AS divided by SB. If we set X equal to AS divided by SB, we get X, you see this equation, which is if and only if X squared minus X minus 1 equals to 0. This equation has 2 roots, alpha equal 1 plus square root of 5 divided by 2, which is an irrational number, 1.61803, etc., and beta equal 1 minus divided by square root of 5 divided by 2, which equals minus a number, an irrational number. Therefore, alpha is simply the first one because it's a positive number. The first denoted here by alpha, even though it is usually denoted by phi, in honor of the Greek sculptor Phidias, because that's how in Greek his name is written, has been called golden section, golden ratio, golden mean, or divine proportion. The numbers alpha and beta are irrational. And you can see below that triangle. There is a geometric construction of S, given line AB, can be done as follows. You have the line AB. Construct a perpendicular BC at point B, with BC half the length of AB. Draw hypotenuse AC. B. Draw an arc with center C and radius CB. This arc intersects the hypotenuse AC at point D. Draw an arc with center A and radius AD. This arc intersects the line AB at point C. Excuse me, at point S. AS is really what AB divided by S is really alpha. And S is the golden section. Let me now just mention that if we take the limit of Fn plus 1 divided by Fn as n goes to infinity, this is simply alpha. And that's a very simple but important result, that the Fibonacci numbers are related to the golden section, are related to the divine proportion. And as we know, if we divide the longest length of the Parthenon to the shortest one, that number is equal to alpha. And people say, architects say, that one of the reasons that the architecture of Parthenon is so important is because of alpha, because of the golden ratio. The proof is very simple. The only difficulty is to prove that the limit exists. And bright mathematicians know how to do it. One of the important formulas regarding the Fibonacci numbers are the Binet formulas. That is, Fn is equal to alpha to the power of n minus beta to the power of n divided by alpha minus beta. And Ln, the Lucas numbers, are a to the power n plus beta to the power n. The proof is simple. One just sets un equal to e to the power n minus beta to the power n divided by alpha minus beta, and observes that un satisfies the defining relationship of Fn. The same is done with V sub n. I just give here a list of some important Fibonacci numbers. I think that one of the most important ones is 5.4, which relates Fibonacci numbers to the binomial coefficients. I indicate here that the proof that the sum of the Fibonacci numbers and Fibonacci numbers is simply Fn plus 2 minus 1 is given simply by the definition. Two results involving infinite series and Fibonacci numbers are shown in 6.1. The second one was established by a high school student. And if one tries to generalize the second one, it's rather difficult. And you may try to, instead of using f sub 2 to the power of I, use the Fibonacci numbers or use the Fibonacci numbers of order k. You may not be able to find that sum, and that is still an open question. Now let's turn to I indicate on top how Sn is found, and let's move to probability and Fibonacci numbers. Suppose you toss a coin until a head appears 2 consecutive times. And if we know this by E sub 2, in general, if we want to toss a preferred coin until a head appears n consecutive times, and we denote this by En, we want to find the probability of En. Here I indicate how one could try to find the answer. just by starting for n equal 2, 3, and 4, and simply probability of E sub 2 is F1 divided by 2 to the second power. E3, probability of E sub 3 is F sub 2 divided by 2 to the third power. And the probability of E sub 4 is equal to F sub 3 divided by the 2 to the power of 4. And in general, it can be proven that probability of E sub n is equal to probability of F sub n minus 1 divided by 2 to the power of n. In fact, much more can be shown, the following. And this was proven by this speaker and Muwafi, a Palestinian in Beirut, Lebanon in 1980. It was published in 1982. Denote by T sub k the number of independent trials with success probability P. Q is simply 1 minus P, until the occurrence of the kth consecutive success. Then, for n greater or equal to k, F sub k of n, which is equal to the probability of T sub k equal n, is this long guy to the right, where the summation is taken over all k tuples of non-negative integers such that n1 plus 2n2 plus k and k is equal to n minus k. Now, the proof is not really difficult. We simply have to note that T sub k equal to n is an arrangement A, which is stated below. The last k are successes, and in all the previous trials, there are no k consecutive successes. There could be isolated successes, 2 consecutive successes, 3 consecutive successes, etc., k minus 1 consecutive successes, and the last k are consecutive successes. Once one recognizes these, everything else follows. I'm not going to tell you the details. The important is that if n1, n2, and k are fixed, then the number of the a's is simply the multinomial coefficient shown below. And each probability is given below, and therefore the probability of all a's, ni non-negative and fixed, I from 0 to n, is the probability shown below. But the non-negative integers, n1, n2, and k, may vary subject to the condition n1 plus 2, n2 plus k, and k equal minus k, and this completes the proof of the theorem. The important question that we ask ourselves at the time in Beirut, is f sub k of n a proper probability mass function? If it is, it meant we discover an infinite family of probability distributions, of which the first one, for k equal to 1, would be the geometric distribution of the classical probability distribution. Well, in Patras, a couple of years later, we were able to find the answer. The answer is yes, and it only depends on this beautiful transformation, 7.1, and the multinomial theorem. Once we were able to establish that this is a proper probability mass function, we were able to find its probability generating function, shown below, and then the mean and the variance. Distribution of T sub k, the geometric distribution of order k with parameter p, Since for k equal to 1, it reduces to f sub 1 of n equal to q to the power n minus 1 times p for n greater or equal than 1. A different derivation of GKS was first given by Feller by a much more difficult way. Theorem 7.1 can gave rise to several distributions of order k, and that's what I mentioned at the beginning. To it, we have the following corollary. Let Tk be as in theorem 7.1 and assume that p is equal to 1/2. Then the probability of t sub k equal to n is simply f sub n minus k plus 1 divided by 2 to the power n. F is, we use a superscript k to indicate that this is a number of order k, which means that once we have the first numbers, the next number greater or equal than k is found by adding the previous k numbers. That's why we call it Fibonacci numbers of order k. And for k equal to 2, these numbers reduce to the usual Fibonacci numbers, and we have the formula to the right. P sub 2 equal n is simply f sub n minus 1 divided by 2 to the power of n. Now, if one tries to evaluate probabilities with the previous formula that I just mentioned, it is very difficult because every time you have to solve a Diophantine equation. However, a few years later, a PhD student of mine and myself were able to prove the following very, very beautiful recurrent relation. F sub k of k is simply p to the power of k. F sub k of n is equal to q p to the power k for all n between k plus 1 and 2k. It's very interesting that no matter how n changes, the probability remains the same, q times p to the power k. And for n greater than 2k plus 1, we have the recurrence. Simply, f sub k of n is f sub k of n minus 1 minus q p to the k power fk of n minus k minus 1. And now let's move on to probability, and this is my last but one section, probability, Fibonacci, and gambling. We all know that some people like to gamble, and we all know that most people lose money, little money or lots of money. There are two well-publicized cases of individuals who beat the casinos, winning a lot of money. There are also quite a few who won once or a few times. Millions, however, lose every day. That is why casinos exist and thrive. There are three popular systems of gambling among gamblers: the WR-bet, the Fibonacci, and the endowment system. Now, the WR-bet system, in any game of chance, you start by betting a certain amount of money, say $8. If you win, you stop. If you lose, you double your bet by wagering $2. If you win, you stop. You bet $4, and so on. It appears, and all of you listening to this talk think the system is unbeatable, earning you $8 when you win and stop. Now, In fact, it is not. Why? Pretty soon, you may end up not being able to double your bet for lack of money, or you may reach the upper limit posed by the casino. Either way, you are a loser. The Fibonacci system, it is the same, almost the same as the WR. Resembles the WR bet one, but it is less aggressive. Instead of doubling, you follow the Fibonacci sequence 1, 1, 2, 3, 5, 8, etc. So there's no difference. Again, you are going to lose if you follow this system. The Delabes system seems a little interesting, and quite a few who are not probabilists or statisticians, laymen, think that this is a good system. According to this system, in any game of chance, you increase or decrease the amount of your bet in a round, depending on whether you lost or won the previous round. The logic is that you lose one round, you are more likely to win on the next, and you should increase the amount of your bet. But this is completely erroneous. In a game of chance, the odds are always the same. And now my last section, the odds in somewhat even games. We wrote this paper with a friend of mine at the University of Texas at El Paso, Schuster, and published that in the American Mathematical Monthly in 1975. Problem 9.1. In tossing an unbiased die until a 6 appears, is the best odd. This will happen during the first trial, during the third trial, or the fifth, etc. Or even this will happen on the second trial, on the fourth, on the sixth. What if the die is biased? The answer is given in the following. I denoted that Bernoulli odd even game, but the correct would be geometric odd even game. In an odd even game of counting IID trials or Bernoulli trials with success probability P, until the occurrence of success, the best bet is odd, since probability of even is Q divided by Q plus 1, and probability of even minus probability of odd is Q minus 1 divided by Q plus 1. Problem 9.2. In counting the number of phone calls arriving at the switchboard of your university today, not September 29, at your university, University of Kerala, is the best bet 1, 3, 5, 7, or even 0 calls, 2, 4, 6, etc.? The answer is given in the following theorem. Poisson odd even game. In an odd even game of counting the number of occurrences of an event in positive time t, following the Poisson distribution with mean rate lambda t, the best bet is even, since probability of even is given by the formula below. Let me not read it to gain time. And probability of even minus probability of odd is e to the minus 2 lambda t. Lest one think that life is always so simple, consider the following generalization of problem 9.1, which is a sucker bet. In tossing an unbiased die until a 6 appears, r times, is the best bet odd, 1, 3, 5, or even 2, 4, 6? What is if the die is biased? The answer is based on the rather remarkable negative binomial odd even game. In an odd even game of counting the number of independent trials with success probability p until the occurrence of the nth success, the best bet is odd or even, providing r is odd or even, since probability of even is given below, and probability of even minus probability of odd is q minus 1 divided by q plus 1 to the power of r. Additional summer bets can be based on Theorem 9.4, binomial odd even game. In an odd even game of counting the number of successes in an n-independent Bernoulli trials with success probability p, the best bet is even, except when n is odd and p is greater or equal than 1 divided by 2, since probability of even is the first formula, and probability of even minus probability of odd is q minus p to the power of n. And here are my references. And I have finished. It will take me a couple of seconds to see and talk to you.
Okay, thank you, sir. Thank you very much, Professor Andrea, for delivering a interesting and innovative talk. Now, the next is the questions from the audience. If there are any questions or doubts, clarifications, then now you are welcome.
I thank you all. I thank you all, especially Professor Satish Kumar and you, Professor David Hannigan, for chairing this session. And let me say that there are many open problems on distributions of Word decay because of the theoretical results and because of many applications, reliability, startup tests, meteorology, etc. One very simple problem, but very difficult to solve, is to find the modes of the distributions of Word decay. The only proper solution known is that the geometric distribution of Word decay has a mode k. If we go to the negative binomial distributions of Word decay, there are only partial results. If we try to find the modes of the Poisson distributions of Word decay, again, there are partial results. And for the binomial distribution, nothing is known, etc. Now, since all probabilists and statisticians know that what is a mode? A mode is the most probable value of a probability mass function. We're talking about mass functions. And it would be good to know. I don't know. So here is simple problems. I mean, it's nothing really, but it's a problem, open, and maybe one of those people who are listening to this talk will find solutions to this. Thank you.
Thank you. I think there are no questions from the audience. Okay.
Yeah, someone has to say something. Yeah, please.
Thank you again.
Anyone?
Okay, over to Satish now. To you.
Okay. Thank you, Professor Filippo, for your wonderful talk. Very interesting talk. In fact, he has provided several open problems even through his deliberations, and the youngsters have a lot of opportunity to work in that way. I hope we will do some works in that respect. And also, we wish to extend our gratitude to Professor David Hannigan for chairing the session in a very nice way. In fact, we have.
I thank you.
Thank you, Professor. Thank you. We have some more time. I think 10 minutes is there for the next session. By the time, if you want to say anything, we have you all are welcome. How is Professor there in this?
I'm sorry, I'm not sure if you are talking to me. Well, as I said, I didn't say that. I did come to India many, many years ago. I came twice, once in New Delhi and once in Trivandrum in Kerala, due to Professor Satish Kumar. And I enjoyed my visit to your beautiful state. And I
Thank you,
made.
Professor. You are most welcome to
Thank you.
Kerala. Yeah. Okay. Just in December also we are doing conferences, but we utilize this occasion to invite you, Professor. Uh, how is Professor, your family, everyone okay? Josar, do you want to say anything?
I wish you the very best.
Thank you. Thank you. Thank you. It's not hearing person.
Hello? Hello?
Hello, Joseph.
Kakak sir. Sir.
Yeah. Do you want to say anything? That's fine.
Nothing. Professor Kanagal is there.
Yeah.
Professor Kanagal.
Yeah, how are you? Fine, thank you.
Yes. Boring.
In fact, while I'm doing research, I need some more papers connected with the Professor Filippo.
Oh,
I was
okay.
written. That time he was the education minister, I think, for some of the university of I think Cyprus, and he sent me a bulk of materials, his papers, and that helped me a lot. And also, I have done that respect some order K and continuing several things in that area. And thank you, Professor. In fact, we are very much glad to have, or nice to have your uh, uh, presence in this platform. And Professor Hane, you
Yeah,
can.
thank you.
Yeah. So, thank you, Professor. Okay, let us wait some more time, some few minutes for interaction. If you want to say anything, can interact. After 2-3 minutes, we can move to the next session, because the next session is scheduled at 2:50. Once again, thank you, professors, for your support and blessings to our event, our WSTA 2025 International Conference. Professor Sheila Mishra, you joined here. Hi, Professor Violeta.
How are you doing?
Yeah, fine, man. Fine, Professor. Fine.
Great job as always.
Yeah,
Thank you for this opportunity.
Thank you. Next time, you also please send a abstract for your talk.
Right now, it was really difficult. I have a pile of papers to grade, unfortunately, but I promise for December a presentation or
Great. Thank you.
organizing a session.
Oh, very good, very good.
Okay.
Okay. Yeah,
Okay.
very good.
Best regards, Professor.
Thank
And
you.
thank you very much.
Thank you, Rosa. Yeah. So we hope to have a session from your side. Thank you. So I have to check the speakers in the next session. I think they have to join. I'm just check. So I have to contact them. Yeah.
ഇൻഷുറൻസ് ഇല്ലാത്തല്ല മേലാണ് ബി എ ഓൾ ബി സി ഓൾ സി അങ്ങനെ
Good afternoon, Sheila teacher.
Yes, good afternoon. So we are supposed to wait for another 3 minutes, right?
Yes, teacher.
Yeah.
Sure.
ബി എല്ലാം ബെസ്റ്റ് പേപ്പർ സി എല്ലാം കോൺഗ്രസ്
So very good afternoon to all of you.
Yeah, madam. Just a minute. Yeah, students. I think Anjana.
Yes, sir.
Anjana, please introduce the chair and do the needful for the session.
Okay, sir. Good afternoon, everyone. It is my privilege to welcome you all to the third technical session of the 10th International Webinar on Rates and Trends in Statistical Theory and Applications, which is a special invited session. We are truly honored to have Dr. Sheila Misra, Professor of Statistics at the University of Lucknow, India, as the chair of this session. With over 3 decades of academic and research excellence, Dr. Sheila Misra has made significant contributions in the field of survey sampling, biostatistics, and measurement error modeling. She has published extensively, held key academic leadership roles, and served as a visiting professor at the University of North Carolina, Greensboro. We are privileged to have her guidance today. We are also delighted to introduce our distinguished speakers for this session. Dr. K. Kumar, Senior Professor of Statistics at the University of Calicut, a respected academician with vast expertise and long-standing contribution to statistical education and research. Dr. Jaydevan Sridharan, Professor of Biostatistics at Gulf Medical University, Ajman, UAE. He brings valuable expertise in medical statistics and public health research. We look forward to rich and engaging session under the able leadership of Dr. Sheila Misra and the insightful presentations by our esteemed speakers. Let us begin the session. Over to you, ma'am.
Okay, thank you very much for kindly introducing the session and the speakers as well. So it is my pleasure, first of all, to congratulate each and everyone on the birthday of our legendary statistician and the planner and the person who showed a path to all the statisticians globally, Professor P.C. Mahalanobis, whose birthday we are celebrating in this conference as well. And in the morning inaugural session, we have already done a lot the remembrance. So our homage to the legendary figure. And with that, it is my pleasure to welcome you all in the technical session number 6, the special invited sessions. We are having 2 speakers, as you are told. So we shall start with Professor K. Jayakumar, University of Calicut, India. And the professor shall be sharing the views on completely monotone functions and their role in the study of distributions. So we welcome you, Professor. Kindly enlighten us, our participants and everyone on your topic. Thank you very much.
Thank you, madam. Thank you very much. And thank you, Professor Sadish. Okay, let me share my screen first.
Yeah.
Oh. Is it visible?
Yeah. Now it's visible.
Yes. Yes, sir.
So, good afternoon to all. And today I am talking on the topic on completely monotone functions and their role in the study of probability distributions, especially in defining continuous positive valued random variables and their distributions.
Sorry to interrupt you, sir, since there are 2 speakers, so I would request you to do your talk in 30 minutes. Thank you, sir.
30 minutes, okay. So I will have to finish my talk by 3:20. Is it okay?
Yes, sir.
Oh, okay, thank you. So my topic is on completely monotone functions and their role in the study of probability distributions, especially as I have already told, it is on the distributions concentrated on the positive half of the real line. And as we all know, the completely monotone functions are defined through it is distinguished based on the nature of the derivatives of the Laplace transform of a given function. Or in other words, the complete monotonicity is defined through the nature of the derivatives. So, the completely monotone functions play a major role in defining Laplace transform of probability distributions on R plus, and as such, on the study on distribution theory. So, a function which is on 0 infinity, we will call it as completely monotone function. Let the function be phi lambda. Or we say that it is completely monotone if minus 1 to the power n d to the power d n by d lambda to the power n phi lambda is greater than or equal to 0 for n is equal to 1, 2, 3, etc. So if this happens, then we will say that the function is completely monotone. And so if you put n is equal to 1, we can see that minus first derivative is positive, which implies that the first derivative should be negative. And if you take n is equal to 2, we have minus 1 square d squared by d lambda square of I lambda is positive, which means that the second derivative should be positive. Automatically, we have the third derivative should be negative, fourth derivative is positive, and so on. So if you have a function whose successive derivatives have the signs of the sort minus, plus, minus, plus, minus, and so on, then we will say that the function phi lambda is a completely monotone function. And there exists a lot of functions in the literature which has of this sort. Which in fact has the behavior of this sort. For example, if I may take my phi lambda is lambda to the power alpha minus 1. Okay. And if you restrict your alpha in the interval 0, 1, you can see that the first derivative is negative. That is, the alpha minus 1 into lambda to the power alpha minus 2, that is negative. Now the second derivative, alpha minus 1, alpha minus 2, lambda to the power alpha minus 3, that is always positive, and so on. So the first derivative is negative, second derivative is positive, and so on. So it is an example of a function which is completely monotone. Second one, if you take e to the power minus lambda to the power alpha, where I am restricting alpha in the interval 0 to 1, and lambda positive, in this case also you can take the derivative and you can see that the nature of the derivative is the first derivative is negative, second derivative is positive, third derivative is negative, and so on. And you can see that that function is nothing but it is the Laplace transform of the well-known function distribution, that is, which we will call in the literature as the positive stable distribution. The stable distribution that is concentrated on the positive half, or which is in fact named as the positive stable law. So it is in fact the Laplace transform of the positive stable law. And you can see that in the very special case, that is whenever alpha equal to 1, you can see that it is simply the Laplace transform, it is nothing but e raised to minus lambda, which is nothing but the Laplace transform corresponding to a degenerate law. And now let me take it as the phi lambda equal to 1 by 1 plus lambda. Lambda greater than 0, you can see that it has again the property that the first derivative is negative, second derivative is positive, third derivative is negative, and so on. And so that is completely monotone, and that phi lambda is in fact well known, the Laplace transform of the well known unit exponential distribution. Unit exponential distribution. Of course, one may be able to extend it. One may be able to extend it to include the shape and scale parameters if needed. And you can see that the corresponding Laplace transform in that case also is in fact completely monotone. And another one is phi lambda is equal to 1 by 1 plus lambda greater than 0. That is again is an example of a completely monotone function. Now, for the properties and applications of completely monotone functions, if one is interested, he may refer to the well-known book the classical book by Berthenfrost on the potential theory of locally compact abelian groups. So this has describes, in fact, the applications of these, the properties and the applications of these completely monotone functions. And another one is the well-known book by Feller, that is the introduction to probability theory and its applications. In the second volume, there is a separate chapter discussing the applications of Laplace transforms, where he in fact uses the completely monotone functions to define certain distributions and so on. And as we know that the Laplace transform is defined as phi lambda is equal to integral 0 to infinity e to the power minus lambda x dfx, where lambda you can take it, in general you can, it can be a complex valued function also. So you can take your real part of lambda. In that case, you can take it as the real part of lambda is greater than 0. Okay. Okay. So, and x greater than 0. And you can see that there exists a one-one correspondence between f and phi. So, which means that there exists a uniqueness between the phi and f, which means that given a phi, there exists a unique f, and conversely. And the next one is in fact the well-known result, which is in fact, which plays a key role in our discussion today. So, a function phi on 0 in infinity is the Laplace transform of a probability distribution if and only if it is completely monotone and phi 0 equal to 1. So, if you have a function which is completely monotone and its value at 0 is 1, then there corresponds to a unique distribution for which this phi is the Laplace transform. So, identifying the function, the corresponding the distribution function from phi, we may be able to define the corresponding probability distribution. And or also you may be able to use the inversion formula, which is given here. That is, if phi lambda is this one, that is integral 0 to infinity e to the power minus lambda x f dx, where I am following in fact the notation by Feller volume 2 itself, where f is nothing but it is the usually in fact the distribution function, and it follow holds for all lambda greater than 0, then at all points of continuity we may be able to find the function f from the Laplace transform of phi lambda using the inversion formula, which is given here. Sigma limit tendence to infinity sigma over n minus n to the power by n factorial phi n of a. So using that, one may be able to invert our phi and find the corresponding Laplace transform. So this is in fact that is the one that I have already told. And the completely monotone functions have some properties. That is, if phi and psi are completely monotone, then their product is also always completely monotone. And if, let me consider the derivative of phi, or I may consider functions with which is in fact the negation of the completely monotone functions, or in fact which is defined through the formula minus 1 to the power n d to the power n by d lambda to the power n phi lambda is negative for n is equal to 1, 2, 3, etc. So, if you let me look at that. So, then what is the nature of the derivative? You can see that the nature of the derivative is the successive derivatives are the first derivative is positive, second derivative is negative, third derivative is positive, fourth derivative is negative, and so on. So that is in fact the nature of the successive derivatives. Whereas in our completely monotone functions case, it was negative, positive, and so on. So functions which satisfies this property, we will call it as functions with complete monotone derivative. And you can see that you can find a number of functions which has this property. For example, if you take your phi lambda is lambda to the power alpha, where 0 less than alpha less than equal to 1 and lambda greater than 0, then you will get this is equal. This is nothing but it is your. This is simply completely monotone. That is, you can see first derivative that is positive, second derivative automatically it is negative because it is nothing but alpha into alpha minus 1, lambda to the power alpha minus 2, and alpha minus 1 being negative, it is negative. And the third derivative, because it contains alpha minus 1, alpha minus 2, so that it is positive and so on. So based on this, so we have introduced the completely monotone functions and functions with the completely monotone derivative, and now we may now try to explain some results connecting with this functions with complete monotone derivative and completely monotone functions and individual functions also. So if phi is completely monotone and psi is a positive function with a positive function, positive Bernstein function. So which means that psi is a positive function with a complete monotone derivative. Bernstein functions are functions which has complete monotone derivative. So my phi is completely monotone and psi is a function with a CMD. So you can see that phi of C is completely monotone. If your phi is a completely monotone function and psi is a Bernstein function or psi is a function with a complete monotone derivative, then the compound function phi of psi. Here, in fact, it is, if you take simply your e raised to minus lambda, you can, and you take this one also, psi also, you can see that the e raised to minus psi, e raised to minus lambda is a complete monotone function, psi lambda is a Bernstein function. So this theorem tells that, this result tells that e raised to minus psi lambda is completely monotone. So these types of functions have applications in different areas, of which one is in fact in the case of branching process, where we will come across the equations of the sort beta lambda equal to phi lambda plus c minus c beta lambda. And so in that case, you can see that let phi be the Laplacian of a probability distribution f with expectation mu, and we can see that this equation has a unit root beta lambda less than or equal to 1, and beta is the Laplacian of a distribution if and only if this happens. And these are some of the properties. A completely monotone function is positive, decreasing, and convex. So it is always a positive function, it is decreasing, and it is a convex function. So being convexity, you may be able to expect infinite divisibility from it. The set of all completely monotone function is a convex cone containing the positive constant functions. So that also you may be able to prove it. And also the product of two completely monotone functions is again completely monotone. These are some of the basic properties of completely monotone functions. And in contrary to that, your Bernstein function or the CMD function, the function of the completely monotone derivative is positive. Naturally expects that it is to be increasing in cone. The structure of the convex cones of completely monotone functions are Bernstein functions, and the relationship between these cones resembles the structure of convex cones of positive definite and negative definite functions and the relative relation between these cones. So you may be able to find a resemblance between the convex cones described by these functions. And for a function f from 0 infinity to r, the following conditions are equivalent. It is a f is a Bernstein function or a function with a CMD. And f is greater than or equal to 0 and the function e raised to minus lambda t is c completely monotone for all t greater than 0. Now, let us look at a particular Laplace particular function So let me consider the function phi lambda equal to 1 by 1 plus lambda to the power alpha. So this is our main thrust in this today's discussion. So we are considering the Laplace transform. Phi alpha lambda equal to 1 by 1 plus lambda to the power alpha. And I have already shown that 1 by 1 plus lambda is completely monotone. That is, its first derivative is negative, second derivative is positive, third derivative is negative, and so on. And I have another function, lambda to the alpha, where I am restricting my alpha in the interval 0 to 1. So that in that case, the first derivative is positive, second derivative is negative, third derivative is positive, and so on. And automatically, my lambda to the power alpha is a function with complete monotone derivative, or I will call it as CMD. In short, we will call it as CMD, which means that the completely functions with complete monotone derivative, or the first derivative is positive, second derivative is negative, and so on. And the completely monotone functions are in short written as CM, where the first derivative is negative, second derivative is positive, and so on. And you just look at your phi alpha of 0. Phi alpha of 0 is in fact equal to 1. That's clear. And we have said that if phi is, we have in the earlier case, we have seen a result. That is, if phi is completely monotone, and psi is a function with a complete monotone derivative, or psi is a positive function with positive Bernstein function, then phi of C is completely monotone. So if I may, therefore, you may have using that result, phi alpha lambda being a compound of 1 by lambda to the power alpha. So you will get, if you take phi lambda as 1 by lambda and psi lambda is lambda to the power alpha, then what is phi of psi lambda? It is 1 by 1 plus lambda to the power. So being that one, since phi has complete monotone, phi is completely monotone, and psi is a Bernstein function, and phi of psi should be completely monotone. So that your 1 by 1 plus lambda to the power alpha is completely monotone. With phi alpha 0, phi alpha 0 is equal to 1. So if these two conditions are satisfied, your phi alpha lambda, which is simply 1 by 1 plus lambda to the power alpha, is completely monotone, and phi alpha 0 is 1. Based on, hence, because of the well-known Bernstein theorem, phi alpha lambda is the Laplace transform of a probability distribution. Phi alpha lambda is the Laplace transform of a probability distribution for 0 less than alpha less than or equal to 1. And why I am restricting the parameter alpha to the interval 0 to 1? Because whenever if I am assuming that my alpha is greater than 1, then phi alpha lambda is no longer completely monotone. That is, the complete monotonicity is preserved only for the case alpha in the interval 0, 1. That is the open closed interval 0, 1. That's why we are restricting our alpha to the interval 0, 1. So you just look at your alpha equal to 1 case, then you may have the Laplace transform is 1 by 1 plus lambda. So what is it? The corresponding distribution is nothing, but we all know that it is like the unit exponential distribution. Now, what is the distribution which has the Laplace transform phi alpha lambda? So this was proved by Professor Arun Pillai in a paper which appeared in Annals of the Institute of Statistical Mathematics in the year 1990, where he established that the phi alpha lambda corresponded the distribution function corresponding to the Laplace transform phi alpha lambda is connected with the well-known Mittag-Leffler function or the Mittag-Leffler series or the Mittag-Leffler integral. And hence, he named the distribution which has the Laplace transform phi alpha lambda equal to 1 by 1 plus lambda to the power alpha as the Mittag-Leffler distribution.
Professor, you are left with 5 minutes.
Okay. So this is in fact the Mittag-Leffler function. In 1903, the Swedish mathematician Mittag-Leffler introduced the function E alpha Z, which is 1 by 2 pi I integral over C 2 to the power alpha minus 1 e to the power t by 2 to the power alpha minus z dt, where the path of integration C is a loop which starts at n set minus infinity and encircles the circular disk mod t less than or equal to z to the power 1 by alpha, and automatically you know that your E alpha is an entire function of order 1 by alpha. So this function is now called in the literature as the well-known Mittag-Leffler function. And by integrating that one, we can represent our E alpha Z as sigma over k is equal to 0 to infinity z to the power k by gamma 1 plus k alpha 1 plus alpha k. And this function, which now is known as the Mittag-Leffler function, has attained a prominent role in fractional calculus and also in dealing with the hydrological analysis of river flow data, and in financial mathematics in the analysis of stock exchange data. And in a paper which appeared by Veron and Koltulski in 1996 in the journal Physica, they have applied the Mittag-Leffler function in describing the cold relaxation phenomena. And it is, you can see that f alpha x, if I may take it as 1 minus of my E alpha minus x to the power alpha, E alpha z is given here, then 1 minus E alpha minus x to the power alpha is a distribution function. You can clearly prove that it is a distribution function. And if you invert that, it is nothing but it has the Laplace transform 1 by 1 plus t to the power alpha or lambda to the power alpha. The function which I was telling, the 1 by 1 plus lambda to the power alpha, the corresponding distribution function is nothing but it is f alpha x. And that is proved in Analysis of Institute of Mathematical Statistics, and this is and a number of results. We have proved a number of results after introducing that by Professor R.N. Pillai. We have done a lot of work on the structural aspects and its applications and inference on this distribution. So a random variable x on 0 infinity is called the Mittag-Leffler distribution if it has the distribution function given by this. And its density, it is clearly you may be able to differentiate that one, and the term differentiation is clearly possible. And you can see that the density function is this, and the Laplace transform is this, and you can see that alpha equal to 1, you will get the exponential distribution. And the same you may be able to put by taking alpha equal to 1 in your f alpha. Then you will get f1x. f1x is nothing but it is the series sigma k is equal to 1 to infinity minus 1 to the k minus 1 x raised to k by gamma 1 plus k. So that is minus 1 to the power k minus 1 x raised to k by k factorial, which is nothing but 1 minus e raised to minus x, which is in fact the distribution function of unit exponential random variable. So, or in other words, the Mittag-Leffler distribution can be viewed as a generalization of the exponential distribution, and these are the graphical plots, and you can of the distribution function, which in fact seems from the graph it is clear that as alpha decreases from 1 to 0, the tails becomes more and more thicker, and for the varying values of alpha, you may be able to model the heavy tail phenomena successfully using this distribution. And it has a lot of properties. That is, it has complete monotone derivative, and its fractional moments are found by Lin 1998 in a paper appeared in Journal of Statistical Planning and Inference, and it is normally attracted to stable law. And the generalizations of the Mittag distributions to the geometrically inferior distribution case was attended by Fujita in 1993. And Lin, in fact, characterized the Mittag distributions using the spectrum of infinitely dimensional distributions in a paper which is in the Australian and New Zealand.
Kindly wind up, sir.
Okay. And these are some other areas. And this is a paper which I have done on modeling overflow data, which appeared in mathematical and computer modeling and so on. And these are some of its properties and so on. And this is useful in various areas. And let me conclude. These are, so you may be able to develop it, the corresponding stochastic process, and there's a further extension to semi-metallic case is possible. So these are the references. So this is the end. Thank you very much.
Thank you very much, Professor K. Jayakumar, for such a elaborate and nice presentation on completely monotone functions and their role in the study of distributions. You have, with quite detail, shown how these procedures can lead to the finding of many distributions, which are also very much practically useful. So thank you very much. And now the floor is open for the questions from the audiences. You may please raise your hand, unmute yourself, and you can ask your queries, feedback, suggestions, whatever. Thank you. So, any of the participants, you may please unmute yourself and ask the questions, if any. Okay, if not now, then you can connect with the professor afterwards, and let us thank him with a lot applaud and the clapping from all of us for presenting such a complicated subject in such a short time, in such a simple words, and with the help of simple equations and procedures. So thank you very much, sir. Now, because of the paucity of the time, let us move to the next speaker, Professor Jayadevan. Yes, thank you so much, sir. Professor Jayadevan Sridharan from Gulf Medical University, Ajman, United Arab Emirates. And Professor Jayadevan is going to speak on estimating MCQ pass rates through blind guessing using the binomial distribution, implications of option numbers on discrimination and assessment validity. So you are welcome, sir, and you are requested to please share your talk with all of us. Thank you. And your time is also, sir, 30 minutes. Thank you.
Good afternoon. Is my screen visible?
Yes, sir. It is visible.
Okay, great. Thank you, madam. Thank you for your introduction. And thank you, Professor Satish. And happy Statistics Day to you all. And in this Statistics Day, today morning I saw one video. It says about statistics. And statistics is using all field, including the physics, the statistics, economics, agriculture, engineering, all the field. But no mention about the education, especially the assessment part. What I'm going to say today is about how statistics is helping in the assessment of the evaluation, student evaluation. So here, first of all, before going to go, I'll say something about the assessment part. So we all know about different type of assessment, which include we will go for multiple choice questions, short answer essay questions, and different type of questions. So all these places, what is happening? Statistics also play a major role. First of all, to see the reliability of the assessment tool, and also to find the validity of the tool as well. Here, the statistics usually help to identify how the trends are going with respect to the difficulty or discrimination of the part. And we can take the decision based on the statistics as well. As I mentioned, coming to the assessment part, we have the MCQs, SAQs, and short SAQ and long essays as well, and assessments, assignment as well, portfolios, the presentations, Viva, objective structured clinical examination. So here, so I'm working in a medical university. That's why now I mentioned about the clinical examination and the skill-based evaluation. Then if you think about different type of things are there, all the places, statistics has some role as well. So here, this particular, the lecture, I'm going to take only about the MCQ part. How statistics is helping in developing the MCQ and how it is helping to see how the question what you are developed is actually the reliable or valid as well. Coming to the MCQ, why we are interested in MCQ? There are many advantages are there with respect to MCQs. Actually, it's the first one, the major one, what you can say is objective score. So you have only two options, yes, correct or wrong. So it's objective answering, but it's not happening in the short essay question or the long essay question as well. Also efficient to assess the large group. If you have a big group, maybe 100 or 200 students, for the examiner, if MCQ means easy to validate, easy to evaluate. Now, many these softwares are available like ExamSoft. If you put in the ExamSoft, the evaluation, it's the software itself will evaluate and they will get the mark as well. And if you go to a SAQ or a long or short essay question, the examiners are supposed to evaluate the assess the thing as well. And the third thing what you can see is covers the broad content as well. Which is different content, we can put different type of questions as well. So the other one is reliable and reproducible as well. Then time saving. So as I already mentioned, even for the students as well as the examiners, is saving the time as well. Then we can think about different higher order thinking also. You can see, maybe if you think about MCQ question, what you can see, some of the questions are, recall questions, some are skill-based questions, some are analysis, some are again interpretation. So here in MCQ, some question we can think about the higher order questions also we can put. Then the MCQs also will help in how we can go for a system thinking, the overall what is happening. That type of questions also we can put in the MCQs. And the next thing is the quantitative analysis is possible. If you have a list of questions after the assessment, you can see whether the questions what you put is sufficiently reliable or valid. So I'm going to tell a little bit more about that later. Then the other thing is immediate feedback. As I mentioned, the softwares are there. The software will give the feedback whether it is right or wrong. And if it is wrong, maybe the examiners or the faculty can give feedback on why it is wrong, why the other one is right. While coming to the MCQ evaluation, we have to think about four aspects. First one is what is called difficulty index. Second one is what is called discrimination index. Then the other one is what is called KR2021 and distractor analysis as well. So we are going to learn this, in detail about all these aspects of statistics. I'm going to discuss a little bit about all these all aspects. First of all, let's see what is difficulty index. So difficulty index is if you're putting one question, one group of questions, or a particular question, if you put how many students correctly answer that question among the total student, that is what is called, that is type of probability what you can say is the difficulty index. Usually what we say, the ideal range is from 0.3 to 0.7. If it is between 3, what you can say, sufficient difficulty index is there with respect to that MCQ. Similarly, for if you have a very high or low values, indicate item maybe too easy or too hard as well. Usually, any MCQ, what we are looking for is to see the difficulty sufficiently the moderate level as well. Then, next one what I discussed is about a discrimination index. Difficulty, and the next one is discrimination. What is the discrimination means? It's a statistical measure that indicates how well an item differentiate between high-performing students and low-performing students. In any class, if you take 3 groups, you can see low performance, high performance, and middle performance students. So, among how we are discriminating with respect to the low performing students and high performing students, what we can see is the discrimination. And why we do that to evaluate the quality of the question, whether it is effectively distinguished between who understood the content and those who do not. So, for that, we usually measure for the discrimination index as well. Now, how we calculate the discrimination? You can see here a formula, U minus L divided by N. So, what is U? Number of students in the upper group. So, here upper group, what you can see here, the upper 27, lower 27% and upper 27%. How to calculate this? You take the whole answers, arrange them, and you can then you can see the top 27% and the bottom 27% as well. Based on that, what is possible, we can calculate the discrimination index, right? So the discrimination index will say whether sufficient discrimination is there or not. You can see here, any value more than 0.4, what you say, excellent discrimination is there. And it's between 0.30 and 39, we say good discrimination. And 20 to 29, what we say is acceptable. And if it is less than 0.20, it's poor. And sometimes you get the negative values. It means the question need revision as well. Now, the third one, what you're going to say is a distractor. A distractor is an incorrect option. In MCQ, we put a 4 options there. One is the correct answer, the remaining three are distractors. The distractors, students who, among the design in distract students who do not know the correct answer. Some students, they come with no prior knowledge. They come for guessing. So what is the purpose of this? To test the depth, the in-depth, the knowledge students' understanding of the thing. The distractor will help you. So even to the quality of check, a good distractor is possible and chosen by the lower performing students, but not by the high performing students. The distractor usually goes for the selection, mostly for the low performing students, and not for the high performing students. Now, the other one is non-functional distractors. Sometimes you put some distractors that's non-functional. What does it mean? The students are not taking that, which means it's entirely different from the remaining options as well. So that's non-functioning distractors. So distractor efficacy, what you can say, effective distractors attract low scores, and distractors selected by less than 5% may be considered as non-functional. If in the question, 100 students are marking the answer, if the one particular answer less than 5% is selected, means that is not a functional distractor. What you can see is a non-functional distractor. So poor distractor reduces discrimination index. So we learned about the discrimination index as well. So all the four aspects are there. If distractor is not that good, the discrimination index will reduce as well. So ideal 3-function distractor usually what we take when we go for a 4-option MCQ. Now we go to the KR20 and KR21. What you can say is the KR20 and 21 are used to estimate internal consistency of the assessment made up of using a dichotomous item. So MCQ usually we can say dichotomous item because one correct answer and the remaining are the wrong answers. Then KR20 measures the internal consistency dichotomy, and 21 also is almost same, but some difference is there that we'll see in the next slide. You can see here, what the difference between the two. So item difficulty, usually actual difficulty, we go for the KR20, and for the KR21, we use equal difficulty. Then more accurate we use 20 and less accurate for the 21. And detail item level we take from the KR20 and only average score we go for the 21 as well. So actually what we can say KR20 is better than KR21 as well. We'll see how to calculate KR20 from the formula I can see here. KR20 is equal to K divided by K minus 1 into 1 minus sigma PI QA divided by the variance. What you can say, K is the total number of items. How many questions are there in the assessment tool? Then the proportion of students who answered the item I correctly. Then Q as usually it is 1 minus PI. Then you have to take the product and the summation. Then you take the variance of the scores. If you put, you'll get a value for the KR20. Then how you interpret the KR20? If it is more than 9.9, what we can say is excellent. And if it is between 0.80 and 8.9, what we can say is good reliability. Between 0.7 and 0.79 is acceptable, and 0.6 to 0.609 is questionable, need the improvement. If it is less than 0.6, then poor. Test may be maybe not that good as well. Now, so why this is actually the introduction what I'm trying to say about this particular the study. Now, what is the objective of this study? This study is the aim to determine the likelihood of passing an MCQ-based examination purely through blind guessing. A person is blind guessing what is the probability of passing the exam, and also to assess how this probability varies based on the number of answer choice per questions. So why this idea? Because recently, so the academic accreditation team, they came for the inspection. They said about some group of students, their exams are most of the students got more than 90% mark. They are wondering why many students are getting more than 90% mark. They suggested to increase the number of options. So right now what we do, the number of options is 3 for MCQ question. What their suggestion is to go for 5 instead of 4. So then I thought, what benefit we are getting if you increase the number of options from 4 to 5? That is the reason why this study is conducted. This study is a conducted simulation-based design using the binomial probability approach. So as I mentioned, to estimate the probability of passing for a multiple choice questions using the blind guessing. So I put here, if there is 3 option, what will happen? 4 option, what will happen? And 5 option also, what will happen? So we know if there is a 3 option, the probability of each question, the passing probability is 0.33. For the 4 option, it's 0.25, and 5 option, it is 0.2. So you can see their argument, the academic accreditation agency, what they're trying to say is, if you increase the option, the probability of each question, the passing, the probability will be reduced through the blind guessing. But so when we go for a examination, it's not possible to say using a single question is to go for a overall. That otherwise, what I can say as a system as a whole, we have to think about. So here, as I mentioned, so what we can say, this follows a binomial distribution with the correct answer and the wrong answer. So from here, you can see a simulation. So I considered for 60 questions. For an examination, 60 questions are there. So I'm trying to say each question is 3 option, 4 option, and 5 option. So I'm setting here the passing minimum is 60%, 65%, and 70% as well. What will happen to the probability? That's what I'm trying to say. So if 60% means the student should get 36 out of 60, and for 65, 39 correct answer, and 70 means 42 correct answer as well. Now I'm trying to say, what is the probability of getting 36 correct answer, 39 correct answer, and 42 correct answer if the student has no prior knowledge and absolutely he or she is going to go for a blind guessing? So here the assumption is equal difficulty for all question put in the examination. So that's what I said, test takers are no prior knowledge. So this is another assumption, no prior knowledge and equal difficulty as well. Now, So as I mentioned, so we have, for that we'll go for the cumulative probability. So I said, what is the each question? What is the probability of each? From 0 to 60? What is the probability I'm trying to calculate? So as you know, is the probability distribution. Based on that, probability of success is equal to each question. Already we mentioned it's for 0.25 if there is 4 option question, and if it is 3 option means 0.33, and 5 options 0.2 as well. This already mentioned. So now we know 3 options. So the assumption, higher probability of passing by guessing. This one of the assumption is, if it is only 3 options, the probability passing is high when you go for the guessing. And if it is 4, is balanced, means between the 2. And if it is 5, very low guessing. The chance for passing is very low compared to the other 2. But is it really right or wrong? And too many options can reduce the discrimination. So another thing, if you go for too many options, what will happen? The discrimination index will reduce because you may not have sufficient option to put, so which will affect the discrimination as well. Now, what is happening with respect to the probability? You can see here. So this is individual questions. If you go for probability of 0.33, this 0.33, this many questions get correct. Right, around 20, what we can say, and 2.5 means the highest is here around 12 or something, and 0.2 maybe less than that. So this is the way it's going. Now we see here, what is happening, the cumulative frequency. You can see here, the probability, this is the number of questions. So if you reach number 30, what is happening? Probability is almost equal to 0. So what is happening? Irrespective of whether it is 3 option or 4 option or 5 option, the pass chance is 0. No probability of passing if we consider the exam as a whole. So my point is no need to go for the 4 option, 5 option MCQ. It's better to keep 4 option, which will increase the discrimination of the exam as well. So coming to this discussion. If you want to go for a MCQ assessment, it's always better to go for not the increase more number of options, keep the number of options 4. 3 also we can use, but the balance between the 2, it is better to go for 4. In that 4 also, the student is not going to pass the exam with blind guessing. Blind guessing if the student is not having prior knowledge about the particular subject. Now, another thing we can see coming to this part. So 5 plus option. What is happening actually? If you are increasing the number of options, ultimately what is happening is the discrimination. The discrimination will be different. And distractor, if you take the distractor, maybe easily we can rule out 1 or 2 distractors. And then again, what is happening? For example, 5 option MCQ, 2 distractors easily we can rule out. Then what will happen? The other 3 is there. Again, what is happening? The probability is 0.33. So if the 5 option is there, the probability of guessing is again 0.33. So in that case, if you increase the things, that's not a good option to go for reducing the or increasing the reliability of the test tool. This is what I have written here. Student can eliminate. We can rule out 2 out of 4 options. Then what happens? The probability is 50% as well. So that is not a good option to increase the number of options for an MCQ. So the best thing is what we should do is we should keep the proper difficulty and proper discrimination and disaster index. Then the question will be okay. Now, in conclusion, what I want to say is 4 options. Better to go for the 4 option MCQ, which will actually help in assessing the student knowledge about not only the lower level knowledge, even the higher level knowledge also we can test using this 4 option MCQ questions. Thank you so much. Thank you for listening.
Thank you so much, Professor, for presenting such an interesting and such a daily kind of our experience, especially those who are in teaching. We face these difficulties as many people, the administrators, managers, and the vice chancellors, they are asking to go for MCQs because that helps in expediting the results. So
Yes.
now these are the things which we can keep in mind, because usually it is thought that increasing the more options would make it more difficult. But as you have shown that it is not so, always depending upon the distractors and other options difficulty level, we can see that it is going to be different. So, thank you very much for such an interesting talk from the point of view of especially the educators. Now, the forum is open for the questions, feedbacks, or queries, if any. So, our participants and the guests are requested to unmute themselves, and you can raise your query, or you can suggest, or you can ask if there is anything. So, if not, then let us thank the speaker for such
Okay,
a
by the way, ma'am, I want to thank you as well, so for your words. Moreover, this is what is happening. They come and say without any proper evidence, they come and say that increase that thing, reduce that thing, this thing. So we have to go for the evidence. All these things, we need sufficient evidence to change the thing. That is not happening here. That is why I thought most of my research on medical only. So first time I thought I'll go for the educational research and see how we can defend this concept.
So this was very, very interesting. Actually, I was just wondering, all these measures and indexes can be obtained only after the MCQs have been attempted by the students. But while preparing the questions, is there any way so that the teachers can also a little bit guess, like these questions they should put into the paper and these should be avoided? So, what would you suggest? What could be the options?
Yes, ma'am. The options are there. First of all, we need a committee actually. So what actually we do here, the faculty will put the question. The committee will sit together and analyze the content of the thing, whether sufficient discrimination is there or not. The content validation is happening before the examination. Then once the content the validation is there, then we go for the exam. That exam will calculate the difficulty index and the discrimination index and KR20 as well. Then the question is proper, then move to the bank. Then what happens next time we can take from the bank. That question is already validated.
Okay. Thank you so very much for giving your valuable answers and inputs. And if there are any other questions from any of the participants, have they thought of anything they want to ask, they are most welcome. In the meantime, I would just like to take the opportunity to thank and express our gratefulness to our wonderful friend, colleague, researcher, Professor Satish Kumarji, who has been tirelessly conducting these webinars of international level each year, and all the colleagues and his the team, wonderful team, who have been supporting him. So we are really grateful to you, sir, for giving us the opportunity to come together and share our experiences, opinions, thoughts, our researches. And you have really been wonderful organizers, I must say. Thank you very much. Thank you.
Thank you, Dr. Satish again.
Thank you, Jay. Thank you. In fact, I am very much thankful to both the speakers of this session, the excellent speakers, both Professor Jayakumar and Professor Dede, for their excellent talks, as well as Professor Sheila Mishra for chairing the session, making it a very nice and very attractive session. Thank you so much, madam. Thank you. And
Thank you so much. Thank you very much. So now we can leave for the next session. Or any other hall, if anyone wants to join, they can. Thank you so much. Yes, sir. You want to add something?
No problem, madam. The next session will begin at 4:10. Yeah, here. So now we have 20 minutes time for
Yes,
debate.
about the break.
Yeah, we can take a, in fact, whether if
On break.
interaction or anything like, no problem, we can utilize.
Okay.
And
And
other to join the other parallel sessions. Two parallel sessions are going on.
yes.
One is best paper presentation awards, and the other is the contributory presentation.
Mhm. Okay. Thank you very much. Thank you all the participants and everyone.
Jadi, hello. മെസ്സേജ് ഞാൻ കട്ട് ചെയ്ത് അല്ലേ പുള്ളി പാർട്ടിസിപ്പന്റ് ആണോ? ക്വസ്റ്റ്യൻ അല്ലേ ചോദിക്കുന്നുണ്ടോ? ഇല്ലല്ലോ. ക്വസ്റ്റ്യൻ അല്ലേ ചോദിക്കുന്നുണ്ടോ? ഇല്ലല്ലോ. ടെസ്റ്റ് പേപ്പറിലെ എക്സ്പേർട്സ് മാത്രം ക്വസ്റ്റ്യൻ ചോദിക്കാറുണ്ട്. ഈ കഴിഞ്ഞ പ്രാവശ്യം ഈ പുള്ളി എന്താണ് ഈ പുള്ളി പ്രസന്റേഷൻ ഉണ്ടായിരുന്നു. അത് കഴിഞ്ഞിട്ട് വേറൊരാള് ഇതിനൊക്കെ കയറി ചോദിക്കുന്നുണ്ടായിരുന്നു. അങ്ങനെ ഒരു ഇംപ്രഷൻ കൊടുക്കാൻ വേണ്ടി ചോദിച്ചാൽ ശരി. ഓക്കെ. കഴിഞ്ഞ പ്രാവശ്യം ഉണ്ടായിരുന്നു. എനിക്ക് പേര് ഓർമ്മയില്ല.
Nandana?
Yes, sir.
Okay. Professor Bani? Okay.
Namaskar, sir. How are you?
Yeah. Now let us start. Professor Victor is here. And Nandana, please introduce you and fill it in.
Okay, sir. Good evening, everyone. It gives me great pleasure to welcome you all to the 7th technical session of the 10th International Webinar on Recent Trends in Statistical Theory and Application. We are honored to have with us as the chair of this session Professor K.S. Banu, Institute of Science, Nagpur, Maharashtra. Professor K.S. Banu specializes in reliability modeling and optimization, specifically in the context of hardware, software systems, and related fields. She has also explored the application of the simulated annealing technique for optimization problems. Ma'am, we are grateful for your guidance and leadership in this session. It is also a distinct privilege to welcome our keynote speakers, both of whom are leading voices in the field of statistics. First, we have Professor Vijay, Madras University, India. His topics of research have been probability, stochastic processes, operation research, differential equations, and supply chain management. He will be delivering the keynote address titled Stochastic Dynamics and Passage Times for Diffusion Approximation. Professor, we are delighted to have you with us. Next, we are honored to welcome Professor K.K. Jose, Mahatma Gandhi University, Kerala. Professor K.K. Jose specializes in statistics with a focus on statistical modeling, stochastic processes, time series modeling, multivariate statistical methods, design of experiments, statistical inferences, etc. He will be delivering the keynote address titled on non-Gaussian autoregressive time series modeling a redesign. Professor, we are delighted to have you with us. We are privileged to have both of them with us today. With that, I now invite Professor K.S. Banu to take the session forward. Over to you, ma'am.
Thank you, Nandana, for the brief introduction of all the speakers. It gives me great pleasure here to be attending this conference once again. Thank you, Dr. Satish Kumar, for inviting us. And a happy Statistics Day to all the statisticians here, veterans and budding statisticians. The first speaker for today is Professor Vittal. So you have approximately 30 minutes for your talk. I'll just briefly introduce, though Nandana has already given a small introduction, I'll add to that. Professor Vittal is a postgraduate professor in mathematics at Ramakrishna Mission Vivekananda College, Chennai. He retired as the principal of the college in 1996. His vast experience in teaching includes as a visiting professor at Professor Vittal is a visiting professor in the Department of Statistics, University of Madras, Institute of Chartered Accountants of India, Chennai, the Institute of Technology and Management, Chennai, National Management School, Chennai, and Research Guide in Management Science in BITS, Pilani. He has over 30 research papers in reputed international and national journals and has guided a number of students for MPhil and PhD. He is a fellow of Tamil Nadu Academy of Sciences. His topics of research have been probability, stochastic processes, OR, differential equations, and supply chain management. In addition, he has authored 26 books in mathematics, statistics, and operations research. With this vast academic knowledge, we invite Professor Vittal to deliver his lecture in invited talk today. Over to you, Professor. Dr. Vittal. Hello, Dr. Vittal, are you audible? Is my voice audible to you? You can present your work, sir.
Yeah, he's here in the.
Professor Vittal, sir.
So unmute Professor Vittal, unmute your mic and. Yeah, he's probably the network issues or any technical. Yeah, unmute Professor, and also you can open your camera.
He's perhaps not able to unmute.
He has not in the list at present because I think he.
In that case, allow other speakers.
Yeah.
In that case, allow other speaker. When he comes, you will speak.
Yeah. Should we start?
All the other speakers.
Would we invite those, sir?
Yes, no problem. I'm ready here.
Yeah.
Even then, yeah. In case he join immediately, can continue with him. Otherwise, it's better to pause.
Let us invite Professor Jose, our next speaker, till Professor Vittal joins us. I take this opportunity, sir, to welcome you to this session. And I was very impressed by your biodata that was sent to me. I'll just briefly introduce you to the audience. It gives me great pleasure to introduce Dr. K. Jose, an eminent statistician, an academician with over 40 years of distinguished service in teaching, research, and administration. He is currently the Honorary Director of the School of Mathematics and Statistics and School of Data Analytics at Mahatma Gandhi University, Kottayam, Kerala. He has held prestigious positions including Principal of St. Thomas College, Pala, Professor and Head of the Department of Statistics at the Central University of Rajasthan, and Honorary President of Kerala Statistical Institute. He has guided 25 PhD scholars, published over 150 research papers in reputed journals, authored 5 research-level books, and completed 6 research projects funded by UGC, DST, and MOSPI. His areas of expertise include statistical modeling, stochastic processes, time series modeling, biostatistics, epidemiology, reliability analysis, and industrial quality control. He has been a recipient of several prestigious awards, including SB Award for Best College Teacher in Kerala, AIACHE Award for Most Innovative Teacher, Professor P.V. Sukhatme Award, Sam Higginbotham Award for Best College Principal in India, and FSMS Fellowship for contribution to biostatistics. He has been elected member of the International Statistical. He is an elected member of the International Statistical Institute, Netherlands, fellow of the Royal Statistical Society, UK, and member of various statistical societies. He has been an invited speaker and resource person at over 150 conferences and workshops with visits to countries like Portugal, Netherlands, Ireland, UK, Singapore, and China. He has edited the Stars International Journal. He was the executive editor of Journal of Kerala Statistical Association and reviewer for journals published by Wiley, Springer, elsewhere, etc. Apart from all this, he has organized over 200 quiz programs and seminars to popularize statistics in Kerala and actively promoted social service and NSS activities. Dr. Joe's career is marked by excellence in teaching, research, and leadership, making significant contributions to the field of statistics and biostatistics. With such an impressive background and academic biodata, it's a pleasure, sir, to have you here. And I invite you to deliver your lecture today.
Thank you, madam. Thank you, madam.
1620.
Yes, I will share my slides.
So you have roughly 30 minutes. We start at 1620.
Okay. I think it is coming. It's not coming. It's visible? Not the full screen is not coming. That is what I looking for.
Visible?
Yeah, it's visible, but
that means put the full screen.
it's not, the full screen is not visible, but the slides are visible.
Yes. Oh, okay. So today my talk is on. So but the slides are not moving.
Oh,
Problems.
it's moving?
Okay.
It's moving now. From beginning,
So okay. So the topic is largely time series modeling, and today I will be starting with the introduction. Time series, as you all know, it's a realization of stochastic process. It is a sequence of chronologically arranged observed values of a process, like atmospheric temperature, price of a commodity, sales, exchange rate, currencies, etc. Then it was actually Yule who made a systematic study on time series analysis, starting with the analysis of Wolf's sunspot data. And Box and Jenkins, 1970, had made systematic study and made it popular with their ARIMA models and ARMA models. And there are many nonlinear time series also developed by Subbarao and others, like the bilinear time series model and so on. So the pioneer work, non-Gaussian autoregressive time series modeling was done by Gower and Lewis in a 1980 paper. And they introduced the exponential autoregressive models. And with that, actually a new era of non-Gaussian time series modeling has opened up. Lawrence, 1978, considered autoregressive models with exponential and Laplace and gamma marginals. And further, they have developed some extensions of these exponential models to have the new exponential autoregressive models. So that way, they have done wonderful work in this area. My slides are not moving very well. So now I will be coming to. Okay.
To stop sharing and start sharing once again.
What?
I think it's better to share it once again. Stop sharing, and if it is not moving.
It is moving now, but as I expected. So now I will be coming to
It is moving.
exponential AR1 models. Maybe because of this net connection also. Exponential autoregressive models introduced by Gower and Lewis. they considered the first order recursive model of the form xn equal to rho xn minus 1 plus epsilon n. And they considered the form of innovation sequence, assuming that this is a stationary model. So for that, actually, they have considered the Laplace transform, and using the Laplace transform, so they have obtained phi xt equal to lambda by lambda minus it. So which is actually giving phi epsilon t equal to lambda minus I rho t by lambda minus it, which will give you, which you can rewrite in the form rho plus 1 minus rho into lambda by lambda minus it. And that actually gives you an idea about the structure of the innovation. So the innovation will be having a zero component with probability rho. And it is otherwise it is exponentially distributed with probability 1 minus rho. So this actually leads to something like a non-linear model, that is xn is equal to rho xn minus 1 with the probability rho, and rho xn minus 1 plus en with the probability 1 minus rho, which is eventually a non-linear model. So even though we have started with a linear model, it ends with a non-linear model of this type. That is actually one advantage and disadvantage, as far as you can say, of this time series model. So now we will be coming to the new exponential autoregressive model. So actually, Lawrence and Lewis found some difficulties with this model, with the original model, something like zero deficiency. So that they have considered xn equal to a new revised model, new exponential autoregressive model, given by the structure xn equal to epsilon n with the probability alpha, and rho xn minus 1 plus epsilon n with the probability 1 minus alpha. So this is actually referred to as the new exponential autoregressive model. So here actually this innovation epsilon n is having a significant important actually. So this is actually applicable in many cases. And when there are some catastrophes in the stock market, then certainly the innovation is actually taking place. When there are something like wars, etc. So the innovations will be having some, that is in stock markets, etc. This innovation will be making a significant role. So just as in many years we have been observing heavy rainfalls, heavy rains for 1 or 2 days in Chennai, in Mumbai, etc. So in such situations, this actually the innovation is actually taking place. So that is actually the problem, and that can be also modeled by using this type of models. Now we will be coming to random selfhood. Why the movie is not moving? So here in my laptop it is moving. Then we will be coming to the generalized random walk model. So this generalized random walk model is actually xn equal to epsilon n with the probability alpha, and xn minus 1 plus epsilon n with probability 1 minus alpha. These were actually considered by Jose and Pillai in 1993 paper. So usually our random walk model is actually xn equal to xn minus 1 plus epsilon n. But here we have considered epsilon n. So this is just a simple situation of the NEIR1 model. In the NEIR1 model, we are having epsilon with the probability alpha and AXN minus 1 plus epsilon n with the probability 1 minus alpha. But for financial situations, etc., this random walk model is preferred by economics actually. And this generalized random walk model is more realistic in such situations also. So that is actually the advantage. And for that actually, we can make use of self-decomposability and geometric. So this you can put in the form of geometric infinitesimality or self-decomposability also. decompressibility, we are actually considering epsilon and rho x and minus. Minimum this is actually rho x and minus. So this is actually corresponding to the minification model. So in a similar manner, you can have a maximal model that is instead of minimum, you consider maximum also. So that actually gives you max self-decompressibility, max random self-decompressibility. So this way, we can have different types of stochastic process, or we can have different types of time series models. Then we will be going to some other model that is actually called the product autoregression. So in the case of product autoregression, what you are having is xn is equal to xn minus 1 raised to alpha into epsilon n. And we are having count models. We are just having number of x, number of births, etc. So which are actually also correlated. So in such situations, we are having binomial case, Poisson case. You can have integer valued time series models with binomial innovations, Poisson innovations, negative binomial, geometric, and so on. So Mackenzie, 1986, then Allosh and Alstead, 1987, then Allosh and Allosh, 1990, etc. developed such models. Even recently also, Nastic and Rishtik 2012, then Nastic et al. 2012, and so on. So there have been a good number of integer valued autoregressive time series models. And very recently, I have seen there are applications in risk analysis also, risk modeling also. So these integer valued time series models, that is actually something of very much importance. Then comes integer valued models for count data. So like so various types of count data, like a number of so deaths in insurance, so number of claims, then medical sciences, number of persons affected by a particular disease, then just like COVID, then contagious disease, etc. Then queuing systems, then in psychometric studies, in financial modeling, etc. This type of integer valued autoregressive time series models are of wide use actually. Now we will be coming to INAR, so integer valued autoregressive model of order 1. So here, If you just make a modification that is 1 minus phi is equal to g of 1 minus equation of the form, then you will be getting an equation of the form. Phi is equal to phi of beta is into phi of beta is into which resembles the sub-decomposability condition. It is actually easy to proceed with this model, this structure, just as in the case of additive model. So just a suitable thinning operator should be defined, only that much. So that is actually the advantage of this model. Then now we are going to a unification of these models. So how to bring Gaussian and non-Gaussian models into the same platform. So myself and my student Lishamor in 2008 and 2009 developed this unified framework for Gaussian and non-Gaussian time series models through the convolution of a Gaussian and non-Gaussian random variables. And in that case, under the convolution, we write x equal to z plus y, where z is normally distributed and y is any self-decomposable random variable. So it should be independent of z. Then we can have so this unified work will help us to have the characteristic function equal to phi xt into is equal to phi epsilon d into phi yt, where xn is actually in the autoregressive structure, first order autoregressive structure axn minus 1 plus epsilon, and then we will be getting similar expression, that is phi xn t is equal to, and that you can develop. Plus E1 minus E2 where E1 is exponentially distributed with the parameter alpha, and the eta distributed as exponentially with the parameter beta. So that E1 minus E2 will not be a symmetric Laplace, it will be an asymmetric Laplace. Along with that you are having convolution with Z, which is normal variable. So that will actually give you the normal Laplace distribution. And this you can apply in the case of or distribution that is for normal Laplace situation. So in the normal Laplace case, so you will be getting some results. So just like when gamma tends to 0, you will be getting asymmetric Laplace. When alpha tends to infinity, beta tends to infinity, you will be getting the normal distribution and so on. So that you will be getting the speciality then different situations we are considering. Then when alpha and beta are equal, we will be getting the symmetric Laplace, and so many modifications you can have. So it is actually a combination of both the cases. Actually, the graph of this distribution is actually this form. So it actually gives various possibilities. So symmetric situation, then positive situation, negative situations for different combinations of the parameter values. So that is the advantage with this. Then we can develop the model also that is actually having So we can have the generalized situation also, that is the generalized normal Laplace case. So in which case we are just considering gamma differences. Instead of exponential differences, we are considering gamma differences. And the characteristic function is here, and that will also give you something like x is distributed as normal plus gamma 1 minus gamma 2. So gamma difference is actually leading to generalized Laplace. So this is actually the generalized normal Laplace. So Z plus gamma 1 minus gamma 2, where gamma 1, gamma 2 are differently distributed, not they are independent gamma random variables with scalar parameters alpha and beta respectively. Hello? Hello?
No problem, boss. No problem, sir.
Can proceed. Okay. Okay, thank you. Then we will be having the structure. So the structure of the process, it can give either in this way. So this is actually one structure, that is the gamma difference you can write as P1 plus P2 alpha by alpha minus IT plus P3 into beta by beta plus IT. So the difference of gammas, beta, not gammas, you can think of as something in this form. And that will actually give you some simple structure. So that is actually the innovation structure you can give us Zn with the probability P1, Zn plus exponential with the probability P2, Zn minus exponential with the probability P3. So this is actually a very simple structure so that the random variables or the innovations can be generated easily. Then comes the structure. Then we have developed some models also, something the mean, variance, etc. we can obtain very easily. So the mean is actually in the very simple structure. So the mean, the expression for the mean and variance are actually some difficulty. So the expression for the mean and variance are in the closed form expressions. Expectation of epsilon is equal to 1 minus a into delta into nu plus 1 by alpha minus 1 by beta, and variance also can be obtained very easily, and cumulants also can be obtained very easily. So that is the advantage with this model. Then we can have the regression and variance. Regression also is very easy to obtain. So regression we can obtain, that can be used for prediction. Expectation of xn given xn minus 1, that is equal to x plus 1 minus a into delta into nu plus 1 by alpha minus 1 by beta. So that way predictions are also, forecasting also can be understood very easily. And the parameters can be estimated using a method which is familiar, which is similar to that of method of moments. So here we are considering cumulants. So using the cumulants we can estimate the parameters. Also the MLE method is possible, but it is a little bit difficult, only that much. So that way we can estimate the parameters in terms of the cumulants. Then we can have the generation of the Laplace, the process. The process can be very easily generated also. This is actually the algorithm for generating the process. And using this algorithm, we can develop the process, and we can generate the random variables, and we can generate the GNLR, generalized normal Laplace process. Then this you can write in terms of a short noise representation also. The engineers may be liking that one. So you can have a short noise representation of the form. So in this case, a short noise representation can be used to generate the gamma differences. Then epsilon and etc. with some probabilities P1, P2, etc. Pk. So that this can be extended to any number of lags, you can say. So n minus 1, n minus 2, etc. So k lags, where whatever be the value of k that is possible. So that is actually one advantage of this model. Then another possibility is actually you can have an ARMA structure also. ARMA 1-1 process also can be developed using this distribution, using this style. So generalized normal Laplace autoregressive model moving average of order 1-1. So this way we can have different structures, and moving average model of order 1 also you can obtain. We can have different generalizations. So this actually leads to various special cases, different cases, generalized normal alpha Laplace, normal alpha Laplace, generalized normal Laplace, normal Laplace, then Laplace situation, especially you can obtain. So all these models can be considered as special cases of the model which we have already developed. And then comes the log Laplace distribution. Log Laplace distribution means instead of Laplace, you take, so just like the log normal distribution, if y follows log normal, log Laplace, then so if x y equal to log x follows log Laplace, then we say x follows the log Laplace distribution. So in that case also you can develop the model. And then we have considered a little more generalization, that is actually
Sir, you'll have
using,
to wind up soon. Excuse me.
yes,
sir.
yes, yes, yes. So as a special case of product autoregression, so we can have the logarithm of, so that is if xn follows log normal actually. If x follows log normal, then we will be having the product autoregression structure. Then the that is yn follows logarithm of yn follows normal Laplace. Then we say xn is equal to logarithm of yn follows this product autoregressive model, and that is referred to as double Pareto log normal model. So this double Pareto log normal model is of use in financial situations and economic contexts. So this is actually the importance of this model. So all these are actually feasible to generate. That is actually the advantage of these models. Then comes the estimation of the parameters. So the parameters can be estimated using different methods. That is actually least square method, generalized method of moments, and the usual method of moments. Then ML is also conditional least squares method, etc. So using this, we have developed the estimates also, and that is actually feasible. So the estimates can be obtained, and here we are actually making use of the generalized method of moments. So there actually the method is actually developed by Seneta, and then the conditional least squares method. So in which case we are considering expectation, the difference between the expectation then the sum of squares. So xn minus conditional expectation of xn given xn minus 1. So that actually will lead to the estimates. Very easily, the estimates can also be obtained. We have closed form expressions for that. And this have been applied to model US dollar and Indian rupee, exchange rate of US model, dollar and Indian rupee from 2000 to 2007. And actually, this is the graph.
Professor Vittal, please don't share your screen right now.
Okay,
Sir, will wind up.
Okay, thank you. So that way, the parameters can be estimated, and this has been applied for inflation modeling also. And thank you all.
Thank you very much, sir, for giving us a deep insight on different types of models. A lot of study has been carried out by you and your students. Now I invite the audience to have some interaction with him. Anyone wants to question him, have some questions, we can take up one or two.
Okay.
Sir, what about the application part of these models?
Applications, actually, these are actually applied in financial modeling. Then we have already developed the financial models. Then these stock exchange rates, etc.
Area-specific models are there, or because you discussed many types of models.
Actually, the normal Laplace model in special we have developed. Then the double Pareto log normal model also we have developed. Okay. These are very good for modeling crop prices.
Share
then inflation
prices.
rate,
Inflation. Okay.
Inflation rates, etc.
I see.
And
in spite of the non-Gaussian structures, they work very well for share pricing.
Okay. This Hurliman actually says, Hurliman in a 2022 paper, he actually makes a comparison And he says our model is the best one. The normal Laplace model developed by
Oh,
Johann Lichamol Tommy is found to be the best one for modeling this inflation rate.
oh, I see. That's great.
Okay. Thank you.
Thank you very much, sir. On behalf of the organizing committee, I thank you once again for your excellent talk.
Yes, I also thank you, Professor, for chairing this session and your nice words. And I thank Professor Sadish Kumar also. So thank you, Professor Plani. Thank you.
Thank you, sir. It's been a pleasure. I invite our next speaker, Professor Vittal, to share his slides and deliver his talk. Professor Vittal.
I will.
Yeah. If you have started talking, we are not able to hear you. Professor Vittal.
Unmute your mic, Professor.
Please unmute your mic, sir. Professor Vittal, we are not able to.
In the mobile, there the bottom there is a mute and unmute mic. Or otherwise, we can share it from here, and you please speak from the using your mobile if it is difficult for you. Anyway, you have to unmute your mic, Professor. Or otherwise, you just left the group and join once again.
What I should do is unmute this.
Now we're okay.
Now we can hear you.
Are you able to hear me? What?
Yeah, Professor.
Yes. Now fine.
Fine. Now we can talk.
Fine, sir.
Fine. So, I thank Professor Satish Kumar and the organizers for giving me an opportunity to take part in this international conference. Now, the topic that I have chosen is that the first passage time and diffusion approximation out of it. Now, there are a number of papers which appeared in first passage time. Now, Lindbergh and Schuler have worked out a discrete version of the first passage time. Before going into this first passage time, I like to give, in the previous talk also someone asked about the application. I like to give the applications of this topic. One is, see, in insurance, the company question is going to raise the reserve and the reserve is going to exceed a fixed level. Then they discuss dividend and bonus and so on. Such types of problems are going to be discussed. But also in the insurance company, due to unforeseen claim, there might be a possibility that the company might also be ruined. So the question is either ruin or the excessive reserve which will enable the company to give dividend and bonus to the shareholder. The second application is a queuing theory. When customers come and arrive at a queuing station, there is a possibility that the customer, the server is always going to be busy. That means the full strength, or is going to be empty. They are basically going to be to the two variables. One of the neurobiology, there is a very wide application that our electrical impulses like inputs and output analysis, the neuron, they collide and they fire. Immediately, the information is taken to the brain cell and the action takes place. Now, so in dam model, storage model, can the dam become empty or can the dam become overflow? If it is overflow, what is the wastage of the dam? What is the content of the dam? These are the questions of interest in this problem. There are a number of other applications also to this problem is concerned. Now, first, I found out a paper on somewhere in 1986 or so, Lindbergh and Schuller, who considered the discrete version of this problem. And then Weiss and Lebo of Maryland considered the continuous version of this problem. Now, we look into the process of the problem that we are going to study. We come to the page 7 or 8. They are called the first passage time problem. Basically, they are called the first passage time problem. Can you move the slide, please? They are called the first passage time problem. Nagesh. See, I consider a model to study the first passage time as well as the first passage time moments of the process. Now, there are two methods, Kolmogor's forward equations and Kolmogor's backward equations. Each is great in its own place. I'm going to apply Kolmogor's backward equation and then apply Richard Bellman embedding technique to study about the barrier crossing problem. Satish Kumar, can you move the slides, please?
Professor, you can move from present from here and then move.
See,
don't worry. Please stop sharing. We can share from here and move.
Yeah. Kindly, please move page number 9.
Okay. You please stop the sharing.
Yes. And now you see, probably you might have got the discrete version of this problem. Px is equal to 0 and Pj equal to 1 by 2 e to the power of lambda minus 1 and so on. The continuous version of the problem, there are processes moving with upward jump and the backward jump. In the insurance company, due to unforeseen cases, claims come and therefore the company loses, it is the backward jump. The premium comes as the upward jump. Therefore, we have both forward and backward jump. And x is the initial level of the net result. Now, to study this passage time, the barrier corresponding to ruin, the barrier where reaches enormous amount, the company has to declare dividend shareholder. In order to discover the dynamics of the process, we decompose FXT. I define what FXT is. FXT stands for the probability density that starting from the level A, it is going to cross either the barrier x equal to 0 or x equal to a at time t. Now, it is a complicated analytical issue. To resolve this problem, we decompose FXT into two forms, F plus and F minus. F plus is that the initial start goes with a forward jump. F minus is that the initial start goes with a backward jump. Now, first we are going to consider FXT. Can you move to page number 9 and 10? Now you see, we are going to consider the initial jump. The initial jump can be, there is no jump at all in the initial interval of time t, or there is a jump which is below the upper level k, or there is a jump of enormous size, it might cross the upper level k also. The upper level k also. Now, we write the backward equation for the process. This is also called Kolmogor's backward equation, or we apply the embedding technique of Richard and Bellman. We apply the embedding technique of Richard, page number 8. We apply the embedding technique. Now you see, fx t plus dt is 1 minus mu dt. 1 minus mu dt. That means there is no jump at all, and therefore it remains at the same position. Or there is a jump of Poisson intensity mu, so that it comes to the position y by a transition from x to y. Or it makes a jump such that it has crossed the upper barrier at all. Now, we expand by Taylor's theory, and Satish Kumar, are you able to hear these things? Hello?
Sir, we are able to hear but not see the screen now.
The screen is
not seeing the screen.
Yeah.
Are you able to see the See,
some cone is,
see,
Professor?
see, I'm able to see the screen, but the screen is not moving with me.
Yeah, we can share it from here, Professor. Some call is coming to
See,
your
yeah, now I'm able to see that my son has helped. Now, now see, what is that f plus of x comma t is that there is no possibility of jump in the initial interval of time. So there is 1 minus mu t into et with the Poisson intensity, or there is a jump of with the intensity mu, and the process goes from fy dt into a jump size ay dy. Or it might have a jump which crosses the upper barrier itself, that is given by a delta function of the last time. Now we go into the expanding by Taylor series. We go into the diffusion equation, and the diffusion is we go into the integral differential equation, and that comes in the form, in this form, right? So once we have, I take the transition density in the simplest form, e to the power of lambda by 2 into e to the power of minus lambda into x minus y, transition x to y. So when you feed the transition density into the general integral differential equation and expand the Taylor's form, and you now get the differential equation of the process. And what I do that, I divide through it by e to the power of mu x, so that the right hand side is free from x, and we convert into an integral differential equation. Now what I do that, I differentiate totally with respect to x, and thereby convert this integral differential equation into an ordinary differential equation. Now what we obtained in 2.7 is an ordinary differential equation for a process starting with a jump in the forward direction. Now similarly we can go into an ordinary differential equation for a process with a negative jump. If we eliminate this f plus and f minus and totally arrive at an equation in f, we get a second order differential equation. Now you see it is given by 2.8. Second order differential equation, which can ultimately also given by 2.9, which is also ultimately given by 2.9. It is so simple a second order differential equation that with a constant coefficient, we can solve this differential equation and get the solution in terms of the arbitrary constant a and l, which are functions of capital N and the transform variable N. And the transform variable N. Now, the question is that having got the solution, general solution in terms of A and B for the differential equation, the question is now how to determine A and B. For this, we need the boundary condition. In order to get this boundary condition solved, what I do that, I go for the total differential equation, integral differential equation, without f plus and f minus, and therefore there might be a jump in the negative direction as well as the jump in the positive direction, and the jump might also cross the barrier either upward or downward, and that is given by 12.11. That is given by 12.11. Now what I do that, we substitute the solution, general solution into this equation for f plus. Ultimately, we are able to get two conditions, boundary conditions. All terms involving s will get cancelled. We yield two independent boundary conditions which are given by 12.13. Which are given by 12.13. So we can solve for A and B from these two equations and then ultimately find out the solution. Now why I have given in the form of the simplest differential equation is that we consider only a jump of both the direction. We can have a consider a jump in positive direction, a drift in a negative direction, and the dual prop. Or we can consider the situation wherein the jump would be of the exponential type. that is the content, the proportional, the reserve is going to be, the expenditure is going to be proportional to the reserve, and thereby we study the process of the company being prosperous or ruined. So we can manipulate this problem into a different type of density, different type of barrier, and different type of reserve level, and so on. Ultimately, we get a complicated differential equation and solve it, but this is the process by which you can arrive at a simple solution in terms of A and B. The solution ultimately comes in terms of hyperbolic function, and we determine A and B also. We also satisfy the condition f of x comma infinity is equal to f of x comma 0 equal to 1, which is the given in the this guy, you can see the solution in Cox and Miller also, that our ultimate verification holds good. Now, mean passage time. We can obtain, this is the, what we obtain is the transform of the density function. Now, when you determine the transform, we can derive the nth order differential equation for the moments. In fact, when you put n equal to 1, you get the mean passage time. We write down the nth order differential equation and also for n equal to 1 the mean passage time, and see that we get the mean passage time of crossing the barrier k or leaving the barrier x equal to 0 is given by the equation 2.19, is given by the equation 2.19. And the simplest situation, we also arrive at the mean passage time by 2.19. Now, Weiss and Szabo attempted this problem. What he did is that he is unable to apply the embedding condition of Richard Bellman, that is feeding the solution into the integral differential equation and then solving for the Broglie casting when the boundary is going to be crossed. So what he has defined that, look at the next one, what he did is that he derived, and now you see fxt is nothing but ux into u, he put in a separable form. So x and t are now dependable variable there, and we cannot split into separable, no question of independence come. That's a mistake Weiss and Szabo did in his paper which appeared in Physica in 1986 or so. But our technique not only gives the first passage time of crossing the barrier or even the probability of ruin, and also we are able to obtain the moment. Another question that we of interest that we are considering is that, which you have not considered by Weiss and Szabo, is that they have considered only absorbing barrier. That means either the process has to cross the barrier x equal to k, or the process has to be ruined at x equal to 0. Now we are introducing the question of reflecting barrier. What do we mean by reflecting barrier? I am not interested in any crossing of the upper barrier reserve, but I am very particular that the company should not be ruined. Therefore, upper barrier x equal to k mathematically cross any number of times. If we cross it, reset at the x equal to k, and then the process continues. Our time of interest is question to study whether the process x equal to 0 is going to be crossed. Now, we apply the same technique. And arrive at the solution of reflecting barrier problem of the probability of ruin. Again, the two conditions that we have to consider, A and B, are got by solving the integral differential equation and substituting. Now you can go into the solution. Now you see all the initial conditions are now satisfied, and we are able to see the fxt in a very nice form after simplification of that. Then we go into the diffusion approximation. What is basically diffusion approximation? And consider the jump process. Jump could be a mini magnitude. In diffusion, the jumps is going to be a small magnitude. Both upper and lower jumps are upward and backward jumps are taking place. So we are going to impose certain mathematical condition in order that we are going to apply the mathematical condition in order that the jump process is converted into a diffusion process. One is allow the number of jumps to be very large, that is lambda tends to infinity, and allow the size of the jump tends to be very narrow, so that mu tends to 0, and the second order moment is considered to be d. The second order moment considered to be d. Thereby, your diffusion equation comes. So the jump process, if you proceed into the jump process, we arrive with f plus and f minus the equation. Arrive the f plus and f equation 4.1, And then proceeding to the limit, we arrive at the diffusion equation. You see that the equation number 14.2 is the diffusion equation. And the solution for the diffusion equation, Carlin and Taylor, or even Cox and Miller, any standard stochastic process, we have it. In fact, we have also solved the solution by a technique called compensation function introduced by Kielson in the case of the diffusion process. That's the equivalent to the method of images. That's a different process. Now, for this diffusion process, we have arrived at the solution in a very nice form. Now, we go with a separable curve. I told you that we can manipulate the different techniques. Once you catch up the embedding procedure, once we catch up the embedding procedure. Now you see, now generalized separable curve. AXY we consider to be in exponential form, the simplest time. Very nice to add the integral differential equation. We are very easy to see closed form solution. Now I go into generalized form of the transition density. Look at the equation number 1.5.1. We have the x minus y modular. And for this, if you go into, for example, even the case n equal to 1, even the case n equal to 1, we apply the same technique, but we get the fourth order differential equation. If you get n equal to 2, you get a differential equation of order 6. So n equal to n, then we get a differential equation of order 2n. So the differential equation order changes, the procedure of getting the solution is the same, and we can one interesting thing for the case n equal to 1. What is the, now you see, they look at these algebraical methods of solving these equations. So we arrive at the differential equation for the moments in a very simple form, and also the differential equation for the first passage time. By the first passage time, I mean that the process crossed the fixed reserve level x is equal to k, or the process comes to the ruin at x equal to 0 by crossing the lower barrier. Now, they turn out to be differential equations of different orders. Ultimately, we convert the integral differential equation to differential equation, and thereby we can find out the solutions of these equations. We can find out the solution. Now I go into very nice separable form. We now go into, now look at this. Now first we consider the transition density is exponential. Then we consider the transition into x minus y whole power n modular e to the power minus lambda into x minus y. Now e to the power x minus y can be decomposed in e to the power x into e to the power y, so in separable form. Now I go a generalized separable form. Now to ax rho y by or ay rho x by, you see, x and y is separable form. Rho x is now the normalizing factor so that the total probability becomes 1. This embedding technique is very nicely applicable to all the separable density. When I go into the diffusion, the differential equation for this generalized transition density, I now get a differential equation. I now get a differential equation for F plus and F minus. F plus correspond to the first jump in the positive direction, and F minus correspond to jump in the negative direction. Now you see how nicely these equations are turning out to be. Ultimately, I come across in terms of A dash, B dash, where A and B are defined, you see what, and I get in terms of W we define in terms of a function of A and B, and thereby the differential equation takes a very nicest form which corresponds to a Fokker-Plotz equation. Fokker-Plotz equation is equation used by Wiener type, by Cox and Miller, as well as by Kolmogorov. Now you see this equation now is generalized into this form. Now when you ultimately the rho x can be determined also in terms of the defined function. Now what we have now seen is that ultimately we looked into a Fokker-Plotz equation arrives at the diffusion process and a Brownian motion of type which could easily be solved. Therefore, you can also see one other thing before going into the conclusion. I like to point out that this can be also applied to moving barrier. especially in the finance company, the risk reserve cannot be a constant all the time. The risk reserve will vary because of the inflation of the price rise, the cost of the commodity, and so on. And therefore, the barrier is to be remained to be moving. K becomes KT, a function of T. And in the case of moving barrier, also the same technique could be applied. And the Richard Bellman's technique of embedding method easily enables us to determine the arbitrary constant of the crossing of the barrier. And solution comes in a very nice form, but the only condition imposed is that the transition density should be in separable form. So, in generalized, to come into the question, what we have considered is that a transition, a probability density f of x comma t, which means starting the level x, is the process is going to cross x is equal to k, this level at time t, or is the process is going to be a terminator Boolean at x equal to 0, and then we have written the forward equation and the backward equation of the Kolmogorov. In fact, first we have written the backward equation, and the backward equation is converted in terms of the differential equation, and we solve the differential equation. The differential equation contains the arbitrary constant. In order to determine the arbitrary constant, we write down the total differential equation of the process concerning the jump both in forward and negative motion into one equation. We substitute this generalized solution into the form, and we are able to succeed at determining two conditions for determining the true arbitrary constant, and the closed form solution is obtained. Second, what we do that, even though we consider the density in separable form, we now consider the density in a generalized gamma function of the type modulus x minus y whole power n in e to the power of minus gamma x minus y. We succeeded arriving at the solution. The technique and the procedure remain the same for solving any type of problem, except for the condition the density should be in separable form. Then we go for a generalized separable form density. The transition ax comma y into the form ax rho y into by, ay rho x into bx, and we are able to find out that is x greater than y or y greater than or equal to. Rho is called the normalizing factor, so that the total probability density is 1, and we are able to succeed in such a solution. I told already that the main applications of this problem, even though they consider with reference to the stochastic norm, it is more applicable in storage theory, wherein the storage is going to be full or the storage is going to be empty. Or in the case of the brain cell, there is two type of inhibitory and excitatory cell which produces electrical impulses and crosses a fixed level, the message goes to the brain, and thereby we are able to see that the messages is now decomposed into various form electrical impulses and comes in a final coding form. Now, so since are basically they are called boundary value problems. The boundary value problems have different types of application with reference to the different fields. We have seen application in biology, we have seen application in technology, we have seen application in physics by studying heat conduction equation, the diffusion process. We have find application in finance and so on. There's so many applications, and therefore it might be possible to go into all these things. Now, what we are now finally going into that, in the case of finance, is the company is going to be ruined or the company is going to be prosperous. When the company is ruined means the net reserve becomes 0. If the net reserve becomes 0, the company still can borrow money from outside and then continue their business to expecting to be prosperous or other further it to be ruined. This is called the concept of bankruptcy. Now, we have extended this idea to bankruptcy in our next paper, probably might give a very interesting aspect of this type of finance problem to going into bankruptcy. Is really the company is going to be bankrupt because even the loan they are unable to pay, therefore below the negative level will go, or is it going to be ruined or is going to be prosperous. All these conditions to be analyzed to different form of the stochastic process and going into hypergeometric functions of type 1 by considering that the expenditure are proportional to the risk level. They are quite interesting.
So we have to wind up,
Possible
sir.
to solve all these things. Again, I am concluding this session by saying that the problem of diffusion ultimately go into the different fields of finance and neurobiology, not only start with physics, not only start with physics. Thank you very much for giving me the opportunity to conclude. If any question there, I will try to answer.
Thank you, Professor, for your exhaustive talk. I have touched on various aspects of your talk. I now invite the audience for questions and interaction with Professor Vittal.
Yes, thank you.
Anyone has a question? Mohan Kumar has raised a hand. Yes,
Yeah.
Mr. Mohan Kumar. You can ask your questions.
Yeah, is there any question?
Any question, Mr. Mohan Kumar? I saw somebody raising hand. Sir, you consider only the exponential kernel or different types of kernels also can be considered?
See, kernel, we started with one of the important condition is that the kernel should be in separable form.
Yeah.
Now, we started with the kernel first in the exponential form as the sake of simplicity to present the concept. Then we have seen that when the kernel is taken the form modulus x minus y whole power n, in e to the power of minus lambda into modulus x minus y, the procedure remains the same. The structure of solving the problem remains the same. We succeed in applying the closed form solution. Also, when the kernel takes the form ax rho y bx, and then in a separable form, either the jump from x to y upward, or x to y, x downward, this separable kernel helps you to get the solution in closed form, not only for a jump process, but also for a diffusion process, not only for a constant barrier, but also for a moving barrier and so on. So the structure of the kernel is necessarily very important in solving the embedding method, and that is, it should be in separable form. You catch very nicely the kernel structure.
Okay, sir.
Any other questions?
Any other questions? If there are no other questions, then we wind up this session by thanking Professor Vittal Kumar and Professor K.K. Jose for their excellent talks. On behalf of the organizing committee, I thank you both for your invited talks today. Thank you very much. And I thank Professor Satish Kumar for giving me this opportunity to chair this session.
Once again, I thank all the authorities in spite of the problem that they came across with the network and be able to at least give the talk. Presenting the talk in the
Sir,
presence is more important.
we couldn't see you in person, so if you can just open your camera so that the others also can.
Correct. Was it audible?
Yeah, it was audible. You can just stop sharing and maybe open your video so that
I see.
Can have a look at you.
See, I'm 87. I do not know how to buy. I have to ask my son. Anyhow, see, probably Satish Kumar sent in the message all of our photos. You see, in there.
Yeah. We could see you on the biodata. Yes.
All right. So I'm really very much thankful. If God permits, I will come to Trivandrum and then give you a talk physically there. Might be more impactful. I hope so. Thank you very much.
Thank you.
Most welcome, Professor. Yeah, most welcome. Yeah, we are there.
Yes, sir.
How to stop? Yeah, stop sharing. Yeah.
If you stop share,
there is an option to stop sharing.
Correct. Rakesh.
Yeah.
Correct. Rakesh, you stop sharing.
Yeah. Then only that that disappears. The mobile. You can see the mobile. Yeah. Once you have to stop share, then only the others can present. That's why. Are we okay? No, can see your mobile. There is a stop sharing only. Stop sharing option. Yeah, now it's fine. Stop sharing. Yeah, you can open your. Yeah. You can open your the camera so that we can see you. There is a camera option.
See me now? See me now?
Yes, sir. Namaskar.
Yeah, now we can see you.
Yeah, we are able.
By
Namaskar.
the time
I'm
we
on.
could see you, that's why.
Thank you, Satish Kumar, to be a good friend of mine and probably of the initiatives that gave me and all that. Some of them are also enthusiastic by your
we, in fact, we are all, yeah, sound is, you have to place your, yeah, some audio is not in better mode, I think. Okay, you have to, yeah, left. He left.
Next session is at 5:30, I suppose.
Yeah, 5:30. Now there's time, no problem. Yeah.
Yeah, 5 more minutes.
Yeah, 5 more minutes.
Yes, sir. Speaker from Israel is already ready.
Yeah.
Namaskar, sir.
Yeah.
Shall I share my screen, my presentation?
Yeah, before that, you have to just introduce the chair of the session, because chair has to join, the session chair has to join, Professor. Yeah.
Okay.
In your session, there are two speakers. Professor Indranil Ghosh also there, the second speaker. Yeah.
Great.
We can start with you, no problem. But before that, the chair, Ranjita Pandey, Professor Ranjita Pandey from Delhi University of Delhi,
Okay.
she has to join.
Yeah. But can I try and see whether I can share
Yeah,
my
you can
screen?
try. Yeah, you can try for the sharing, etc. No problem. To check it whether it is working or not. Like that.
Okay, so it works.
Yeah.
Right.
Now it is coming. Yeah, we can see the slides. Yeah.
Okay, great.
Okay, fine. Let me to contact the Ranjita Pandey. Otherwise, we can. We have 4 minutes, so that by the time she will join. Yeah.
Yes, sure.
Madam is here. Yeah, she has already joined. Okay. Okay, welcome. I think now there are 3 minutes. By the time we can start the introduction, etc. Actually,
Yes, sir.
yeah, actually, you can introduce the chair and do the needful for, and also the speaker briefly, and help the chair to run the session in a smooth way.
Okay, sir. A very warm welcome to all of you to the 8th technical session of the 10th International Webinar on Recent Trends in Statistical Theory and Applications. It is both an honor and a privilege to introduce the esteemed chair and distinguished speakers who will be guiding the enriching our discussions today in the special invited session. Let me begin by introducing the chair of this session, Dr. Ranjita Pandey from the University of Delhi, India. Dr. Pandey is a highly respected academician and a prominent figure in the field of statistics and applications.
Isn't it? Ashwati?
Yes,
Okay.
sir.
Over to the chair. You can invite chair. Okay, please.
Okay. Okay. Thank you, sir. I will begin the session. The first speaker is Professor Elion Solen from University of Tel Aviv, Israel. His topic is Identifying the Deviator. Professor Solen, please present your papers.
Thank you very much. Okay, so yeah. Okay. So thank you very much for the invitation to present my work here. And today I'm going to talk about a paper that originated from my research on game theory, but actually it has implications, I think, and can be useful in other areas as well. And this is the topic is identifying the deviator or the faulty agent. And this is a joint work with Noga Alon from Tel Aviv University here in Princeton, with Benjamin Gandy, who is a postdoc at Rutgers, Xiao He, who joined recently Georgia Institute of Technology, and Eran Shmaya from Stony Brook University. So, let me start with a motivating story. Suppose that we have two agents, Alice and Bob, and we would like them to generate a random sequence of bits, zeros and ones. And how are they going to generate those bits? So Alice will generate the odd bits, the first, the third, the fifth, and so on. And Bob will generate the even bits, the second, the fourth, the sixth, and so on. And each one of them, in his or her turn, should flip a fair coin, look at the outcome of the coin, and report to us the outcome. So if it was heads, he or she should report 0, and if it is tails, she or he should report 1. So this is how they are supposed to generate the random sequence of bits. Now, how do we know that actually they follow those instructions and none of them is faulty? Faulty might be that, and for some reason, they report incorrect outcomes. It might be that they lie and they actually intentionally misreport the outcomes. It can be that the coin maybe is not 50-50. So in any perceivable way, some of them might be faulty. And we would like to know that none of them is faulty. How do we check that? So there are many randomness tests, and people in computer science, there is a whole plethora of such randomness tests. And let's consider a really simple test for checking randomness, which is to check whether the long-run frequency of ones is 1/2. So if none of them is faulty, if both of them follow the procedure we have written here above, then they will pass the test with probability 1. Now, suppose that the realized sequence that they generated fails the test. So the long-run frequency of ones is not 1/2, it is 1/3. Okay? We would like to know who among Alice and Bob is the faulty agent so that we can fix it. How do we do that? So with such a simple test, the long-run frequency should be 1/2. Well, it's rather easy to find who is the faulty agent. You simply calculate the long-run average of ones in Alice's bits, and you see whether it is 50. You calculate the long-run average of heads in Bob's sequence, and you see whether this is 50%. And if the total average is not 50%, then the total average of at least one of them is not 50%. And therefore, we can identify who among the two, and maybe both, are faulty. Okay, so that was a simple test, and then we could easily detect the faulty agent. But what about a more delicate test, a more complex test? So we can interpret the bits, zeros and ones, as a random walk, right? We have a drunk who starts at the middle, and whenever the outcome is one, the drunk goes one step to the right. Whenever the outcome is zero, he or she goes one step to the left. So we have a random walk, and the bits that Alice and Bob generate control the random walk. And as we know, a random walk returns to the origin with probability 1. Every time the random walk returns to the origin, it means that the number of zeros is equal to the number of ones so far. So let's look at the following test of randomness, which is if there are infinitely many times the drunk return to the origin, that is, if the number of prefixes in which the numbers of zeros is equal to the number of ones is infinity, then we say that the sequence is random. Suppose now that the realized sequence fails the test. So there are only finitely many prefixes in which the number of zeros is equal to the number of ones. Our drunk in the random walk returned to the origin only finitely many times. Whom among Alice and Bob is faulty? So now this is more difficult test to verify, and it's not clear at all how we can actually identify the faulty agent. And this is the task that we take in this project. Identify a faulty agent when we observe a sequence of outcomes that is randomly generated, according to some given rule, given statistical law. Okay. And the model, the general model, is as follows. We have a finite set of agents, which I denote by I, and each agent has a finite set of actions, of outcomes, that he or she can generate. This is AI. And I denote by capital A the product, the Cartesian product of the AIs, of the actions, so that A is the set of action profiles. And then we have the horizon of the problem, N, which can be either a finite natural number or infinity, if you would like to work with an infinite horizon. And now we suppose that each agent, each unfaulty agent, follows a pre-specified policy. So what is a policy? A policy indicates to the players how to choose his action in the next period, given whatever happened in the past. So for every past sequence of action profiles, A1 up to AT, up to time t, sigma I star, the policy of player I, indicates how to choose, possibly randomly, the action given the past history. So sigma I star of the past history, A1 up to AT, is a probability distribution over the set of actions of player I. So this is a policy for player I. In our example before, with the random walk, the AIs were 0 and 1, and the policy was simply 50-50. At every period, whatever happened in the past, choose 0 or 1 with equal probabilities. And now we have the equivalent of a test that we had before, which I call here a goal. A goal is a pair of the vector of policies of all players. So sigma star is the set of, or it's the vector of policies sigma star I, together with a set D of sequences of outcomes. So A is the set of action profiles, the actions, the outcomes that we choose in every period, each one of us. Then to the power n is the horizon. So A to the power n is the set of all possible sequences of action profiles. And we have a goal, a subset, a target set, D, which we would like to reach. We would like the sequence that is generated by the agents to be an element of D. So this is a goal. Again, a vector of policies and a target set. In our previous example, D was the set of all sequences, infinite sequences, in which we have infinitely many prefixes for which the number of zeros is equal to the number of ones. Now, suppose that the generated sequence fails the test. In that case, we need to identify the faulty agent. So the function that identifies the faulty agent is called a detection function. This is a function from the complement of D. Remember that D was the target set. So if the sequence of outcome, action profile is not in D, then it means that the players failed the test. And then we like to find the faulty agent. So that we have a function f, a detection function, from the set of all bad sequences that fail the test, to the set of players.
So you have 5 more minutes.
5 more minutes. I thought that I have 25 to 30 minutes.
That's 15 minutes you have.
Okay, fine. So we will faster. And so the goal, we say that the goal is detectable, detectable. Sorry?
No problem, please continue. You have 15 more minutes. Yeah.
Plus 5 minutes you may take, sir.
Okay, so the goal is delta detectable if there is a detection function such that we identify the faulty agent with high probability. So the probability, if the agent is faulty and chooses an alternative policy, then the probability that the sequence does not pass the test and we identify an honest player as the faulty player, this probability is small. And so the question is whether we have, so let's skip the example, and the question is whether or which goals are detectable. And the answer is that all goals, all target sets are detectable. So for every epsilon, take a target set, D, which is obtained if all players are not faulty, if they are follow the policies, then the target set is obtained with high probability, at least 1 minus epsilon. Then, if there is a faulty player and a faulty agent, then we can detect that agent with a high probability, where high is of the order of square root of epsilon. And this bound is the oldest, square root of epsilon is tight. The constant you can prove them, but the bound is tight. So this is the main result, and it works, as I said, with a finite horizon or an infinite horizon. It works whether the agents move sequentially, as in my examples, or simultaneously, as in the general model. It also works if the set of actions is countable and not finite. And this is what I wanted to present today. So I will skip the comments and yeah, any questions?
Callers present online, if you have any questions, Professor would you like to have some questions or suggestions, or maybe some queries related to theory or application of the presented topic, please?
Professor Solan, you can detail the work up to 605, no problem. To 605. Can take 5-10 more minutes. By that time, you can detail whether you can skip anything. Huh?
Okay. So let me go back to an example, if I may, or do you think of a different thing? So covering an example to explain this issue will be fine. Okay, saying that we have the two agents, Alice and Bob. They choose bits, zeros and ones, alternately. Suppose that the policy n, Alice should choose 1 with probability C over n, where C is small. So she chooses 1 with decreasing probabilities along the sum of 1 over n is infinity. She chooses 1 infinitely many times. Bob follows the very same policy. At stage n, Bob chooses 1 with probability C over n. And so suppose that the set of bad sequences, which we do not want to obtain, is the set of sequences where we have 1 both in stages 2n plus 1 and 2n plus 2. So in 2 consecutive stages, we have 1. First, Alice chose 1, and then immediately, 1 stage afterwards, Bob chooses 1. So those are the bad sequences. What is the probability of the set of bad sequences under the policies of Alice and Bob? So that Alice chooses 1, we need probability C over n. So C over 2n plus 1 times C over 2n plus 2, and we should take the summation over all n. This summation is of the order of the sum of 1 over n squared, which is finite. So if C is very small, this probability of the set of sequences is very small. So, okay, and then our theorem says that we can detect high probability if one of them is faulty. This means that if we obtain an element, a sequence which is bad, so Alice chose 1 and immediately after Bob chooses 1, we can identify who among them deviate. How do we do that? Who among them is faulty? I note that how can we identify whether Bob is faulty? Bob sees, he observes whether Alice chose zeros and ones. So we can choose zeros always. And then the moment Alice chooses one, he chooses one. Or the 100th time Alice chose one, he chooses one. So how can we detect such deviations of Bob, such faultiness? So the idea is as follows. We look at the number of times Alice chooses one. If Alice chooses one very often, then we say that Alice is the faulty agent. If Alice chose one only not frequently, then we will say that Bob is the faulty agent. So formally, we look at this up to the stage n in which the players failed the test. So in stage 2n plus 1 and 2n plus 2, they both chose 1. We look at the summation of Alice's choices divided by 2n plus 1 at this sum, and we ask whether this sum is larger than 1 or smaller than 1. If it is larger than 1, Alice chose 1 often, then we declare Alice as the faulty agent. Otherwise, if the sum is smaller than 1, then we declare Bob the faulty agent. And it turns out that this test identifies the faulty agent with probability which is of the order of C. Okay, so this was an example, and now about future directions. So first, our theorem is existential. There is a way to detect faulty agents. But how do we do that? In the random walk case, how do we identify the faulty agent? So in that case, we do know how to do it, but that's it. There are essentially only very specific cases in which we know how to detect the faulty agent. Also, we are able to show that we can identify the faulty agent with probability which is of the order of square root of epsilon. But this is not necessarily the best detection function. So it will be interesting also to know, in cases of interest, what is the best detection function. Now, we assume that we have only a single agent who is faulty. What happens when there are more than one faulty agent? When 2, 3, 5 agents can be faulty at the same time? Then we do not know how to identify the faulty agent. Finally, what happens when we observe the actions, the choices of the agents with some noise? Again, in that case, we do not know how to identify faulty agents. So there is plenty of work to do in this area. And I hope that we will be able to further it and that you will be able to progress this research question. Thank you very much.
Sir?
Yeah.
Yes, Dilip sir has a question. Dilip sir, do you have a question?
Professor Ghosh, you have to unmute your mic. Professor Ghosh, you have to unmute your mic to ask question.
No, I have no question. Huh?
Yeah, okay, okay,
I was
okay.
just asking of Anil
Yeah,
to
yeah.
hi.
Oh, okay, okay, okay. Okay, any other questions you can. Okay.
That was an interesting presentation from Sir. Uh, we thank you, Sir, for this nice presentation and considering the events. Yes, Sir. Uh, Thank you. So now I invite Professor Indranil Ghosh to present.
to say in that direction. So, okay, so now how do I proceed to, okay.
You may sing, Professor Ghosh.
Oh,
You may,
okay.
because this is converted to PDF, you may scroll down, use the sidebar, sir.
Okay, somehow it is not active in my, let me see.
Yeah, sometimes happens. We can
Okay.
stop sharing and start again share. Then it will.
Okay, I'll do that. Okay, and then I'll again reshare. Okay. Okay, still it's
So another option is you may share directly from the mode which is showing on your screen. You can
okay.
share that one rather than sliding it, rather than going to the show. Right. Just do
So,
it as you see on your screen. Don't go to the slideshow, sir.
okay, so just because I have a PDF open, so is that fine? I can.
Yes, you may scroll down. This is good. We can see the movement, sir. You may scroll down.
Okay, I got it. Well, I'm still not that much familiar with the new Google setup. Perhaps I need to change in my Mac. Okay, so here is the outline of my topic: why we need extropy. What is the some of these useful preliminaries corresponding to the notion of extropy, and why suddenly we were concerned with the conditionally specified models or hidden truncation models to get these extropy measures, and then I'll talk about some of these examples in a way. Well, the idea was that there was a seminal paper by Ladd in 2015, and after that, a series of scholarly works have been introduced to the idea of extropy, like weighted extropy, cumulative survival extropy, and so on. However, when we looked at the literature, to the best of our knowledge, not much work has been done in the direction of deriving extropy and other associated structural properties corresponding to conditionally specified models. And of course, one of the major motivation was that, well, it is much more easier to visualize, on a one-dimensional course as compared to a bivariate setup or so. And bivariate distribution can be characterized by, let's say, x given y, the distribution, and the full knowledge of the marginal distribution on y. And also, it can alternatively be represented by two sets of conditional survival functions. So, those things were already in our mind when we look at the extropy measures. Now, one of the other motivating factor was for us, in dealing with from a practitioner's point of view. There is a almost, let's say, on a daily basis, a new continuous or absolutely continuous probability model is being unearthed, or bivariate probability models. So the literature on distribution theory, of course, I haven't seen that much of discrete probability models, maybe due to lack of uh, analytical tractability or dealing with special functions. But the literature on continuous probability distribution is quite huge. Now, from a researcher's point of view or a practitioner, is that how do you distinguish which model to consider? What are those set of rules that will be an yardstick that, okay, if this happens, then I will select exponential distribution. If this happens, then I will select the two parameter gamma distribution also. Now, contrary to that, or I might say in addition to that, there are other situations, especially let's say in income modeling or so. There are scenarios in which a data has been subjected to a hidden truncation, like for, what is the, for example, what is the amount of expenditure that someone spends on, let's say, grocery item, given that the the tax level has not increased to a certain point, let's say t. So you are interested in knowing the structure of x given y less than t, or it could be x given y bigger than t, or it could be that y is truncated from both upper and lower, a to b, and you want to know the distribution of x. There has been a lot of work, and especially I will mention the work by Arnold and his co-researchers. There is a paper on hidden truncation models that appeared in Shankar in 2000, and I have done some work to these hidden truncation models, specifically for Pareto distribution and other type of univariate or bivariate probability models. And then what another big motivation for us was to see, well, how do we come off as a measure of discrimination, that whether to select a non-truncated version of a distribution or the truncated version based on some measures of discrimination that we can develop through the extropy measures. Measures of discrimination is not new in the literature. There is a paper by Balakrishnan and his co-authors that appeared in 2022, if I'm not wrong. The reference is in my list of references. So the discrimination measure would be useful. So that was another motivation for us to consider this work. Now, in terms of the definition, the extropy as defined by Ladd is given by negative one half. See in the equation 0.1. So we consider this as our pivotal quantity, and then we proceed with the hidden truncation models for determining the extropy measures. Now, in terms of hidden truncation models, well, we particularly focused on two types of mechanism per se. One is the type 1 in basically it is developed, originally developed and explored by Arnold and Beaver in their 2000 Shankha A paper. So you start with U1 and U2, two independent random variables with their CDF and PDF, so well defined. Then you look at the conditional distribution of U1 given this a restriction that lambda 0 plus lambda 1 U1 is bigger than U2, where lambda 0 and lambda 1 are two parameters that you bring into your model, and the distribution, the conditional distribution of U1 given that U2 with that restriction would be given in equation point 2. And in such a case, if you consider lambda 0 gets really large, then in the limit it would be non-truncated or unconditional version of the density of U1. Now, if you consider lambda 1 to be 0, then we have the conditional density of U1 given U2 less than lambda 0, which is the unconditional density of U1 because U1, U2 are independent. So it considers, subsumes the independence. The other type of which we call type 2 is given in equation point 3. So that's it's fairly standard definition. So this model considers all three types of truncation from below, truncation from above, and two-sided truncation. Now, I must mention here is that the estimation of the model parameters in case of hidden truncation models is not that easy. Even with this, advent of supercomputing packages, whether it's R, whether it's MATLAB or Mathematica, SAS, you call it, and especially is how to get an idea that whether or not a data set has been subjected to hidden truncation. In one of my co-authored paper, we tried to consider Bayesian perspective. I would say we were partially successful, but not that much. The big question was that what set of priors you would choose for a hidden truncation parameter that you don't have knowledge. And if you consider an uniform prior, or let's say informed prior, let's say flat on 0 to 2, basically you are doing the classical maximum likelihood estimation. Not exactly the Bayesian, but we tried this approach and we were able to see that our procedure identifies to some extent accuracy level that well it is correctly identifying the misspecification that is happening also, but that's a different topic. So coming back to this scenario, so we consider two types of hidden truncation, and basically for two-sided truncation the conditional distribution of x given y is and by the way x and y are concomitant. So y is between a to b, a and b are obviously a less than b, that are in the subset of y, the distribution would look like what we have in equation point 4. Now, of course, there are a lot of details have been provided in our paper. This paper, this is the result of a paper that appeared in Communication in Statistics in 2024. And I forgot to mention, which I must, two of my co-authors, S.M. Sunoj and P. Sarano, as a student of Professor Sunoj. So they were instrumental in developing a section on conditionally specified extropy models. So this was my first time playing with this idea on extropy. So I'm not an expert. I would say I'm still learning few things. So what I only focused on hidden truncation models and developed some theorems for the paper. Um, so here are they. So extropy for hidden truncation type 1 models, the upper bound would be given by 2 times J0 of U1, where J0 would mean the extropy for the non-truncated version of the random variable U1, provided U1 and U2 are symmetric about 0. And of course, lambda 0 is set to 0 and lambda 1 equals to 1. So it is in a restrictive format. And the extropy for hidden truncation model, whether it is one-sided or two-sided, for an absolutely continuous random variable x, it's negative. And then the third one, it is actually developed by my co-author, if we consider x1 and x2 are two non-negative, absolutely continuous random variables with their respective survival functions well defined, and if we further assume, or it is established, that if x1 is stochastically smaller than x2, then the cumulative residual entropy and cumulative past entropy, the following inequalities will hold. The proofs are provided in the paper. I would just exclude from my current discussion, but if anyone is interested, I'll be more than happy to share the paper. Now, the other major point of interest was that how we can come up with measures of discrimination. So we considered a very simple measure. Let's say between two rival candidates. Let's say you have a hidden truncation model and we have a untruncated version of the random variables, and with their respective distribution functions, cumulative, well defined, and we decide in favor of one of them on the basis of the following difference. So we basically took the difference of their entropy, and large values of D12 will support the hidden truncation model to consider, and a smaller values of D12 would indicate to select the non-truncated version. Now, a pertinent question that might arise to our mind is that how small it is or how large it is. Well, we mentioned in the paper that it is that it's there is not a hard and fast rule, or we could not come up with a mathematical or formula or statistical proof to this, but it depends on the experimenter. If you say, well, D1, I mean, simply if D12 is negative 0.09, well, you might say, well, it's very small, it's close to zero, so I don't know, who cares, I can go with either one of them also. But if it is negative, we'll go with this non-truncated version. If it is bigger than zero, I mean, let's say bigger than 0.03. In fact, we had done some simulation studies based on comparison of truncated version of a random variable with that of a non-truncated version. We had some discussion on the paper. So if we do that, well, with this measure, if you want to consider comparison between truncated normal with that of a non-truncated version, it's a simple standard normal distribution. The measure will look like the expression that we have. And in this case, if we have negative values, what we mean is that it might have a less information on the uncertainty in some cases, while a positive value of D12 will indicate that the truncated normal probability model has more to share or offer in terms of uncertainty measure. That would be preferred by a reasonable model for the application purpose. Then, if we had a scenario of truncated exponential with that of a non-truncated exponential, the associated measures of discrimination would look like what we have in the expression as you see in equation point 6. And in this case, likewise, the interpretation goes pretty much the same. Our negative values will indicate us, will guide us that, well, the truncated exponential model might have less information or uncertainty, while a positive value of this discrimination measure will indicate a truncated probability model has more to share or offer. So that was the guiding principle that we came up with, and we have shown with some applications, the real data application for conditionally specified extropy models in the paper. And again, for if we consider hidden truncated exponential type 2 scenarios with that of a non-truncated or simple exponential, the associated discrimination measure will look like this. And here, there are some guiding principles in the sense that, well, if with lambda 0, lambda 1 fixed, and theta increasing, so the non-truncated version has exponential with mean 1 by theta, and if theta is increasing, then this measure will get smaller. If lambda 0, lambda 1 are increasing, and with theta increasing, this measure of discrimination will get smaller. And well, this one we in the paper it says lambda 0, lambda 1, and theta are all increase, but it has to be there is a slightly mistake. So lambda 0, lambda 1 decreasing and theta increasing. Forgot to include that. Then d1 2 gets bigger. So that was the idea. So these discrimination measures based on these extropy is very simple to understand. One of the big question that arises, and of course you can do a lot of these simulations. You may not need a nice analytical tractable expressions or involving complicated special functions in general, because this could be done. But because this was our very pretty much the initial approach, we focused on the paper for simple type of truncated and non-truncated version, so that we can share, we can represent to the audience that, well, in cases, in situations, there is a simple, nice expression, but we do acknowledge the fact that there are probability models like truncated Weibull with a non-truncated Weibull. Things may get real murkier. And of course, the big question is, do we find enough application? That must be the guiding principle before we start on developing those complicated expressions or moving in that direction. So that's why we didn't consider an extensive list of probability models and consider these discrimination measures or associated extropy measures. But one can obviously, even for purely sake of academic interest, one may work on this, and maybe for journals that focuses on mathematical statistics and theory, they might get published, and with some motivation, of course. But we focused on simple type of models like normal huge application, exponential probability models. A lot of applications are there. Now, for conditionally specified extropy, well, this is, as mentioned earlier, well, it's a bivariate distribution, can be sometimes challenging, if not always. And it can be defined entirely by characteristic of two sets of conditional densities. And on this subject, a good reference would be the book on conditional specification or conditional specified models by Arnold, Sarabia, and Cassio. There is a book by Springer that appeared in 1999, and that still I get a lot of these guiding ideas to deal with the conditional specified probability models. So we looked at the dynamic cumulative extropy function based on conditioning of first type for the random variables given x given y equals to t and y given x equals to s. So here is a definition of what we mean by this conditional extropy, conditional specified extropy models. So that is given by these equations, and if you take this differentiation, it would appear with these conditional hazard rate. And if you do this solution to first order partial differentiation, you will come up one will come up with this equations. And for specific models, it can we can have and analytically tractable or closed form expression. So, for the sake of illustrative examples, I have only considered one of them, but in the paper we have three more examples. So, we start with the bivariate Gumbel distribution, and for that, it's a routine computation that gives you this conditional specified extropy functions. And we came up with this theorem that this relationship in this particular form will hold if you have bivariate distributions with beta conditionals with these restrictions, bivariate distribution with exponential conditional that is originally, I mean, this model due to Arnold and Strauss, and then bivariate distributions with the Pareto conditionals So for each of these models, the conditional specified extropy will hold relations as described in this equation point 1, 2. So again, in summary, well, I tried to make it simple because um, from the program brochure, I thought that, well, I have a very short time, I have to present all these things. So I didn't include a lot of stuff, but I'll be more than happy to share the paper, which has a lot of adequate details. So in summary, what we try to do is that, well, extropy measure is not new to the literature. What we only focused on that, well, what happens when we have the conditional specification? Well, there and hidden truncation model is a particular case of conditionally specified models. So let's do some work on identifying what would be the extropy or measures of uncertainty, if you want to call it, for hidden truncation or conditionally specified probability models, and then come up with a simple measures of discrimination that might be useful in situations where one would be interested or we are provided information on extropy. Now, I haven't checked it, so bear with my limited knowledge on that. That measures of discrimination based on entropy, it might have already been a lot of work. I may not be aware of, but certainly we can look into that. And in terms of what we observe is that simple closed form expression for extropy for even simple type of models, when we, let's say we move or we make our departure from non-normal families, such as for Pareto, I mean Pareto type 4 or bivariate Pareto type 4 type distributions, or the most general failure Pareto type distribution would be really complicated. So, but we try to provide in the paper with some numerical examples for illustrative purposes. Now, we were interested that can we mimic this idea to higher dimension? Of course, it can be envisioned. We can think of, but of course, it will involve, bivariate or higher dimension integrals, especially for conditional specified extropy models. And even before we could think of, or we may get some results on that, we were partially successful in obtaining in some cases, but we could not proceed further. And the reason why we are still waiting for that is to come up with a very strong motivation, because without the motivation, it would be like just a piece of graduate levels node on a statistics math stat class. So we are working on it, and we might be able to do a comprehensive literature review and to compare with existing measures of discrimination and observe the relative performance, because if it is not to that satisfactory level, then obviously people will not be interested and say, well, we'll proceed with what exists in the literature. So with that note, here are some of these references. So this is the one that we got a sound idea on hidden truncation model. There is a lot of research work. As I was saying earlier, I could only cite some of them, but a comprehensive list can be found if you just type in Google Scholar. I find that there are what is that, 6,500 results on just using the term extropy. There are so many results, so many papers that it's not possible for me to look at all of them, but there are certainly interesting papers like this by Balakrishnan and his co-authors that appeared on extropy measures. And then some ideas on multiple constant skew normal models as a particular form of within the let's say umbrella of hidden truncation. You may find these ideas quite nicely in this multiple constant and truncation truncated skew models. And here is a reference to this our paper. So with that note, I will stop here today, and any questions that you might have. Thank you for your attention.
Thank you, Professor Ghosh. This was a very theoretical concept, but explained in a very connecting kind of a way. Most of the people are aware of the term entropy, and this concept of discriminating is new to us. Maybe a few of you already know. However, since we have a lot of time now, those who wish to question your suggestions or some confusions in the topic, you may please ask. The scholars, the floor is open for discussions. Please ask. Professors who are present on the forum, would you please like to give some suggestions? As Professor Ghosh said, that he would like to know more practical aspect why we should do this. The senior teachers, professors. Can we have a discussion? We have time. Okay. So thank you, Professor Ghosh. Maybe I'll get in touch with you because I've been making my notes to your slides. And surely nowadays I cannot read properly due to my problem. But I'll surely get in touch with you. I'm interested in the topic, the way you presented it.
Yeah,
Thank
yes,
you so
Professor
much.
Banga, I'd just like to mention that I can certainly share the paper with you if you think that would be useful.
Yeah, sure. Please do that. Thank you. Thank you. Thank you, organizers, for giving us this platform to interact. And it was a good session. Sorry for some goof-ups from my side. Thank you, sir. Thank you, University of Kerala. Thank you, all the scholars, all the teachers who are involved in this huge webinar process. And it's really very good that Satish sir always gives these kind of platforms for people to interact from their own places. So I think it's a very good opportunity for people to understand new areas. Thank you, Satish sir. Thank you for giving me this opportunity to chair the session. Thank you.
Thank you, Professor. In fact, we have an excellent talk from Professor Inaugural Ghosh and Professor Ellen Sula. And both are, in fact, useful talks to the youngsters in particular, those who are interested in working on the area, detailed in several ways. And we are grateful to you, Professors, for your support to our conference. And also wish to extend our gratitude to Professor Ranjita Pandey for joining this session. In fact, we have some more time, 20 minutes, remains for this session. We have, in fact, enough in between. I have placed 10 minutes for the do not affect the next session. That's why in the timely manner we have to go. That's why. And sometimes the discussions go take more time, and that may not. In fact, that is also valuable for us, especially for the young generation or young researchers in this area. Yeah. And I hope these 20 minutes you can spend for, if needed, you can spend for interaction, any type of interaction. I hope, yeah, please, someone, please.
The students may ask questions, this is a good platform and we have time. So little things that you come across in your research and you have some difficulty, the little concept like entropy. So why only sample is required, right? If you don't have sample, you have no entropy, right? So, and then this concept of entropy. If you want to ask the students who are present here, you may please ask Professor Ghosh, she is available. I think they are not prepared because every session has so many varied topics. So at leisure, they can sit down, make their notes, and then contact individually each of the resource person who's presenting here. But Professor Ghosh, if you would like to tell me, I would like to know, sir, I've not heard of extropy before today. I've worked on entropy and the usual conventional was Rayleigh and Shannon only. And we do it through sample. We do understand we are condensing the information. But extropy, if you can please tell us something about it.
Well, Professor Pandey, well, I'm also sort of worked on, I mean, of course, on a distributional aspect of you computing the entropy and the measures of discrimination. I think probably you know better than me. The idea of extropy came to my mind when I read a paper from Professor Sunil that, well, and also there is a paper. He happens to be one of my collaborators. I've worked with Professor Balakrishnan, and I saw a paper that, well, measures of uncertainty, extropy. So, and I look at the simple definition by the seminal work by Ladd, which says, well, it's -1/2 integral f square. I mean, take the density square, and it's a simple integral. And that was the sort of a quick, I would say, interesting fact that appeared to me. And then I thought, well, there has been a lot of, I mean, it's a whole lot of theory and methodology and application that have been provided by, I would say, Balakrishnan in a series of papers. He has worked on a lot more on this. So yeah, I can certainly share that with you. So when I looked at that, okay, how much, what happens that, because one of my research area was on hidden truncation model that I worked under Professor Arnold while I was in Riverside, California. So hidden truncation model itself, it's there are so many issues with that in the sense of efficient estimation, is the lack of information on the hidden truncation parameters you are bringing in into your model. Your model already has certain parameters, then you bring in a truncation point that is combining with the existing parameters in the model, giving you a set of not always simple, uh, complicated parameter space. Whether or not those parameters are identifiable, it's not always identifiable as always. And then if that is the scenario, that if someone is working with a data set that has been subject to hidden truncation, what sort of lack of information could be measured through the help of extropy or measures of uncertainty? So that was the guiding principle for me, uh, to have some things. So I realized that, well, let me try with this. Then I reached out to Professor Suno. She's been very helpful, and we had a nice collaboration. So this was the paper in which I focused on, well, let's look at the simple type of probability models and consider their truncated version and non-truncated version, and see from a practitioner's point of view whether we can do some, or come up with some measures, or set of rules that might help. That, okay, if you see this discrimination measures is positive or negative, then accordingly you might select which distribution to take. I mean, there is a plethora of distributions, like, even on the, let's say, your data set is well defined over the positive part of real line. We have so many distributions like gamma distribution, level distribution, exponential, and so on. Then how do you decide which ones to pick, so that you will have less time in getting to the right probability model, and you can work on it? So because I worked on conditionally specified models, so my interest was on that. And the other factor on a lighter note was that I haven't seen any paper focusing on that. So it was an easy sell for us to work on that. But in the long run, what my plan is to come up now discrimination measures based on extropy for two competing probability models, not just the truncated and non-truncated version, but just two models. So a set of rules that might help researchers that, okay, if this happens based on our data and we do a simulation study and here is the result, or you apply, you have to simply estimate those parameters and here is the discrimination measures, then I might go with the distribution 1 or I might go with the distribution 2. So that's the sort of idea that I had. But for conditionally specified or conditional hazard function related developments that a good chunk of the paper deals on, so that my other co-author might be able to come up with more explanation, because that was his part. He worked on that and he has more knowledge on that. So I will, if you have any question, I'll refer to that or I'll ask my co-author to that. So for me, well, it's a interesting thing, lack of information, extropy. So it was my first attempt to see, okay, what can be done, so my guiding principle was with that simple expression that was given by Ladd, that integral minus 1 over 2, that univariate integral. So that was the guiding principle. So I haven't looked at all these properties, to be honest with you, but I certainly plan to do so.
Thank you so much. So it was a nice explanation from you. So I think we can leave the meet. Thank you everybody for being present here. Thank you organizers. Thank you the presenters here, Professor Ghosh and the first speaker. I'm very sorry we cut down on his talk. That was Professor Elon Solan. So are you present, sir? Okay. I'm really sorry for cutting down on his time. Okay, so thank you, Satish sir. Let's break from here. Okay, thank you.
Because of the no problem, madam, because we could understand the problem, and also there's a typographical error that occurs why. Even though I have sent a message to you, the detailed timing, etc., via WhatsApp earlier, but you are not noticed that. No problem, man.
Okay.
Anyway, we have a very wonderful session. In fact, and we are tired, and we are grateful to all the professors for their support and blessings. And
Thank you.
thank you so much. Thank you. Now we have two other in the next session is Professor David Banks. He's waiting, and Professor Narendra Kumar. I hope he will join shortly. So, yeah. And we have some more time, 10 minutes can take. It's at 7:47, yeah, 10 minutes, around 10 minutes we can take. By the time Professor Narendra Kumar should join to chair the session. How is Professor David Bank? David Professor?
Hello, Professor Kumar. How are you?
Yeah, fine, Professor. Yeah, doing, yeah.
It sounds as though we have a little bit of extra time. Would you mind if I attempted to share my slides to make sure that I'm able to do it correctly with Google Teams?
Yeah, Professor. We can share it from here.
Okay.
Okay. Please try, Professor. Try to share it. You can share, and by the time you can check it, Professor. Or otherwise, we can share down.
Okay, I'm trying. Let's see.
Yeah. Now it is coming. Yeah.
Okay.
We can make it full screen if possible, Professor.
I am trying to do that.
Yeah. Yeah, now it's fine. Yeah.
Okay. Well, that's good to hear.
Yeah.
I'm no longer able to see you, Professor Satish Kumar, but I don't know that that's essential. I can advance things. That seems to work. So we're in good shape, I think.
Yeah.
Excellent.
Yeah.
I am so sorry that I wasn't able to make the inaugural talk. It was 11:30 my time at night, and I was already
Oh,
asleep by
oh,
then.
okay, Professor. Okay. So, Professor Teacher Rao, Professor Teacher Rao, Professor, is from
Yes.
Indian Commission. Yeah, yeah. He inaugurated uh, today morning.
Excellent.
What about the timing there, the morning time, whether it is convenient for you, Professor? While
I am so grateful for the way you scheduled me at times that work with my biological clock.
yeah, yeah,
It's
yeah,
very difficult.
yeah.
Uh,
In fact,
and I'm impressed by your stamina in having these long meetings that start early in your morning and go into late in your night.
thank you, Professor. Thank you so much for your compliment, for nice words, and we are grateful to you, Professor.
Oh, this is a great honor.
Yeah.
What is the temperature like in India right now?
At present, about here in Kerala, it is a medium level temperature always, most of the time. Now it is 30, 32 is the
Okay.
temperature. Yeah.
Warm, but
Uh,
not crazy.
but in India, while considering in Kashmir, and some there's low temperature. In some places, there's a varying temperature. But,
I was talking to a friend of mine at the Chennai Math Institute, and he
oh,
was telling me that last year they had a month in which the temperatures
oh,
got,
okay,
almost to
okay.
50.
Yeah, okay, okay. Yeah, yeah. In Chennai, it is more, almost, yeah. It's almost of the time, high temperature comes. Yeah.
Yes.
Extreme temperature, yeah, Chennai. Here now, there's raining also. Last day, heavy raining, but not much difficulty. But
Well, I'm glad it
and
is not too hot there.
if possible, try to come over here to Kerala, Trivandrum, sometime. It's a great honor for us.
Well, you're very kind. Thank you.
Our December conference we scheduled during 11 to 14, December 11 to 14.
Yes.
Yeah. And sometime next year also there, but in between, whenever time and convenience comes, okay, you please consider.
That is very kind of you. Thank you so much. I am trying to travel less.
Okay.
During the pandemic, I learned I did not need to travel as much as I was traveling. And in fact, I think it's time for me to sort of cut back on a lot of my activities. But I certainly appreciate your good opinion.
Okay, okay, okay. Okay. How is the corona such things are fully eradicated there?
It's not fully eradicated. I still encounter people who have the COVID virus. I get a booster about every 6 months, and that seems to work. I've had COVID once.
Yeah.
It was miserable, but not terrible. How about you, Satish
Here,
Kumar?
I have taken two COVID vaccines, two second vaccine, not up to go up to third time, but here it is not much, very less. But somewhere there is reporting for a situation.
Oh, really?
Yeah, yeah.
Namaskar, namaskar.
Hi, namaskar, Professor. Namaskar. Professor Narendra Kumar joined for, he's the chair of the session. Very glad to meet you.
It's a pleasure to meet you too.
Oh, you're welcome, sir.
Thank you so much for chairing the session. I really appreciate it.
Yeah, thank you. So still time is there, another about 5 minutes.
Yes.
Professor Narendra Kumar from another place was the Chandigarh or Punjab, northern side of India.
Mhm.
The temperature is entirely different there.
Totally.
Yeah.
Hmm.
There is extreme climate also in Punjab usually.
Obviously.
Low temperature, high, yeah. Isn't
Yeah.
it? What about now, Professor?
Now these days it is raining.
Yeah,
So
yeah, very much.
yeah, temperature is a bit down, but otherwise it goes right up to maybe 46, 48 degrees.
Okay, okay.
Oh, that's hot. Okay.
It's very hot. But today or yesterday there is some relief because of rain.
Okay. In Kerala, it is maximum 35 will come. Maximum, right?
Right.
Will not go more than that usually. Temperature.
I'm in New York City right now, and we had very hot weather up until 2 days ago, and then it just completely broke, and everything became much, much cooler. But in these times, we have to expect extreme weather and very unusual patterns.
Okay, okay. Here in Kerala, the low temperature up 19 degree or 18, that much level. Not lesser than that.
That sounds very acceptable. Hmm.
So Professor Banks is from Durham. So this is Duke University. Huh?
It is Duke University, and as you can see, you have the Gothic script there to write Duke.
Mm-hmm. So earlier I thought of that you are from the University of Durham because there is a Durham University also. So when then later I saw it is Duke University Durham.
I visited the University of Durham. It's a very nice place. They have a lovely river that goes through the city, the Weir, and it's a lovely place.
Mm-hmm. That is in UK. That's in UK.
Yes. By any chance, do you know Frank Coulon, who teaches at the University of Durham?
Yeah, Frank Coulon is there. Yeah, I know him very well. So,
isn't he a wonderful man? I really like him. I saw him just a few weeks ago at a retirement party for Sat Gupta, and it was just wonderful to see Frank coming all the way from the UK to participate in that retirement party.
Frank P. Coulon.
Okay.
Yes.
And his wife is also there, Tahani, Dr. Tahani.
Yes, that's right. Yes, Tahini. Yes, she's very nice. She did not come to the retirement conference for SAT, and in fact, I believe they have 2 young children now, right?
I don't know because it was his second marriage, and I don't know exactly. I never asked him. So
I know they have at least one child. I think they recently had a second one.
Maybe. So because I arranged this lecture, 2-3 months back, and even though I know him from last 20 years, but I never asked him about the kids and all that.
Well, how did you meet him, if I might ask?
Sure.
May I ask how you met Frank?
Pardon?
I was asking, you say you've known Frank for 20 years. Where did you meet?
I never met him, but we are meeting, largely virtually. Because he invited me to visit there on a certain fellowship at one point in time, but due to certain administrative reason, I was not able to go. But he did invite me to visit that place. I too invited him, but again, due to his issues with family affairs and all that, because as I said, her dear wife had cancer and all that.
Yes, I know about that. That was very sad.
Yeah.
Yes.
Okay, Professor. Yeah. Okay, now let us move to the session if it's okay for you. I think Anjana,
Yes, sir.
please introduce the chair and invite the chair to run the session, and you also support this chair for whatever you need. Please.
Okay, sir. Good evening, everyone. It's my privilege to welcome you to the ninth technical section of the 10th International Webinar on Recent Trends in Statistical Theory and Applications. To commence this section, I am delighted to introduce our section chair, the distinguished Professor Narendra Kumar, a senior and highly reputed academic in statistics. Professor Narendra Kumar serves as professor and chairperson of the Department of Statistics at Punjab University, Chandigarh. With over 30 years of technical and research expertise, he has significantly influenced the academic and research direction of the department. His research spans statistical inference, specializing in non-parametric methods, multiple comparison procedures, order statistics, and adaptive testing. We are truly honored to have him give this section. It is also my pleasure to introduce our keynote speaker, the renowned Professor David Banks from Duke University, Durham, USA. A versatile statistician, Professor Banks has made substantial contribution across dynamic network analysis, human rights, statistics, and data-driven policy. His distinguished career spans academia, federal agencies, and policy research, earning him prestigious accolades, including top honors from the American Statistical Association. His leadership in editorial roles and institutional initiatives highlights his profound impact on social computation and applied statistics. Today's keynote is particularly meaningful. It honors the legacy of the late Professor J.K. Bosch, a luminary in statistical theory and practice, a former director of the Indian Statistical Institute, and a professor at Purdue University. Professor Bosch was a celebrated scholar whose work continues to influence modern statistics. We are honored to have Professor David Banks with us and eagerly anticipate his lecture. Without further delay, I now invite Professor Narendra Kumar to take off as chair, section chair. Over to you, sir.
Right. Thank you so much for the introduction. So, first of all, I would like to welcome Professor David Banks to to the technical session 9, which is a keynote session in the honor of Professor J.K. Ghosh. So, because he has already been introduced, but let me further elaborate on his, on his introduction. So, Professor David Banks is presently working as Professor of Practice at Professor of Statistics at Duke University, Durham, North Carolina. His research interests include, computational models for computation, dynamic text networks, reversal risk analysis, human rights statistics, agent-based models, and certain topics in high-dimensional data analysis. Professor David is a prolific researcher and has published over 100 research articles, 8 monographs, and 9 edited books. He is also providing or has provided his professional service as a reader, co-editor, coordinating editor, associate editor of several reputed journals such as Harvard Data Science Review, Springer Series in Data Sciences, Journal of Statistical Theory and Practice, Journal of American Statistical Association, Electronic Journal, and many others. Professor David is also the fellow of ASA and the American Association of the Advancement of Science. In addition, he is received many honors and awards. There is a long list. He also has experience of working as a chief statistician of the U.S. Department of Transportation and U.S. Food and Drug Administration as a lead statistician for counter bioterrorism. All in all, we have amongst us a very accomplished researcher and practitioner of statistics amongst us. And now I invite him to kindly deliver the keynote talk. Thank you. Over to Professor David Banks.
Thank you for that handsome introduction. I certainly appreciate it. Professor Ghosh was an amazing human being. He was an absolutely brilliant statistician, but if you spent any time with him at all, you realize that he was a deeply kind man, a humble man, and I'm very honored to speak in the session in his honor. Jayanta was a generation older than me, but we interacted in various ways over many years. He, of course, was the PhD supervisor for my colleague, Shurja Takdar. And I did not know this until recently, but I found out that he was also the advisor for Jogesh Babu. And I'm delighted that my good friend Jogesh is also speaking in this conference. So it's a great honor to speak in the J.K. Ghosh section. I'm going to be talking about adversarial graph traversal, but I think it is helpful to begin with a review of the non-adversarial graph traversal situation. In graph traversal, a traveler moves through an undirected graph with a known structure. And the traveler knows where she is in the graph, and she knows what's connected to what. And as she moves through the graph, whenever she crosses an edge, she pays some unknown cost. And when she reaches a node for the first time, she receives a payoff. And her goal is to maximize her net reward. And that means that she stops moving when the expected value of any further traversal is going to be negative. So this strikes me as a nice choice for a topic in honor of Professor J.K. Ghosh. Professor Ghosh's career started with sequential decision analysis, and of course, he is one of the heroes of Bayesian statistics. And so here we have a sequential decision problem that we're going to structure in a Bayesian way. And so it aligns with several of Jayanta's interests. So the root choice is a sequential decision problem, and as a practical matter, it arises when you're trying to do logistics, routing trucks to deliver things. It arises in portfolio management, where you try to rebalance your portfolio as the world changes around you. And finally, it also arises in things like planning your career. Do you get a job at Google or do you get a job at Meta? After you've been a couple of years at Google, do you move to LinkedIn or do you do something else? So those are the types of real-world problems where this sequential decision-making arises. And optimal traversal is an NP-hard problem, even if the cost and payoffs are completely known. So it's a complex optimization problem, and Caballero et al. have addressed the non-adversarial problem. We imagine that the traveler is Bayesian, and she has a normal inverse subjective distribution over the edge costs, C1 to Cm, and the rewards R1 to Rn. And so we have this random vector that's R and C composed together. And so the total dimension is going to be N plus M, where N is the number of nodes and M is the number of edges. And we assume that this random vector X has the normal inverse distribution. And for each path that she considers, she uses her subjective distribution to maximize her expected net income. And after each traversal, she observes an edge cost and a reward, and she conditions on those to modify her subjective distribution. I will note that this aspect is not quite Bayesian. It's conditioning, not Bayesian. But that's a technical distinction that may not matter very much. Here are two results that make our computation much easier, and they were surprisingly hard to find in the literature. One is if you integrate out sigma in the normal inverse Wishart distribution, you get a multivariate student t distribution. That's not a surprise, but it was really hard to find it proved in the literature. The second theorem that we need is that the normal inverse Wishart family is closed under conditioning. So if you observe an edge cost and a known payoff, and you condition on those, your new subjective distribution over the unobserved edges and the unobserved nodes is still a normal inverse Wishart distribution. Oh, and I will mention, I had to prove the second theorem myself. I could not find a citation for it after a rather deep dive. And I used GPT-4 and I prompt engineered it to actually come up with the proof using the Schur complement to get the results. And I was really impressed that it was able to work out a non-trivial technical result. So I've talked about optimal graph traversal when there is no opponent, but now imagine that you have an adversary. And after each edge traversal, the adversary can reduce the payoff at one of the traveler's adjacent nodes. And this is the type of situation that arises in Stackelberg games. It arises in corporate competition. You have Coke and Pepsi, and each year Coke and Pepsi decide whether they're going to invest in a new product line, whether they're going to try and open up a new market. They look at what their opponent has done, and they're going to try and maximize their advantage against their opponent. It also arises in counterterrorism. The terrorist will choose a target and attack it. The counter-terrorist will decide what to do next. And so you have a sequential game in which you have an opponent who is trying to reduce your payoffs. We can imagine that the adversary is either a level 0 thinker or a level 1 thinker. A level 0 thinker is myopic and greedy, and so they are going to reduce the reward at the most beneficial adjacent node. The level 1 thinker reasons that the traveler is going to try to anticipate that the best node is going to be reduced, and so the traveler will take the second best expected payoff. It gets a little bit complicated, but this level 0, level 1, level 2 thinking has been studied for a while now, chiefly by Stahl and Wilson. The traveler, of course, does not know whether her opponent is a level 0 thinker or a level 1 thinker. And so she has a beta prior on her opponent being level 0. And then 1 minus that probability is the probability that the opponent is a level 1 thinker. We're going to solve the traveler's problem using a technique called adversarial risk analysis that was developed by David Rios Insua and his collaborators back in 2009. Adversarial risk analysis is a decision theoretic alternative to game theory. So instead of finding an equilibrium solution, one has a model for the way an opponent reasons, and you choose the action that maximizes one's expected utility against that model. And we're going to put some math on this, but let me first say that this is actually a very natural way for people to act. If you are asking your boss for a raise, you have a mental model, a subjective distribution over what your boss values. If you think that your boss values punctuality and paperwork and protocol, and you're correct, then you have a very good chance of making a pitch to your boss and actually getting a raise. But if your mental model for your boss is wrong, and the boss actually values how much money you bring into the firm, how many clients you have, how many people you supervise, then you're probably not going to be able to successfully make a case for a raise because you completely misunderstood the criteria that your boss uses to evaluate you. So I think that the adversarial risk analysis perspective is a mathematical encoding of a very natural way for human beings to behave. In adversarial risk analysis, you're able to partition your total uncertainty into 3 components. There's the aleatory uncertainty, which is the uncertainty in the outcome conditional on the choices that the opponents make. There's epistemic uncertainty, which means that you don't know your opponent's actual utility function. You don't know how your boss evaluates paperwork, protocol, punctuality. You don't know about the available resources that the department has. Are they able to afford giving somebody a raise? And you don't know what the boss knows about you. Finally, there's concept uncertainty. We don't know how the adversary makes decisions. It may be that the adversary likes game theory and is trying to find a min-max solution. It may be that the adversary is a level 0 thinker or a level 1 thinker. We don't know those things. In our case, the traveler has a subjective distribution over all the different sources of uncertainty. So in our case, the aleatory uncertainty arises because we have a normal inverse Wishart subjective distribution over the costs and the rewards. And that's the payoff conditional on what the opponent does and what the traveler does. There's epistemic uncertainty. The adversary knows the true costs and the true rewards associated with the graph and can penalize an adjacent node by 20%. But the adversary doesn't know what choice the traveler is going to make. And finally, there's concept uncertainty. And here we encode that as allowing the adversary to be either non-strategic and greedily penalize the best adjacent node, or a level 1 thinker who is strategic and who penalizes the second best node. So for each adjacent node I, define the original net payoff before any possible reduction occurs as being delta I, that's the reward at node I minus the cost of traveling to node I, and the joint predictive distribution over the k neighbors of your current node is going to have a multivariate t distribution. Because the adversary may or may not penalize each adjacent node, the observed payoffs have two possible scenarios. One scenario is that the node I is penalized by the adversary by 20%. So the actual observed payoff is going to be 0.8 times the reward minus the edge cost. Alternatively, it may be that node I is not penalized by the adversary. In that case, the observed reward is the full reward for node I minus the edge cost. Let omega sub I be the probability that the payoff at node I has been reduced. And then the expected value of the observed reward is going to be omega sub I times the expected value of the penalized reward plus 1 minus omega I times the expected value of the full reward, where the expected value of the full reward is going to have the multivariate t distribution, and the expected value of the penalized award is going to have a rescaled multivariate t distribution, or a rescaled t distribution. And so the traveler, well, she is going to select I star, the node to which she travels, as the thing that maximizes her expected value for the return. And that leaves the traveler with the problem of trying to determine what omega I would be. And now the traveler considers two scenarios. The adversary is level 1, which happens with probability pi, and penalizes the second best adjacent node, or the adversary is level 0 with probability 1 minus pi, and he penalizes the best adjacent node. So a particular node I is penalized under level 1 adversary if it is second best, and by level 0 adversary if it is the best. And so we're going to let Q1 sub I be the probability that delta I is the maximum over the expected payoffs, and Q2I is the probability that is the second best among the expected payoffs. So the omega I is going to be the expected value of pi times Q sub 2I plus 1 minus the expected value of pi times Q sub 1I. And you'll recall that we had a beta distribution over the probability of the adversary being a particular type. And so the mean of the beta is going to be alpha over alpha plus beta. And so omega I is going to be alpha over alpha plus beta times Q sub 2I plus 1 minus alpha over alpha plus beta of Q, times Q sub 1I. So the traveler now chooses where she's going to go, and she traverses that edge, reaches that node I, and she observes a payoff x sub I. And so that's going to be the net benefit, which is the reward minus the edge cost. But she does not know if the reward she receives is the base node reward or a value that's been reduced by, say, 20%. So now the traveler needs to update her beta distribution. The probability that the adversary is type 1. And so we're going to place the alpha and beta by a fractional update, alpha plus gamma and beta plus 1 minus gamma, where gamma is the probability of level 0 given the observed reward. And it turns out that this gamma is going to be this quantity shown here, and f of xi is the predicted density evaluated at the observed CI and RI combination. F of x sub IR is the predictive density evaluated at the true values with a rescaled R sub I to account for the possible reduction in the reward. And then we substitute the prior mean alpha over alpha plus beta for the pi. And that allows the traveler to evaluate gamma and update beta prior on the adversary. Since the traveler cannot tell if xi is the reduced value, then after the first step, her conditional distribution of the remaining costs and rewards is a two-component normal inverse mixture. So after we observe the reward and costs from traveling to node I, then she has a distribution over the remaining costs and rewards. It's going to be equal to omega I times the predictive density for the rescaled. That's if she thinks that the node has been reduced, plus 1 minus WI if she thinks the node has not been reduced. So now she has this new distribution, and the omega I has the same form as before, except now the expected value of pi is calculated from the updated beta distribution, and the predicted distribution over the true values of the unobserved components is a two-component multivariate t distribution. And if you think ahead a little bit, you'll see that after t steps, the traveler distribution is a mixture of multivariate t distributions with two raised to the t components. And for large networks, it's going to become computationally challenging. And what we do is use regularization. We set to 0 the components that have very, very low weight. Which I guess brings us to our simulation. We're going to have a 6x6 grid that's generated in accordance with the traveler's subjective distribution. And the adversary is truly, in this case, the adversary is a level 0 greedy, myopic opponent. And we imagine the traveler has a beta 1-1 distribution over pi. And so the traveler starts down here at this corner always, and she makes the best choices based on her subjective distribution. When there is no adversary, her cumulative net reward is 56.56 for this particular realization. So the edge costs and the node rewards are randomly generated. I'll tell you more about that in a moment. But when there is no opponent, then she gets a very nice net reward, 56.56. If there is this level 0 greedy opponent, but the traveler does not take account of trying to model for that opponent, then she's penalized very heavily. Her cumulative net reward drops to 29.63 as opposed to 56.56. If, however, the traveler knows that there's an adversary and uses the protocol that I described earlier, then she does much better than ignoring the adversary. Her net reward is now 41.24. So she does much better against the adversary when she directly uses an adversarial risk analysis model to try and model the decision making of her opponent. Our simulation study is a 3-factor analysis of variance, and the factors are, first, a level 0 versus a level 1 opponent, whether the opponent is greedy or strategic. Secondly, the factor is whether or not the traveler's subjective distribution is pessimistic, accurate, or optimistic in terms of the mean function. If the traveler is pessimistic, then her mean function for the rewards is an underestimate of the truth. If she's optimistic, then her mean function for the rewards overestimates the true mean function for the rewards. And if she is accurate, then her expectation for the reward at a node is, in fact, correct in expectation. The third factor we consider is 3 different search strategies that the traveler uses in order to determine what her next step is going to be. And I'll talk more about the 3 different search strategies in a moment. In our simulation study, we generated 100 6x6 grids with payoffs and costs as shown on the previous slide. And if we assign Cartesian coordinates from 1, 1 to 6, 6 to the 36 nodes in this images, then the node corresponding to the Cartesian coordinate xy has an expected payoff of x plus y, and the edge linking x1, y1 to x2, y2 has an expected cost of the average of those values, x1 plus x2 plus y1 plus y2 over 4. The covariance 0.5 raised to the 2 times d sub 1, 2 minus 1, where d sub 1, 2 is the difference in the x components in absolute value plus the difference in y components for the absolute value. And basically what this means is that nodes that near each other are more strongly correlated than nodes that are distant from each other. I have not laid out what the correlation among the edge cost is, but it has a similar spatial structure. Edges that are near each other are more strongly correlated with their costs than edges that are far away from each other. And for all these costs and all these payoffs, the joint distribution is going to be a multivariate normal. The pessimistic traveler has the correct covariance function, but her mean payoffs are 10% below the true values. The optimistic traveler has means that are 10% higher than the truth, and the accurate traveler has mean functions that are equal to the truth. And I will add the pessimistic traveler, these travelers don't actually know the correct covariance function, rather they have the same normal inverse Wishart distribution over things, and the mean of the normal inverse Wishart is in fact the true signal. That probably sounds a little bit more complicated, but I hope the big idea sort of gets across. We're doing an analysis of variance of a 2 cross 3 design, and we're trying to understand what the effect of the type of the adversary is, what the effect of the optimism, pessimism, or accuracy of the traveler is, and what the effect of the 3 different search strategies is. And we compare these 3 search strategies. There's greedy myopic search, in which you try and pick the node that's going to be the best node according to your expectation. There's the H-path search, which considers all paths of length 3 and tries to find the path that maximizes the net reward for a 3-step path. And this is used by Caballero et al. In their 2025 paper in decision analysis. And finally, we propose a search depth policy. And the search depth policy is myopic when the observed payoffs are far from what the traveler expects. But as the difference between the expectations and the observations becomes smaller, longer paths are explored. So if the traveler is pretty clueless and is observing rewards and costs that are far from what she expects, then she's very conservative and she only looks at the adjacent nodes and takes the one that has the highest expectation for her. If the rewards and costs are a little bit more in line with what she expects, then she might look for two-step paths. She will consider nodes that are 2 steps away from her current node, and she'll try and find the best path of length 2. If the observations are very close to what she expects, so she's not being surprised at all, then she'll consider longer paths and might look for paths of length 3 or even 4. That's the search depth policy. So we generated 100 6x6 grids according to the multivariate normal distribution previously described. And for each grid, we used all 2 × 3 × 3 combinations of factor levels and recorded the net reward that the traveler received. It took about 2 days to complete this simulation, but we really weren't trying to optimize the computation. If we regularized the mixture components and we took advantage of other computational shortcuts, I think we could really reduce the time. There's a particle filtering approach that we could use that might work very well. The analysis of variance found that there were interactions between the pessimism, accurate, and optimist factor and the level 0 versus level 1 factors. All the main effects were significant. We did not find a three-way interaction. So it looks as though things are actually fairly simple. It's not a surprise that there would be an interaction between the pessimism, accurate, and optimist factor and the level 0 versus level 1 factors, because basically trying to learn about the type of thinker that her opponent is. And that gets confounded with what she believes are going to be the true costs for the node payoffs. In our simulation, the best search strategy was the H-path search strategy with a strategy that looked 3 nodes out. I don't believe that is a durable result. I think that under different circumstances, the search depth policy is going to prevail, and if we did a more athletic simulation, we would probably find a way to demonstrate that the depth search policy has desirable features. I'd like to unpack some conclusions. First of all, in the spirit of Jayanta Ghosh, this work takes a Bayesian approach to a sequential decision problem. And this sequential decision problem arises in many different ways in practice. And so I think it's a nice contribution. The adversarial risk analysis framework extends previous work on graph navigation to the case where the traveler has an opponent. And you can have more complex ARA frameworks than what we described here, but this is the simplest version that fully exercises the features of the model. And I would argue that this formulation abstracts a fairly large class of real-world problems, but I wish I would have had a more concrete application with data. But to give you an idea of the type of situation that could arise, imagine you've joined a large company, you are trying to rise, you can try to navigate to join this team, another team, a third team, and you have a rival who is trying to get promoted ahead of you. And that rival can do things that will reduce the apparent quality of your work. And that's not an absurd situation. I've seen it happen in practice, but I don't have a data set that would really flesh out the specifics of that type of modeling. This is joint work with Elvin Chan and Leah Johnson, both at Auburn University, and with my PhD student, it's with Elvin Chan and Li Zhu at Auburn University, and my PhD student, Leah Johnson, at Duke University. And it was supported by a grant from the U.S. Office of Naval Research. And I see that I have ended much earlier than expected. So apologies for that. Let me stop sharing and maybe take a few questions. Professor Kumar, thank you very much for chairing this session. I should mention that this is building out on work. A few years ago, I gave a talk on adversarial risk analysis in general at this very same conference. And it was a great pleasure to do so. And I am delighted that I'm now able to share with you the more recent extensions of that work that try and carry it forward. The graph navigation problem is something that is becoming, I think, a little bit more sexy than it was back 10 years ago. It's related to something called the Canadian traveler's problem, the traveling salesman's problem, and then this graph navigation problem that the Office of Naval Research is interested in. They have funded my work. They funded some work by Caballero et al. And there is a growing literature on trying to navigate a graph in some optimal way when there's uncertainty about what's going on. The graph navigation problem is inherently hard. It's NP hard, so there is not going to be any pure solution. But there are heuristics that seem to do a pretty good job of helping one move ahead in a sensible way. And since I have time, I will add that the next step that I intend is to move beyond the level 0 and level 1 opponent to instead have an opponent who does not have perfect knowledge about the costs and the rewards in the graph, but rather has a subjective distribution over those. And both the traveler and the adversary learn about the graph as the traveler progresses. They observe the costs, they observe the rewards, they each condition or update their subjective distributions and make choices that correspond to what they're learning. And this corresponds to something that I called a mirroring equilibrium in the talk I gave a few years ago on adversarial risk analysis. It's an alternative approach to the level 1, level 0 thinking that I described here. But that's work in progress, and we haven't completed that yet. Let me pause now and see if anybody has any questions. I turn it over to the audience.
Right. Any query, any question, or any comment, please?
I apologize for finishing a little bit early. This is the first time I've given this talk, and so I probably didn't time it out properly.
No, it's okay. It's okay. Not an issue. So I have a query for you.
Thank you.
So in the 6x6 grid situation you have undertaken, right?
Yes.
So it is traveler is placing beta 1-1 distribution over pi.
Yes.
Right. So, but beta 1-1 distribution is just a uniform distribution.
Yes.
Right. So, and if we change the parameters, so the results would be similar, or they might be a bit different, or what is likely to be there?
I'm sure it would be different. The beta 1-1 distribution says that the traveler thinks it's sort of equally likely that it's a level 0 adversary as a level 1 adversary. As she begins to move through the graph, she's going to learn about what type of opponent she has. She's going to be getting information about whether it's a level 0 or a level 1 adversary, and she's going to update her beta prior. And so if it's a large graph and there's lots of time, the uniform distribution is going to learn the adversary's type and concentrate on either a level 0 or a level 1. And so I think that the uniform is sort of the natural starting point in a situation like this. There's work by Stahl and Wilson, who did an empirical study of college students in a certain category of games. And what they found was that very few people were more than a level 1 thinker. Level 0 and level 1 were pretty common. Level 2 was rare. And except in certain highly structured games like chess, it was unusual for somebody to try and think 10 moves ahead. That wasn't the way human beings worked for the types of games that they considered. I see that we have a question. Thank you so much.
Right, and you said that it takes 2 days to have simulations of the order of 100. I mean, there is a lot of complexity in computations.
What's driving the complexity is the fact that we have a mixture model. So it's a mixture of t distributions. So her predictive distribution for the future rewards and costs is going to be a mixture of multivariate t distributions, and that's going to have 2 to the t components after she takes t steps. So that actually grows combinatorially fast, and that takes up a lot of memory and is just a pain. On this first pass through, we did not try to optimize the computation. We just did it as best we could. I turned it over to the graduate students, and they did it. If someone's life depended on doing it fast, I'm very sure we could come up with computational shortcuts that would work very much better than what we did. Professor Kumar, I believe I saw that somebody had raised a hand. Are you able to unmute that person and let them speak?
I think that organizers will be able to do it if they have, I mean, those kind of permissions they can get. Is there anybody who has raised hand? He or she can ask the question?
Well, I saw a hand go up, but perhaps it was a false alarm.
Right. So anyway, so I have one more query. So as Wishart distribution has several properties. So sum of 2 Wisharts is again a Wishart. And if you pre-multiply and post-multiply, it is again a Wishart. So similarly, NIW also has all those properties that just for my knowledge.
Yes. And those represent potentially interesting extensions of what we're trying to do. We're aiming this paper for the journal Decision Analysis. That was a journal that published the Caballero paper, and so we hope that they're going to be interested in something that builds out the Caballero paper in a different way. There are a lot of things you could do with this, and I don't want to get down in the weeds on this. I think the big concepts are what's going to matter. Certainly in a conference talk, you want to stress the big ideas rather than get into the weeds. David Donahoe once said that talk is an advertisement for the paper. You don't want to prove things. You don't want to get into details. Instead, you want to make somebody go and read the paper so that's where they would study the details. From my perspective, at the high level here, what we have is a sequential decision problem in which you don't know what your rewards are going to be and you don't know what your costs are going to be. So that's very much like being an undergraduate. You are signing up for courses in college, and you could take a history course, you could take a math course, you could take a computer science course, and those are going to have different costs. It may be that the math course is really hard. It could be that the history course is really easy. So those are the costs, but you also get rewards. Taking the math course might open the door to a future career. And so that's a very nice reward. And we've extended that sequential decision problem to the case in which there is an opponent. It may be there's some classmate who is trying to cheat off of you or otherwise, make himself look good while making you look bad. It's sort of an arbitrary, contrived example, but it's not completely unrealistic. And there are many, many cases where there, in fact, is real competition in sequential decision-making with uncertainty. And what we're trying to do is to create a framework in which somebody can begin to formally analyze that type of situation.
Right. Anyone, please, one wants to clarify something? I think there is no further query.
Thank you very much. It's been an honor.
Rather, I must thank you that you had a very interesting talk. So we all are greatly benefited with your keynote address. So thank you very much again.
Thank you.
Over to Professor Satish Kumar, please.
Thank you, Professor. In fact, very, very excellent and informative talk. In fact, Professor Narendra Kumar raised questions and make it a more vibrant and more useful one. In fact, several are asked.
He was very good, and I appreciate him weighing in with questions. That was nice.
So because there was a time, so I have taken you to the full time. So it is almost 35 now.
Yeah. In fact,
So there is no
we plan to have a little more time in between because sometimes some people ask questions and that will be beneficial too. It will be beneficial then only these deliberations have a more value. That's why in between we have placed some time. So a great, very wonderful talk, and we are grateful to you, Professor.
Thank you so much.
Thankful, and also Professor Narendra Kumar for chairing the session in a very nice way. And thank you, Professor David Bhai. So in fact, we are very much grateful to you. We hope you will come over here to Kerala.
You're very gracious. Thank you so much.
Yeah. I hope there is no other anyone has to interact. Anyway, not asking questions, but you can interact if you want. There's a great chance. There is any students you want to say anything to? Professor Ghosh, the yeah, Professor Golam Kibriya, you are here. Okay. Do you want to say anything in this context? Yeah, you have to unmute it, Professor. You have to unmute your mic.
Oh, sorry. Thanks a lot, Dr. Kumar. I am not in Miami. I am driving a long trip.
Oh.
So
Yeah.
I'm attending through the email, internet, cell phone. And it is very nice presentation, but my presentation, my student will present the paper, Mr. Naim.
Okay.
He will be present soon, probably. Yeah.
Okay. So, in fact, we are waiting for the.
I think my presentation is right now, right?
No, Professor. After the next session. After the next session.
Okay.
That,
No problem.
8:35. Yeah. 8:35.
Yeah. Okay. Thank you.
Now it is 7:36 only. Okay. And
okay.
Time. Yeah. Whether Naim is your student?
My student is Naim. He will present the paper.
Okay. Sorry for not adjusting that time. In fact, that was missed by us. And several all the talks are tightly scheduled. That's why you couldn't.
Yeah, no problem. We have another few minutes. Yeah.
I hope the Professor K.K. Joseph, whether you joined here.
Yes, I am here.
Okay. Professor Carlos Coelho, I hope earlier he. Yeah.
Yeah. Okay.
I think we let us wait some more time in between because some people has to attend in particular. In between, you can say something. Do you want to have
Professor Carlos, I have been to Lisbon in 2007 for the ISI conference.
Yeah, nice seeing you here.
Conference.
Yeah, it's good to see you here, and
in
thank you for sharing this session.
In 2007. So ISI biennial conference was hosted at Lisbon.
Yeah, it was in Lisbon, 2007.
Okay.
I did not attend that one actually.
Okay.
I just had a family problem there and I could not attend it.
Your areas are biostatistics, multivariate, isn't? Biostatistics, multivariate analysis. Your areas.
Sorry?
Your areas are multivariate analysis and.
Yeah, mainly that one, and also linear models and stuff like that, and generalized linear models, but mainly multivariate analysis. Yeah.
Okay, sir.
It maybe I can try sharing my screen to see if it works. Do you think
Yeah,
so?
yeah, bro. Yeah, sure.
Okay, let me see if I can do it the right way. So. Always I have some difficulties with this because
the bottom there is a upward arrow. Yeah.
I'm selecting a window, but now why I cannot share? Always have some problem with this.
I don't know. Yeah, if it is difficult, we can share it from here. No problem.
I think you should open your
Yeah. Try to
slides on your desktop, and then go back to the Google meeting and press the button that looks like a monitor that's in the middle of the screen and it has an up arrow.
Yeah, I did it, and so I get the window.
Now it is going.
Now it is going to Outlook. I don't know why. But I get the window.
Use the other option, press enter screen.
Yeah, I also have a problem with. Okay, now it should work. I hope. Okay, is it working now?
Yeah, it is working now.
Very well.
It is fine first. It's now fine.
Okay.
Yeah.
It's okay now, right?
It's okay.
Yeah,
now
if
it's
I
fine.
if I put it in full screen, I don't see you anymore. Yeah. So.
Okay.
We can see you. We can see your slides.
That's right. In full screen, you cannot see the audience.
Yeah, that is the point. Yes, I'm not so much used with this one. I'm more used with Zoom. But yeah. Okay,
it's
so
fine.
but
It's
anyway,
fine. It's fine.
Yeah, better go full screen later on.
For us, it is fine.
I think you can kept it. No need to change. It can move in that way. So whether you check whether it's moving or not.
If it is okay for you, if you can see well, actually at some point in time, I will need to go out of screen because I need to show half of one slide, half of the following. So
it's okay.
So if this way it is okay for you, it's okay for me also.
It's okay. I hope it is okay. Everyone. Okay. Abhiya?
Yes, sir.
Yeah, you please introduce the chair and support the chair to run the further proceedings of this. Let us move.
Good evening.
By the introduction time, we can take the without wasting the time. Please.
Okay. Good evening to all the respected delegates, researchers, and participants. It is my pleasure to welcome you to the plenary section of the 10th International Webinar on Recent Trends in Statistical Theory and Applications. We are honored to have this section chaired by Dr. J.K. Jose, Professor at Mahatma Gandhi University, Kerala, India, a renowned academician and researcher in the field of statistical modeling. His recent publication titled Autoregressive Processes for Financial Modeling, Recent Developments reflects his deep expertise in time series analysis and its applications in the financial domain. We are also privileged to welcome our plenary speaker, Professor Carlos A. Coelho, from the Nova School of Science and Technology, University of Lisbon, Portugal. Professor Coelho is a distinguished scholar known globally for his outstanding contributions
to multivariate statistical analysis, distribution theory, and inferences methods. His work has had a far-reaching impact on both the theoretical advancement and applied research in statistics. We look forward to a stimulating section ahead. Over to the chair to take the section forward.
So, thank you for the nice introduction. Now, our speaker is actually Professor Dr. Carlos Manuel Colge. He is from Nova School of Science and Technology, Nova University of Lisboa, Portugal, and he is a full professor in of statistics in the Department of Mathematics. As far as his areas are concerned, he has a PhD in biostatistics from the University of Michigan, USA, while he was a Fulbright scholar. And his main area of research is multivariate analysis, likelihood ratio tests, multivariate analysis of various models, and their distributions. Then, related to this area and other areas of interest in mathematical statistics and distribution theory, he had worked in estimation, univariate and multivariate linear models, generalized linear and mixed models, etc. And he had over 100 publications, and he had been associated with many reputed international journals, and at present he is an associate editor in the editorial boards of various statistics journals. He had published more than 100 research papers in various journals. And today he will be speaking on profile analysis for high dimensional situations. A very hearty welcome to Professor Carlos Coelho, and request him to deliver his talk. Thank you.
Thank you very much. Thank you very much, Professor José, for this nice introduction. Thank you very much, Professor Satish Kumar, for inviting me and preparing this nice meeting for us. So I'll be talking about profile analysis for the high-dimensional case. It means in situations where the number of observations is smaller than the number of errors. Actually, some part of these the two first tests, I had presented them before at another meeting at University of Kerala, another online meeting. And so I'll be focusing mainly on the test for horizontality. It may look like as being the less important one, but what happens is that, sorry, I'm not being able to move my slides for some reason.
So can you make it full screen? Then it will be easy, I think.
Yeah.
It is moving.
Yeah, it's okay now, right?
One by one, you have to move that.
Yeah, okay.
Just to drag down, only that way. Now it's abstract.
Yeah. It maybe I could go full screen. And is it okay for you?
Now it is okay. It is okay.
Okay.
And so,
okay. And so, as a full profile analysis, I'll be showing the test for the profile parallelism, the test for coincidence, assuming the parallelism, and finally the test for horizontality, assuming the coincidence. And it will be on this later one that I'll be focusing mainly, because although it is a test that only sometimes it makes sense, it only makes sense actually if all the variables are measured on similar units. Anyway, there is a very tricky problem when getting the distribution of statistics, of the associated statistic. So, for all three cases, I'll be showing the associated statistics and their distributions, and very quickly how we can obtain them. Actually, for the two first tests, there is a publication we have that you can also refer to. As I said, the two first tests, they were already presented at ICSTC 1 year ago, 2024. And so I'll be just running a little bit over them, and I'll be focusing mainly on the last one, on the third of the tests. That is because there are some nice tricky problems about getting the distribution of statistic. First of all, as an overall thing, how can we do a likelihood ratio test with a sample size that is smaller than the number of variables? Usually people think it is not possible, but it is really if we just get a covariance matrix that has such a structure that you can specify with a very small number of parameters. It means instead of assuming what is usual, only that covariance matrix is positive definite, I'll be assuming a particular structure for it. It may look like it is a very stringent limitation, but it happens that in practice we can use it for any kind of covariance matrix without any problem really. So covariance matrices, I'll be assuming they have circular, symmetric circular structure that is a structure like this one. We just have on left side the case for p equal 5, on the right hand side for p equal 6 variables. And so they have this kind of diagonal band structure. Carlson and Kra and Simanka, they showed that actually the circular matrices form commutative algebra. This is very much important because it means, together with other results about likelihood ratio testing and likelihood ratio estimation mainly, it shows that we can estimate the parameters one by one just from the non-structured covariance matrix, assuming the places where the parameters they should be equal, and you can just average those positions of the non-structured MLE and just get the MLEs for the parameters in the circular structure. This is very nice because it makes the estimation much simpler and much faster also. And also the structure, the circular, symmetric circular structure has as particular cases two important ones that are the equicorrelation and the equivariance structure and also the spherical structure. And so it is not that much of a limitation if we just assume a circular structure. Moreover, if you then use just positive definite covariance matrices for the tests, anyway, the type 1 error will be very good. It will not be inflated usually. And so let us start with the test of parallelism. H0 may be written in this way, where C is this matrix. This is actually a contrast matrix. And so the hypothesis of parallelism may be written in this way. This is because if you get a drawing like this, and so if you just assume the profiles are parallel, it means that this C mu k, they should be all equal. And so we should be able to really write the null hypothesis in this way here. So how can we get the likelihood ratio statistics in this case? It is actually done in a book that I wrote with Professor Barry Arnold, and so I'll be mentioning it a little bit later. But so we just need these usual matrices, A and B matrices that are actually the sample products of the within and the between sample covariance matrices, where SK is the sample covariance matrix, and so X bar K is the sample mean for the kth sample, and X bar is the overall sample mean. Okay, and so we can get this likelihood ratio statistic to test for the unstructured case. This is a classical test, and so it may be found in many books in multivariate analysis, that to test this hypothesis with just positive definite matrices, likelihood ratio statistic is this one. Then we can show that to test H0, the null hypothesis of the parallelism, it is this one. We should have the matrices A and B with that C matrix. That is the matrix we saw up there. And then if you just assume that our if you just assume that the population covariance matrices are circular, we should replace A and B by A star and B star, where A star and B star are matrices with these running elements, with these HJK, J star elements that are actually the corresponding averages of the elements in A and B, where A and B are those matrices up there that are the MLEs for the unstructured case. Then we can show that, for example, determinant of A star, it may be written in this way, where this A1 and so on double star, and this double star are the diagonal elements of these matrices here, of these A double star and double star matrices, where this U matrix, it is a symmetrical orthogonal matrix with this running element here. This is done in this publication, for example, here, where it is shown this relation about the determinants of A star and C star. Okay, it is a bit intricate to prove itself, but it really holds. And then we can show that if we write Vj star, Vj double star in this way, we can show that determinant of A star may be written in this way, determinant of C star in that way there, and so the determinant of C, A star C prime, where the C is that matrix of the contrast up there, it will be written in this way. It means that the likelihood ratio statistic will be actually, it will have the distribution we just have here. I'm not sure if you can see it well because I have a part of the screen here. Okay, it's okay now. And so we can show that the likelihood ratio statistic may be written in this way, where each one of these ratios has a beta distribution. This is so because we can show this is diagonal matrix. This is if sigma is circular and this U matrix is that U matrix we saw up there, then this matrix is A double star and B double star. That are the ones, let me go back with these diagonal elements here. Then these matrices will be Wishart with a parameter matrix that is a diagonal matrix. And as such, we just get from the distributional results out of the Wishart distribution, we know that these diagonal elements of A and C and B also, that they have these distributions. A and B are independent, and so C, the diagonal elements of C that are the sum of A and B diagonal elements, they just have also a chi-squared distribution with n-1 degrees of freedom. So getting all that together, we just can show that lambda 1 that may be written in this way. This variable here, it is a beta random variable with these parameters n minus q over 2, q minus 1 over 2, where n is sample size and q, it is the number of populations that we are testing. And then these random variables here, they will have beta distributions with n minus q and q minus 1 parameters, and all of them will be independent. This also shows that to really carry out the test, we just need to have n larger than q. It means we just sample size larger than the number of populations. And so this n is the overall sample size. It means that for each of the populations, we may just have a sample size just one, and only for one of them, the size is larger than one. This in smaller case, in smaller possible case. And so it means we can carry out analysis where n is really smaller than p, and so it is adequate for the high-dimensional case. Okay, then we can show that for out p, for example, in this book here that was mentioned before, this was mentioned before. No, it is mentioned after. Okay. Then from this book that is mentioned a little bit after, we can show from this theorem, if you just get parameters in this way, that the distribution of lambda 1, it is what we call an exponentiated generalized integer gamma. It means it is the exponential of a gamma generalized gamma distribution that is a sum of independent gamma random variables with integer shape parameters. And that is nice because that distribution is all finite. We don't have any infinite sums or anything like that. It is very, very easy to really compute. If also is odd, in that case, we also use theorem to show that if you set up in this way, we also get an EGIG distribution. So also in this case, very simple distribution. What is this distribution in very simple terms? It is, we call the generalized integer gamma distribution sum of independent gamma random variables, all with integer shape parameters, these are j, and then sum has what we call a generalized integer gamma distribution. The PDF and the CDF have this form. Everything is finite in there, and so it is very simple to really compute with an adequate software, just like Mathematica, but also nowadays we just implement it in Maxima and in R also. And then if we just exponentiate it, we get what we call an exponentiated generalized integer gamma distribution. This is the notation, and that is the expression of the PDF and of the CDF in terms of the PDF and the CDF of the generalized integer gamma distribution. This distribution, the generalized integer gamma, is dealt with in this paper here, and also in this other paper here. Similar results may be obtained working through the characteristic function of W, and so I'm not going through details. I don't have enough time for this really, but we can work through the characteristic function of the logarithm of the negative logarithm of lambda to really get a similar result. Okay, that is this one here. But for LP and for odd Q and for odd Q, the distribution is far more complicated because we can get something like this that is actually similar to what we got for odd Q, but then we also get this other part because okay, this is yet for even P and odd Q, we can get a somewhat similar result. But then what happens is that for even P and even Q, it is a far more complicated situation because we get that part that is a bit similar to the other one before, but we get this part here that is the characteristic function of the logarithm of a beta distribution. And getting the two of them together is not so easy. And so we can do what we call a near exact distribution. That is, we may leave, just to go back, we may leave this part untouched, this part, the phi, the phi one, and that one, and then you just approximate asymptotically phi W2, that is a smaller part, and in such a way that the moments match. And that is what we call a near exact distribution, and so the results are very sharp for this approximation. I'm running a little bit over this because we don't have much time for it. And that near exact distribution will be actually the PDF and the CDF will be actually mixtures of what we call generalized near integer distributions that are the distributions of the sum of a generalized integer gamma and an independent gamma where the shape parameter is not anymore integer. And so the PDF and CDF have these forms, everything is finite, only this one F1 that is the two-confluent function is really a series. But anyway, it is implemented in many softwares. We just implemented it sharply in R also, and so it is rather simple to really compute and rather quick. Okay, and so we just get the near exact PDFs and CDFs with these expressions. This is the PDF of the generalized near integer gamma. This is CDF of the generalized near integer gamma that have the expressions back there. So, just an application, for example, this is a subset of a very large set of data that I had access to. And so I actually got just some values out of that very large set. And it is about humidity, about soil moisture. These are data in percentage, and this was for some place where the depth at which the humidity was measured, the moisture was measured, it was 10, 20, 30, 40, 50, 60, 80, 100, and 120 centimeters of depth. And so we get 9 variables, the 9 depth. This was at a corn plantation at the month of April, May, and June. I just selected these 3 so that I could have a small sample size. And so this is Q equal 3. This is the three samples corresponding to the 3 populations of the 3 months. And for each month, I got only 2 different days. And so I get the normal sample size n equals 6. I get P equal 9 variables, so I have n smaller than P, and I get Q equal 3 populations. These are the plots of the means for each month. And so, of course, we cannot look at the data and just infer from it. But well, if we would not reject the parallelism, we would not be shocked, right? So what happens it is that lambda 01 has this computed value for the original data with a p-value that if we would use the alpha value of 0.05, which is rather common, we should not reject H null. So we should not reject the hypothesis that the profiles are actually parallel. Okay. The point is that we are dealing with percentages because it is moisture in percentage, and so it may be better just use the sign transformation. But if you do that, the results are quite similar anyway. Okay, and so we should not reject the hypothesis of the profile parallelism. Okay, so we have been assuming, I said this before, but we have been assuming covariance matrices to be circular, but in this case they are not actually. But anyway, this is not a problem because I've done many simulations, and some simulations show that for all kinds of shapes of covariance matrices, the type N error levels, they are really very well kept. They are not inflated. And so now, if you go over the second hypothesis, the hypothesis of coincidence of the profiles, assuming that they were parallel, so what we can do, it is, first of all, we get the likelihood ratio statistic case of equality of the profiles without assuming the parallelism, and so this is lambda 2 is for the absolute the equality of the profiles without assuming the parallelism. These are the same A star and B star matrices we just had up there. We can write the test statistic in this way. And the test there, it was dealt with this book with Barry Arnold in section 5/2022. Everything is there explaining about obtaining this likelihood ratio statistic and its distribution. And then what we can say, it is the likelihood ratio statistic test equality means assuming the parallelism. The parallelism should be something like this lambda 2 just here. This lambda 2 here, divided by lambda 01, that was the likelihood ratio statistic to test the parallelism. And so if you just do the ratio, we are just left with this simple ratio here, which we have shown before. It is a bit unfair with n minus q over 2 and q minus 1 over 2 parameters. Once again, of course, we just need to have n larger than q. It means we just need the overall sample size to be larger than the number of the populations. This is a single bit random variable. It is very easy to really get the p-values with softwares we just have available nowadays. Even with R, we can get the p-value of a bit, and we get the p-value, or we can get the CDF of a bit random variable very easily. And so we can compute the statistics both for original data and for the assigned transformed data. Once again, the values are rather similar. The p-values are not that much far away also, and both of them are very small, which would lead us to really reject the null hypothesis of profile coincidence. This is not a shocking thing. Let me go back to the plot. The plot is here, and so it is not shocking that we don't reject the parallelism, but we reject the equality because they're a bit far apart. Okay. But so if we just reject H-null coincidence, given the parallelism, we should stop here. So anyway, we go to the test of horizontality. So I'll be screwing up a little bit the data, making the profiles a bit closer, so that we don't reject the equality, the coincidence, and then we could go to the test of horizontality. Of course, it only makes any sense in case. Let me see the time. So yeah, I still have 10 minutes, something like that. So in case we don't reject the coincidence, we go for the test of horizontality, which null hypothesis may be written in this way. And so we should estimate A as being the overall mean. It means the mean of all the observations. And so it should be horizontal. It means it should be an horizontal line, the graph, the plot of the population means. And so what happens it is not very hard to show that likelihood ratio statistics is for the non-circular matrices, for the unstructured case. It is something like this, where B3 is this matrix here. Okay? We just use here A hat, this sample estimate. EP1, it is a vector. It is written here, a vector of ones of dimension P. And so we can show that then for the circular case, it should be something like this, where this B3 star matrix, it is a matrix with any element defined like this. Once again, the corresponding averages of the elements of this B3 matrix, that was the matrix for the non-structured case. Then if you define C3 as being C3 star as being A star plus B3 star, we can show that the determinant of C3 star is something like this, where these C4 star JJ elements are the diagonal elements of this matrix, where this U matrix is the U matrix we saw a while ago. But now it will be a very hard problem to really get the distribution of the statistic, because what happens is, we know, and we can show very easily, that if our B matrix, that is the original B matrix we considered up there, it is defined in this way, then we know that if you just get this B double star matrix, that is the one formed from 3 star up in the beginning, we just have the diagonal elements of this B double star with this distribution here. It makes full sense because we just spent P degrees of freedom with the estimation of these means, okay? And so we get the Q degrees of freedom minus 1 on each of them, P times, because we get minus 1 for J equal 1, for J equal 2, for J equal P, and so we will split degrees of freedom here, really. If it would be the case that I was only testing for nullity of the mean vectors, the B matrix should be this B plus, and it should be computed in this way. And so I am estimating here the 0 parameters. It means I don't lose these p degrees of freedom. And so it is easy to really show that the diagonal elements of this b double plus matrix are like this, and they are chi-squares with 2 degrees of freedom. And so between here and here, in second case, I don't lose the p degrees of freedom that I'm losing up there. But so the problem now is, and let me go like this now, it is what about these other metrics here, where I just compute one single estimate, that is my A hat. And so what happens is I should lose only 1 degree of freedom. And so what is the implication of that? It is that if I just call before this matrix here, then the diagonal elements of B4 will be like this, which is a bit weird, but it is the first one has a chi-square with q minus 1 degrees of freedom, and all the other they are chi-square with q degrees of freedom. And so between here and up there, the first case, okay, and this one here, it may be between here and the case before, I just lose 1 degree of freedom. And so it makes full sense. But what happens is that the proof of this result here, it is a bit hard. I got the sketch of a proof for this, which is not a full proof, and it is very, very intricate. And so this is where I'm stumbling a bit, but then doing all kinds of simulations you can do, it is really confirmed that this is the correct result. And then it happens that for symmetrics defined in this way, the distributions are these. It means that lambda 3, and lambda 3, it is the likelihood ratio statistic to test the non-conditional horizontality. It has this distribution here, okay? Where we just get, for this first y, we have q minus 1 degrees of freedom there. The parameter is q minus 1 for this beta. For this one, that is dropping in the middle of these, and all these we just get only q. And for this one here, we also get a q there, and not a q minus 1 there. And then we can show that what happens is that then, if you just get a chart like this, we are looking for this likelihood ratio statistic, this one here, the test of horizontality, assuming coincidence. It should be the ratio between this lambda 3 we just got up there and this lambda 2. And so what we can do, it is from the results in this paper by Hogg that I referred up there already, we can show that this lambda 0302 and this lambda 2, they are actually independent. And so if you just plug these lambdas, if you just call the W's to minus lambda for lambda 0302, lambda 3 and lambda 2, we can write the characteristic function of W3 in this way. It means the characteristic function of W0302, it will be the ratio of the characteristic functions of W3 and W2. And so we know from the distributions of the beta random variables and the expression for each moment, we can get the characteristic functions of W3 and W2 in an easy way. We can get the ratio, and so the ratio is something like this. Then it happens that for odd p, we can work through the results, and so we can show that actually W0302, it is just a gamma random variable with this rate, this n minus 1 over 2, it is the rate and shape equal to p minus n minus 1, where n is the floor of p over 2. And so this is a very simple result. However, if p is even, it is not so simple. We just get something like this, plus another part that is a log beta. And so, for example, if I just screw up a little bit the data I just added and subtracted some numbers to each one of the months there to make them closer. So in this situation, if you compute lambda2, the likelihood ratio test for coincidence, assuming the parallelism, we should not reject H null. It means I can go to the test of horizontality, and then for horizontality, we just get these values for the original and the arc-sine transform data. They are again rather similar with a very small p-value. It means we should reject H null. We should reject the horizontality of the profiles, which is not a shocking result if you look at the plot there. Of course, once again, the plot is not showing everything. And so this is what I like to really show you. I think I did not go that much over time. And so we may have some time for some questions.
So, thank you, Professor Carlos, for your very interesting talk. Now it is time for discussions or questions, clarifications, etc. So we have about 5 minutes. Any questions from audience? Sir, your talk has been very interesting for me since I have been teaching multivariate analysis for many years. So all these profile analysis, we are teaching at a postgraduate level. And I hope these statistics can be converted into Pillai's trace, etc.
Well, that is another different approach. There is not a one-to-one correspondence. This is a different approach. Pillai's trace is another competing approach. But the problem is that I'm not sure we can use Pillai's trace in the high-dimensional case, because what happens is that some of the matrices, sample matrices, they are not invertible anymore. They are not positive definite anymore, because if n sample size is smaller than p, the sample matrices, the common MLEs of covariance matrices are not invertible, they are not positive definite. That is why I needed to just assume that population covariance matrices were circular and do the estimation in that way that I was doing it.
Okay. Another question is actually this assumption of circularity for covariance matrices. How it is justified?
Well, it is not that much justified, really. One case is it has as particular cases, sphericity cases, and also the equal covariances and equal covariances. But for the common case, the positive definite, there is not an upfront justification. What happens is I ran a lot of simulations, actually only for the two first tests, the test of horizontality and the test of equality assuming horizontality, and I ran it for a number of distributions. Normal distributions with only a positive definite matrix, and so an HNO, the rate of rejection, it is actually very close to our alpha, whatever alpha is. And also, I used other distributions that are very skewed, even the skewed normal, skewed T, even discrete distributions that are only living on N0, on the positive or non-negative integers, and in all cases, the type 1 error, it was very well kept. And so I would say that it is, although it looks like at first as being a very big limitation, it is not, because we can use it. And I compared the test with other 3 tests around, and the power out of H0, of course, under H1, it was usually larger than the common tests, some of the common tests that are around.
Okay, thank you. So any more questions? Professor Ghosh sir, you have some questions? DK Ghosh sir? Yeah. So in the absence of questions, so I will thank Professor Carlos and leave to Professor Satish Kumar. So thank you, Professor Carlos, for your nice and informative talk on multivariate analysis, profile analysis,
Thank you very much.
especially.
Thank you, Ethan. Thank you very much.
Sadish. Sadish, your mic is to be muted. Mic.
Okay. Sorry. Sorry. Thank you so much, Professor Kailo, for your very interesting and informative talk. In fact, we are very much grateful to you, Professor. And also, and thank you, Professor Jones, for chairing this session very nicely. And in fact, several has had to ask some questions, maybe there. And in the case of the serious questions, they will contact you via email or like that.
Okay. Okay, thank you very much once again. Thank you very much, Joseph, for chairing the session. Thank you very much, Professor Satish Kumar, for inviting me.
Thank you, Professor. Thank you. In fact, the
scheduled time.
Yeah, the right time we finished. Even then, a few minutes there.
We have 5 more minutes
For the next session, because someone has to clear or any clarifications required. We kept in mind that way. Anyway, we are very lucky to have your presence in this situation, in this conference. And youngsters are also especially very lucky to have your deliberations. And the next session, we have 2 speakers, Professor Ghulam Kibriya and Professor Peter Lohamander. I think both instead of Professor Ghulam Kibriya, he has some urgent matters during author of the paper, Nayam, isn't it? And the Professor Peter Lohamander from Sudan is also here with us for the second speaker. And Professor Darba Bhattacharya is here to chair the session. Welcome, madam.
Hello, Professor Ghosh.
Professor Ghosh, you have to.
Sir. I'm here. Thank you very much. How are you? How are you? Your mic is off. Mic.
I am fine. Okay.
Okay, doing fine. Still active.
Yeah.
Going to the department.
Going.
Okay.
I'm going to department. Actually, tomorrow we are organizing this program.
Oh, okay.
Because today is Sunday, the student didn't come.
Oh. I think Gautami, yeah. We have a few more minutes. You can just 2-3 minutes. You can wait, and I think Professor Gorsab is always with us, especially.
Gorsab has been to Palai many times.
Yeah. Sure will come.
Yes. So you should come once again.
Yeah. Right.
I'm now in Mahatma Gandhi University.
Now you join Mahatma Gandhi again.
I'm just after retirement.
Yeah. You are staying at Kajipalli.
Very young. But here, all the teachers have to retire at 56.
Very bad, very bad.
So I have retired 10 years back.
I know. After that, you joined the Rajasthan Central University.
Yes, then came back to Mahatma Gandhi University.
Then you got Mahatma Gandhi, yes.
Yeah, in other states, in most of the states, the retirement age has extended.
Not good, sir. Not good, sir. 56 is retiring age, not good. The teacher get trained only after 55.
Actually, that is the
In
After
our
that,
state,
get
it is
real knowledge.
65.
Yeah,
In
in
West
West
Bengal, it is 65.
West Bengal,
65. In
The
Central University,
Central University and many states 65. Many states. But there are 60 also in Rajasthan, Maharashtra.
In most of the
Karnataka,
states.
they have 60.
only 2-3 states only.
Yeah.
Yeah.
65 in Central Universities.
Gujarat has 62.
Oh.
Yeah.
Gujarat is only 62.
David Banks has joined.
Yeah,
Professor
Banks.
Banks. I have been to Hong Kong with your invitation.
Good.
You invited me for some session.
Good.
You have organized that session on financial modeling.
Oh.
Professor David Banks.
David Banks.
Yes.
Yeah, he's from Hong Kong, I know. He's from
2013.
Chime in because Duke is offering me a buyout. I'm going to be retiring next June, so I have one more year.
One more is more than 1 year.
1 more year.
365 days.
No, 70 actually.
Oh, okay. 70.
We do not have mandatory retirement typically in the U.S. And so Duke is worried about funding.
US there is not much retirement, or you can continue.
At a certain point, the department chair or the dean has a conversation with you and suggests that you should pursue other activities. But if you're famous, they'll let you keep working. I mean, if you have a Nobel Prize, you can work, as long as you want. They'll probably keep you on the rolls even after you die.
I think as a distinguished professor or professor of emeritus, one can continue.
Oh, yes, as a professor emeritus, you can continue to come to the office, you can supervise students. You can teach if they're not going to pay you for it.
In our India also, we have this system.
Here also, after retirement, we are not allowed to supervise teachers.
That is very bad.
Students.
That is very bad.
We can do only co-supervisors.
Yeah. No, not co also.
That can be up to 70 if you are active in teaching.
No, but in Gujarat, it is not there. Once you retire, you retire. When you can't, paper said you cannot guide PG, nothing, cannot do anything. Except Public Service Commission, you can become the selection committee member. That can be done only.
In politics, we can work.
It is politics.
There is no retirement at all.
Younger people was thinking that time, if they want to retire from all the activities, how we can go that post. But they never thought that after 3 years, we will be also in the same position what the senior were there. Now they will be repenting. Because Gujarat, they did this thing. All junior professors, they started a station, etc., Gherao, and did this thing.
So, sir, the time is reaching.
Yeah, Professor. Yeah. Gautami? Yeah. Gautami? Hello?
Gautami, please introduce the chair.
Okay, sir.
Okay. Yes. And let us welcome, please.
Welcome to the 11th technical session of WSTA 2025. We are pleased to have Dr. Durga Bhattacharya, Head of the Postgraduate Department of Data Science at St. Xavier's College, Autonomous, Kolkata, As the chair of this session, she holds a PhD from the Indian Statistical Institute and works extensively in statistical modeling and applications. Her research interests are Bayesian non-parametric modeling, Bayesian computation, biostatistics, multi-objective optimization, machine learning, and so on. Our speakers for this session are Dr. B.M. Golam Kibria from Florida International University, USA, who will speak on the topic The Impact of Penalty Parameters on Estimator Accuracy and MSE in Regularized Logistic Regression under Multicollinearity. Dr. Kibria has diverse research interests, including applied statistics, biostatistics, computational statistics, environmental statistics, and so much more. And we have with us Dr. Peter Lavmander from Optimal Solutions, Sweden, who will present on linear and non-linear optimization of international trade and tariffs. His main focus is management and economic optimization and also forest economics. Now, I invite Dr. Bhattacharya with great respect to chair this session.
Thank you. Thank you. Good evening, everyone. And it is my great pleasure to welcome you all to WSTA 2025, the 10th International Webinar on Recent Trends in Statistical Theory and Applications, and being held today on the occasion of National Statistics Day, commemorating the birth of the legendary statistician Professor Prashant Chandra Mahalanobis, a day dedicated to celebrating the vital role statistics plays in the evidence-based policymaking, research, and innovation. So I would like to congratulate the organizers, especially Professor Satish, to consistently provide us this wonderful platform of WSTA. So thank you, Professor Satish. And so we have here two speakers, distinguished speakers. I think Professor Satish has briefed us about Professor B.M. Golam Kibria not being able to present today due to other engagements, and his student Mr. Naim.
Yes.
Yes. So you will be presenting in on the impact of penalty parameters on estimator accuracy and MSE in regularized logistic regression under multicollinearity 9.
Yes.
Okay. So I would request you to kindly give a brief introduction, and I welcome you, Naim.
Thank you. So, may I share my screen? Can you hear me?
Yeah, please.
Yes.
Please.
Yes.
Yes. Can you see my screen?
Yes. Yes. We can see.
Yes. So So, good morning from Miami, Florida. So, it's a very sunny day here. I am 89 from Florida International University. I am pursuing a PhD in mathematical science, major in statistics. My major supervisor is Dr. Golam Kibria, but I'm also working as a graduate research assistant in a civil engineering department, majorly on transportation engineering as a data analyst. So today I will present the topic that would be my research dissertation topic for my thesis, PhD thesis, the impact on penalty parameters on estimator accuracy MSC in regularized logistic regression under multicollinearity. So I would like to thank Sinha Aziz, my co-author, also Dr. B.M. Golam Kibria, my advisor, for this work. So, is it moving the slides?
Yes, the slides are moving.
So, as we all know, the logistic regression is a type of generalized linear model that designed for a specific situation where the outcome variable is binary. So it takes on two possible values like yes, no, success, failure, or 0, 1, like this we call it. It is one of the most widely used statistical tools for classification and predictive modeling when goal is to estimate the probability of an event. And the logic simplifies the application across many fields like regular social science, machine learning, especially in machine learning, like acts as simple yet powerful baseline classifier. It is often used to like natural language processing when the like spam detection or K scoring. So logic is more than just a modeling technique. It forms the theoretical background of many advanced machine learning techniques like regularized regression, also the multinomial, the ordinal logistic regression, and logistic regression as a loss function. It classifies the is classification based machine learning algorithms like neural network. It can work on that also. So its simplicity, interpretability, versatility ensure that logistic regression remains the essential tool in modern data scientist toolkit. So challenges of multiplicity, as we all know, the multiplicity, the high correlation among the predictors is known as the multiplicity. This is one of the assumption of the classical linear regression model. So when there is multiplicity in the multiplicity characterizes the high correlation among the predictors. So it does not introduce the bias into the coefficient estimate, same as the linear regression model, but it significantly increased the standard error of this coefficient. So it inflated the standard error, lead to the decreased T statistics or Wallace statistics associated with the coefficients, which also reduce the likelihood of detecting the statistical significant effects. The increased risk of the type 2 errors, where the genuine relationship between the predictors and the outcome may be overlooked. So, as a result, the practical implication of multi-learning can lead to the misleading conclusion, ultimately, like the compromising the model's usefulness for both predictive and explanatory. So, uh, yes. Problem slide. Yes. So the high correlation among the predictors completes the identification of the individual impacts on the outcome, so risking the misleading conclusion about the influence. So interpretation of the odds ratio, which are the central to logistic regression, can be problematic. So with the inflated standard error, the confidence interval around the odds ratio broaden, making it difficult to draw precise inference about the magnitude of the effect. So this complicates the practical application of the model findings. So the regularization technique to mitigate the multiplicity, the Orlan Moran in 1970 introduced the risk regression for the classical linear regression model. Then the last will estimate they are also developed over the years, and over the years also around 300 plus the risk regression parameter estimators are developed. So most of the studies they focused on like the linear models or the mean square error, and the classification accuracy, especially in logistic regression, is often overlooked. So despite its potential, the logistic regression remains incredibly underexplored, and particularly in scenarios involving high multiplicity or non-normal predictor distribution. So this gap underscores the need of deeper investigation into the logistic risk regression performance and robustness under such complexities. Despite extensive research on the regression, relatively little attention on the logistic regression under the multiplicity. So that's what our study objective is, to study the compare between three risk estimators plus the logistic regression, lasso risk, the regularized and risk, generalized risk regression, and evaluate both MSC, mean square error, and the classification accuracy, and analyze the performance under the varying level of multiplicity and data conditions. So additionally, the real world data set will be utilized to corroborate the findings of the obtained from simulation, thereby demonstrating the practical applicability of the methodologies employed. So I start with the race regression that was first introduced in 1970 by Roland Conrad to mitigate the multi-quantity issue. This approach minimizes the sum of the squared while applying a constraint on the total sum of coefficient squares. So taking this equation and finding its derivative with respect to zero. So we get the estimator, the raise, and we can compare with our OLL, the ordinary least square, the regression estimator. There is a bias parameter like k. K is known the raise or shrinkage estimator, and it needs to be estimated based on the observed data. And we can get also the MSC, the mean square error from the estimated raise model. And here we see the lambda I1 to lambda p are the eigenvalues of the X transpose X matrix. So now we like to introduce the logistic regression framework. So we know the OLS, the ordinary least square, for the estimated value. So limitation for binary response, we do the OLS not appropriate. We do the logistic regression. So we have the binary Bernoulli setup for logistic regression. So if we do the maximum likelihood for the logistic regression, we take the log likelihood, we did by this can be achieved by the derivative of the expression equals to zero. As a result, the maximum likelihood estimates are found by solving this equation. Is the non-linear in nature, so Newton-Raphson method must be developed to find the solution. So as a result, the solution is the previously mentioned equation. This equation can be obtained through the subsequent iterative weighted least square method. So the asymptotic covariance matrix of the maximum likelihood estimator is the inverse of the matrix of the second derivative. So, and a key drawback of the maximum likelihood estimate is that its asymptotic variance can inflate due to high values. So that's why in to mitigate this multi-quantity issue in logistic regression, Schaefer and et al. They in 1984 they proposed the logistic Rees regression estimator. So here you see in the previous is with the maximum likelihood estimator that we from our logistic regression. So it incorporates the introduce the bias estimator here. So, so as I said earlier, like numerous Rees estimators have been suggested in the literature for different kinds of models, as mentioned previously, to determine the Rees parameter k. So for this study, we selected only 16 Rees parameter from most effective estimators identified Marmi et al. He studied 366 Rees estimators on based on the previous